He's still not there. Shall we call him, do you think?
I send him a WhatsApp message now.
Okay,
so
yeah, WhatsApp shall be efficient, yeah.
I'm not sure. I hope it works.
I also sent an email to them, so I think we did our.
Jan.
Okay, Nicholas is here.
Hello, Jan.
The cell phones. Good morning, Jan.
Yeah. Jan, as you took my link, you appear under my name, but it's great. Please do great show.
Excuse me, you are on YouTube.
Actually, Jan,
yes.
Since you use the link of Nicholas, your name appears as Nicholas, so you can rename it now.
How to rename it?
On your video, on the right top, you have these 3 dots.
I see it, yes.
But anyway, you have somebody whose name is Schmutz under your organization by method test. So maybe a cousin of mine, I don't know.
You have the company name at the end or not? No.
Yeah, it's up to you. Okay. I think like you can all make such changes. Okay, yeah. So we are just missing Andreas now, but since Jan will be the first speaker, I think we can start it and I will make moderation. Yes, please.
You are now in YouTube Live.
All right then, thank you.
Look into chat, I will forward the link.
So, Korkami, we're still missing one presenter.
Yes, we are missing Andreas. So let's wait a few minutes also for the audience and our one speaker.
Maybe Jan, you have the phone number of Andreas. Maybe you can just WhatsApp him.
Can check, but I guess not. What
I don't think I have the cell number either. I can search for the office number.
I only have his email address. Can check.
You don't have by task 16? You don't have it?
No, normally we don't have phone numbers only. No.
The organizing committee, can you share this introduction presentation like from the organizer team so that we have the landing presentation? Then in a few minutes, I will open the session. Can anyone from the organizing committee share this one page of slides that we see the workshop details? Perfect, thank you.
Okay. I have the number of Andreas. I will call him right now.
Oh, okay. Yeah, I also found it, but go ahead.
Okay, I will use my.
But just now, yeah.
Hello, everyone.
Hello, Ismail.
How are you doing?
Fine. I think we are already in YouTube
Please do not touch the mouse. Just to share the sound. Just to share the sound for the presentations.
I am trying, just a second.
Give us the 30 seconds to
share the sound.
To share the sound. Okay. Yeah.
So hello, everyone, all the speakers and the audience. Just let us give a few minutes to have all the onboarding is done, and I will open the session in 1 minute. Okay, so I think we can start. So hello, everyone. Good morning, good afternoon, or good evening.
Excuse me, a few minutes to allow participants to access the platform.
Okay, all right, sure. And can you also make the full screen of the presentation? I'm not able to do that, or maybe it's loading.
Yeah.
So the organizing committee, is it okay to start now?
5 minutes, 5 minutes, only because as mentioned in the program, we start at 9. Okay, now we are 115 participants are joined now, are joined the conference.
Okay.
Are waiting for others. 5
All right.
minutes. Okay.
Okay, yeah, let's wait 5 minutes.
You can follow participants. You click on participants on the Zoom menu to see the participants and panelists, attendees and the panelists.
Okay. So hello, everyone. Just for your information, we will start the session in 2 minutes. Organizing team, is it okay to start now?
Good morning. We start today the second day of the International Renewable and Sustainable Energy Conference. Today, Mr. Golim Teller will share the session of the advances in renewable resources forecasting and their economic aspects. Mr. Gunnar Tenner is a specialist in renewable energy forecasting and wind energy expert with more than 10 years experience in the renewable energy academia and industry. He has mechanical engineer background with a master degree in energy technology focused in wind energy power from Uppsala University. He is consulting renewable energy producers and electricity market player get best use of energy forecasting. Mr. Golim, the floor is yours.
Thank you so much. So hello, everyone. Good morning, good afternoon, and good evening, wherever you are attending this virtual event. So first of all, we would like to thank you for all the organizing team to gather such valuable conference. So it's the 9th International Renewable and Sustainable Energy Conference organized by like a part of the branch of IEEE. So we are in the second day and the first session in the workshop 3, the advances in renewable energy forecasting and their economic prospects. So I also would like to thank this workshop organizing team, Abderrahim Yamrani, Ismail Belhai, and Abdelali Dijdia to gather all the experts from the global markets who will share their experiences and the competence in this power forecasting area. So maybe just a short introduction. This workshop is specifically focusing on the energy forecasting, and we will be discussing the market of renewable energy forecasting, its economic prospects, and the technological advances of forecasting methods deployed in the industry and the ones still in the RD. So the workshop will also be an opportunity for networking and discussing promising forecasting tool and their deployment in the context of today's big issues such as smart grids, mobility, and the trading. And we have some key topics to mention here: the importance of the methodology in renewable energy, the state of art renewable energy forecasting, existing methods in the industry, the market of renewable energy forecasting, and economic prospects of renewable energy forecasting in the context of smart grids, mobility, and the trading. And we have 4 invited and keynote speakers for this session. And there will be a second session on Saturday, actually, which we will continue our discussion on the power forecasting. So today, our experts from the industry, actually, we gathered the topics mostly focus on the solar forecasting and what's additional methods or some brand new technologies has some improvement in the solar forecasting area of it. And the release agenda, I mean, we changed the presenter order a bit in order to avoid some repetition and make it more consistent with all the experts and the topics that we'll talk about. So the first speaker will be Jan, the second will be Stefan, the third will Andreas, but he's not here yet. We will see if he will join us. And finally, Nicholas will make the speech. So that's why I am happy to share the floor to our first speaker from Meteorite, Switzerland, Mr. Jan Remund, and he will talk about the prediction of solar radiation and photovoltaic production today. So please, Jan, you can also make a short introduction about yourself and your company, and the stage is yours.
Yes, thank you very much, Gorkem, for this introduction. Hello, everybody from my side. I'm Jan Raymond. I'm working at Metrotest. I'm the head of climate and energy here in Metrotest. It's a company in Bern in Switzerland. And I'm also the task manager, which is a new term of the IEA PVPS task 16. I would like to share my screen, which is not possible at the moment yet. So like this, I would then start with my presentation. Now it should work. Yeah.
Are you going please to share your screen?
I just see it, yes. And I guess you will see it now, my screen. Is it okay? Okay. As I said, I will talk about the state of the art of solar and PV forecasts, not from my main point from the company, but from the IEA PVPS task 16. PVPS task 16, that's a group of about 50 organizations from 19 countries, which are working together. It's mostly research organizations. There are also med services and service providers like Metrotest or other companies working in this field. Also, Morocco is part of, and IRSEC is taking the part from Morocco of this team. Metrotest is a SME founded more than 40 years ago. We are located here in Bern in Switzerland. Okay, I will talk about first an introduction about our task 16 solar resource handbook, because there are a lot of topics described, also handling the forecasts. Then I will go to forecast topics, showing which forecast for which size and which time resolution. Then I'm going to short-term forecasts, talking shortly about numerical weather prediction models, and coming to the uncertainty of the forecast. And the final point will be about firm PV power. And I will show you what we mean with this term. Okay, why we are working together on this worldwide scale. Solar resources are the fuel of PV, CSP, and solar thermal energy. And as you know, PV gets bigger and bigger, and also in the States, like in Europe, the penetration gets really high. So the value of meteorological information is getting higher and higher. We are making benchmarks. In the benchmarks, like the All Sky Images benchmark, which will be described later on this morning. We make state-of-the-art descriptions like the Solar Resource Handbook. Finally, we try to lower the uncertainties of the solar resources, which lowers then the cost of the implementation and makes more easy to implement more PV. This is our handbook. It was released in May of this year. It includes basics, it includes state-of-the-art science, and also it's quite huge. It's about 350 pages, so nobody will read it the whole, but you can select your topic you are working in, like the forecast chapter, and you will get a good overview of what is the state-of-the-art and what is the science doing at the moment in this field of work. We have also made this table there. You see there which kind of data, of meteorological data, do you need for which size of your installation and also for which phase of your planning. So first phase is pre-feasibility and planning, then is feasibility, due diligence and finance, and then finally operation and maintenance. And that's also where forecasts are needed. You see it's mainly for the medium and large scale systems, where you need local measurements and forecasts for your installation. Of course, also then going to a larger area for the distribution systems or the transmission systems, there the forecasts are also needed. What kind of forecasts are optimal for which size? So there's a spatial dimension and also a forecast horizon dimension. And for each part, you have an optimal method. Going for seconds, it's mostly using the measurements at the point itself. Going to minutes and hundreds of meters, then the cloud motion, that's CM, and SI is the all sky imagers are a good option. We will talk about this later on. If you go to a few hours and kilometers in the resolution, then the cloud motion satellites are the best method, and go then more than 6 hours ago for the forecast horizon, and in the size of 10 kilometers, then the numerical weather prediction models are the best. I will show now 4 examples of forecasts, two about nowcasting, then one about numerical weather prediction based forecasts, and then this firm PV power method. One method to make forecast, I'm talking not about all sky images today, because this is handled then later on by Andreas and also by Stefan and Nicolas. So I left this aside. This is an alternative method here, which is, you see this publication by CSI in Neuchâtel. They are using all the PV installations in Switzerland. They were all available, and there are so many nowadays that you can make forecasts based on them. So you know the state of the systems. Of course, there's a lot of noise in the signal. You have to filter this out. This is done by artificial intelligence. And currently, we are making a benchmark comparing this with a cloud motion satellite method, and we are looking which one is more accurate. This is done not only in Switzerland, it has been also largely published by another group of our IEA team, by the University of Utrecht, who has a similar work done. Of course, this can be done only in regions where you have a lot of small systems, which are also connected to the internet, so you get online data. This is a method MetroTest is providing as a solid.metrotest in our forecasting. We are using a cloud motion satellite and enhancing this by the ongoing measurements, the local measurements. You will see this perhaps also later on. If you combine the satellite data or the all sky images data with ongoing measurements, normally the quality gets quite better. And you see this also in other studies. It's about 20% you can gain if you use this ongoing data. And also here we are using in this method not just always in all cases the measurements. We are using it mainly in the case where it is stable, not to include a lot of extra noise. And also here we gain about 20% of accuracy when you include this kind of a smart persistence. A few words about numerical weather prediction forecast. So this is the state of the art for the methods for a time horizon more than 5 hours ahead. If you are using all sky images, this is up to, let's say, 20 minutes. If you're using satellites, normally you can use this easily for the next few hours. But more than 5 hours, normally the clouds are dissolving or there are new clouds. So this is can only be handled by forecasting systems based on models. You can't use them, you shouldn't use them as they are, not a direct model output, but you should use them as statistically corrected. For example, as a model output statistics, this can be done with machine learning or without machine learning. Also, automatic methods based on simple linear regressions are quite useful. If you use one single model, the IFS ECMWF is still to be beaten. It's clearly better, for example, than a GFS model from the United States Weather Service. The problem is, of course, the IFS model is only available for scientific use and not free. Another alternative is WRF Solar. This is regularly updated also now with a spectral model. They're doing a lot to enhance the quality for solar forecasts, but still, if you compare them one-to-one, normally the IFS has some points higher or somewhat better looking at the uncertainty. A good way is also to combine all different models, the all sky images, if we have them, the cloud motion, satellite data, and also the NWP with a machine learning technique, also to combine multiple methods like GFS, IFS, all combined by machine learning. That's quite the state of the art. And nowadays, probabilistic forecasts are getting important in the wind forecast. This is quite the case since a few years. In solar energy, this is the same. I will talk about this on the next slide. Just to give you one number about the RMSE, I'm coming also to the uncertainty later on. If you go into a 24 hours forecast, the forecast of a 1 hour forecast average, it's about 30% if you make it relative to the average insolation. A new benchmark about forecasting will be done in the next few years also by our task. One word about the probabilistic forecast. It's physically adequate, as I would call it, because the atmosphere is a chaotic system and you will never know the exact position of a cloud 24 hours ahead. So it's good to give some probability where this cloud could be and what is the distribution of this. And coming to this leads to this probabilistic forecast where you give some probability of radiation. In this case, of course, this is determined mainly by the position of the clouds. Of course, you get a lot of new systems and statistics. That's perhaps the bad news about this, but the industry will learn to work with this. They're just not getting one simple figure, but they have to learn how to use them in their downstream models. Uncertainty, I announced one word is 30% RMSE. But actually, that's quite a difficult question, how to measure this uncertainty in a good way. Normally, this RMSE or also the mean absolute error are quite standard. Often it is taken into relation to the average radiation, but partly it's also done by the installed capacity. Of course, this leads to a lot lower values. The error measures are normally the standard ones, as I mentioned, the RMSE, the MAE, and more. If you're going then to, of course, to the probabilistic forecast, then you need more new measures. I will not show them today. This would take too much time. Of course, skill course, how good are you in getting some, for example, a sunny phase or a cloudy phase? And persistence are very important. Persistence has always to be beaten. So if you keep the sun more or less in a constant way, only taking into account the path of the sun, this is always the basic benchmark which has to be beaten. Normally and also advisably, we make analysis of the forecast areas in respect of the solar elevation and also of the cloud conditions, as we will see also later on. Here is another way to measure the uncertainty. You see here a forecast PV and also the reality of the PV production. And you have some hours with undersupplies and some hours with oversupply. And in this case, we try to model this and say how much of cost you would have to produce this if a battery would be needed to store this energy and to give it back to the grid. So somehow you have then the penalty for a real system in a real world, because only the RMSE are just general values which are partly depending on a use case quite artificially or theoretically. You see this kind of they have now a price, $400 to $1,600. This is in relation to the kilowatt peak installed of the PV. And then you see how much you have to pay for this storage if you would have it based on the not perfect forecasts. As I said, forecasts can never be perfect. And like this, you have some relation how much is the worth of a good forecast. To the left, you see the State University of New York models, and you see the 1 hour, 3 hour, and 24-hour forecast. Of course, the forecast errors get up high and high. You see the smart persistence for 1 hour forecast. It's the cheapest, so this is a good way of forecasting. You see the GFS model, which has higher levels. You see the ACMWF IFS model, which has some lower errors. Among the GFS, NDFD, and the meteorological models you see to the right, you see this IFS model has the lowest uncertainty. The SUNY models includes different global models. Additionally, they use also satellite data. And you see these mixtures of all gives also quite low uncertainties. Going to the last phase now, to the firm PV power. At the moment, production is still lower than the load, but we will get soon in a few years in the situation that production will be higher than the load. And this is a totally different situation in future. We have to think how with PV you can make a system work 24/7 all the year round, based mainly on solar and also on storage. And of course also on wind and on hydropower if available. So you can also, I made a few phases, 1, 2, 3, that's artificial to some extent, but to see it is a major step if you go from phase 2 to phase 3, which will be in the future. To show an example of the current phase, this is a work which has been done by Università Tor Vergata and IRSEC in Italy. They looked how much you will gain in RMSE first, based on optimal forecasts. And this optimal forecast is also a combination of different model techniques and also artificial intelligence. You will get then some improvement, quite a lot. And also, if you go into a larger area, always the forecasts are better. But as I said, you don't know where the cloud position is tomorrow. If you go to a large area, this error is smoothed out. And like this, the larger area you make a forecast, the lower error you have. In this case, it's the case of Italy. They have at the moment about 6 market zones. If they would go to 1, they would gain quite a lot of uncertainty. Here the RMSE is in relation to the installed capacity of the whole Italy. That's why the figures are in the area of 5 to 8 and not to 30 to 40%. You see here then in figures now, not in RMSE, but in the cost of million euros. Of course, if you go to an all Italy market, you would need some grid reinforcement. This would cost about 7 billion euros. If you look at the imbalance cost and with optimal forecast and optimal handling, you would gain 500 million euros. So this would be paid in only 12 years, which makes the case quite easy. So to enforce the grid would help to have lower costs for PV integration. You see also this figure here in Germany. As I said, this we will get soon at this threshold where, let's say here in this case, it is wind, it is PV and solar and some must-run hydro, where this gets higher as the load. And this will get higher and higher, of course. Of course, there must be some curtailment, there must be some storage, that's clear. You see here another example, theoretical, you see the yellow line, this would be the PV load, and the black line would be the load. So somehow we have to get to this situation where we have some peak shaving and storage, and that's this firm PV modeling, where we try to look what is the optimum between storage and overbuilding and curtailment. So the main point here is that the cost of storage will be higher as the cost of PV. This is foreseen for sure at the moment the case, but it will be also in future. So our sizing is always cheaper, and finding the optimum of this is the final target of this work. Here, this is a specific activity we have in our IEA task. You see here, if you only have the cost of production of PV, that's quite cheap. That's quite an easy thing. But of course, if you have no curtailment at all, you would need a lot of storage, which will be very expensive. If you have then a lot of curtailment, this is the PV overbuilding range. You get, of course, it costs more and more to make PV, but there is an optimum at this point C, and this is looked for in several studies. For example, there has been one in the United States, or several ones, one in Minnesota, here one in around New York, and more in the eastern part. They showed that with 20% of curtailment, with 30% of wind, 65% PV, and 5% gas, you will get overall LCO costs of 3.5 US cents per kilowatt hours. That's cheaper than it is today. You have also another study done in Italy together with the team I showed the slide before. And at the moment, Clean Power Research and State University of New York and Method Testing is doing a new study in Switzerland where we are looking for this optimal. The biggest issue of this is not finding this optimum. This will be quite clearly defined, but another question, of course, is how to get to this with simple PPAs, and so it is not possible. So we have to find new incentives for this. Coming to the conclusions, please have a look at the Solar Resource Handbook. There, the basic concepts, the state of the art are concluded. If you go into the forecast, I think it's no size fits all. So you have really look at what size and temporal and spatial resolution you are working on. Nowcasting with satellite and ground data is for sure useful. If you go then to really high penetration, think also about not just making kilowatt hours, but also thinking at the capacity and make PV deliver electricity 24/7 and also for the whole world. Just a last thought about this. If you really have a lot of curtailment, then of course forecast will be a little bit more important compared to this, but the know-how about integration gets more and more important. That's all from my side. Thank you for your attention, and I'm happy to have your questions. And also, unfortunately, I have to leave around 10 o'clock, so I will be not available for this discussion today, but on Saturday, I will be there again.
All right. Thank you so much, Jan, for an insightful presentation in information, and maybe a practical reminder to all our audience. I think like some of the questions were put in the chat, but I encourage everyone to raise their question on the Q&A button on the Zoom function, and again encourage you to ask specific questions on the power forecasting, not on a general question. It will be hard to answer them in this workshop focus. So I think, I see two relevant questions on the forecasting. So let me raise this directly to you, Jan. So the first one was, what about using inverse methods for solar prediction forecast? I'm not sure, I haven't heard about this inverse method, but if you have some feedback.
Oh, I don't know what is meant with inverse questions. So I could have a look at this and answer it on Saturday, perhaps. No.
Okay, yeah, maybe like we can leave it for the later discussion if we have more information. And the second question was from Rahali. When having a short duration, let's say a few months of ground measurements from soiling and albedo, how to forecast the long-term yield uncertainty?
Yes, soiling and albedo is a relatively new topic. We are looking at this in also an activity. Normally, if you have making DNI and GHA measurements, you need 1 year. How much of what is the optimal duration for soiling? I don't know at the moment. Of course, there are some seasonal effects in many areas, and also albedo has many seasonal effects. So only a few months is perhaps not good, but I wouldn't know any study who would show this. Perhaps then Stefan knows a bit more about these topics. He's the specialist in our task about this.
Okay, yeah. Thank you so much. We have also two short ones. Can we rely on satellite data only for areas with no PV data?
Normally, yes, it's getting better and better, satellite data. And if you don't have any ground data, I would go for this, yes. They're quite reliable, yes.
And finally, won't forecast be equally important to drive and manage curtailment?
Both will be important, of course. At the moment, it's more the forecast. If you can, it's more accurate, then you will gain a lot. But in future, where you have really heavily or a lot of curtailment, of course, it's a little bit less important. But that's just a small change of the shares. But both is important for sure.
Okay, thank you. And maybe the final one is from me. Since you have mentioned this like working task of 16, IEA 16, I also like had some contribution to this IEA wind task 36, which was mostly for the wind forecasting. So what is your personal, or maybe like in this task 16? I think eventually all the players that we have, I mean, we have like all of us has some like internal methodologies and so on. But do you think in the near future, we will introduce some, like, let's say, an IEC standard on the power forecasting, especially addressing to such definitions like uncertainty and so on, which was really, I mean, should we have some standard methodology and the definition for the market? So what is your opinion on that? When do you think we will get an exact forecasting standard to define such terminologies?
It would be good to work together. So we work a bit together with Task 36. We started to do that,
yeah.
And we want to enhance it in future because there are similar questions. I'm in the forecast. There is not that much defined in standards. In measurements, yes, but in forecast not. So there is quite a lot of open space. But we try to give also in our handbook some answer to these questions about these RMSE questions. Of course, I could imagine that we also get to this state that we make IEC standards together. So I would be open to do this. Yes.
Exactly. Okay then. Thank you so much for your presentation and the contribution. Now we can move to our next speaker, Mr. Stefan Wilbert from German Aerospace Center, the team leader of energy metrology. He will today talk about the all-sky imager-based radiation forecast for solar energy systems and the electrical grids. So stage is yours, Stefan.
Thank you very much. I hope you can hear me clearly.
Yeah.
Let me just share the screen. So I hope you can see now the presentation, the first slide in full screen. Yes. Can you please confirm?
Yes. Yeah.
Okay, very good.
Yeah.
So welcome to my presentation on all sky imager-based radiation forecasts for solar energy systems and electrical grids. I present this on behalf of a group of colleagues from DLR from two institutes, the Institute of Solar Research, where I lead a research group called Solar Energy Meteorology, and another group in the Institute of Networked Energy Systems in DLR in Oldenburg, which works also on solar energy meteorology. In my presentation, I will give an introduction to all-sky imager-based nowcasting. That will be the biggest part of the presentation, also to introduce the topic so that we have a good basis for the next presentations by Andreas and Nicolas. Then I'll come to the validation, and I'll also say a few words about the uncertainty of all sky imager forecasts. I'll quickly talk about the application of all sky imagers, which we will hear more about later as, let's say, an appetizer for the topic. And then I'll come to the topic of networks of many all sky imagers. So let's say 30 all sky imagers or something like that. So let's talk about the approach in general. We can see here an all sky imager. This is a simple fisheye camera that creates RGB images, just as your cell phone. There are also other types of all sky imagers that use curved mirrors and downward looking cameras, for example. There are also infrared cameras that can be used, which allow you to derive further information on the clouds. But this kind of simple fisheye camera is the most common kind. These sky images look, for example, like that here on the right-hand side. So we typically have a very bright season close to the sun, which is a general feature of these images and also a complication. And you can clearly see the clouds, at least if they are a little bit far away from the sun. In addition to the camera, you also use radiometers for the forecasts. Most of the cases, there are pyranometers at the PV power plants or a pyrheliometer in the case of a CSP power plant, and you take this kind of irradiance measurements to create the best possible forecast. Many systems use only one all sky imager, but there's also the option to use more. If you are working within a bigger power plant, maybe working with 2 or even more cameras can make sense, as we will understand later also. So now that you have at least one of these all sky images and a history of those from the last minutes, what is the next step? The next step is the cloud detection. For many years, the cloud detection was done in most cases with so-called clear sky libraries. This clear sky library is a database which stores the red to blue ratio of each camera pixel based on a large number of photos that you took under clear sky conditions. And then you analyze this large number of photos and write the red to blue ratio of your images in a database sorted by the pixel zenith angle, the distance of the pixel to the sun, the air mass at the time of the image acquisition, and also a turbidity parameter, for example, the Linke turbidity. Then if you have a new photo that you want to analyze, you convert it into red to blue ratio, and then you create, using this clear sky library that is shown here, a clear sky image that you would expect for this point in time and the current turbidity conditions. So this image here is created from your library. Now you subtract it from the current red to blue image. And in this image, it's easier to detect the cloud, this different image, than in the original image that you had at the beginning. So that was a very common approach, as I said. Now, artificial intelligence is getting more and more important. So this is one of the many alternatives that you have for the cloud detection. And now it seems as if artificial intelligence is the most accurate option under the many available options. For example, you can use convolutional neural networks, and some of the methods also do not only allow to distinguish between clouds and the clear sky, but you can actually also classify the clouds in low, mid, and high layer clouds. this is shown here also in the example where you have a very complex situation with thin clouds here and directly in front of the sun. So you actually see also this halo. And then you have also lower clouds, and all these different kinds of clouds are then detected by the method. Now let's come to the next step, the cloud modeling. This is also strongly connected to the cloud tracking, so I'll explain it somehow together. Also here, the situation changes a lot depending on the kind of camera that you use. So if you have only an RGB all-scale imager and only one has to consider that you cannot measure the cloud height. This is shown here in the sketch. So you have your camera and you only know the angular region that is covered by a cloud that you see. But if you now want to know how high it is, you have a problem, because this angular region can correspond to very different heights, and you will not be able to detect the height exactly. Then in terms of cloud speed, this also brings along a limitation. You can detect the cloud speed in image series. So maybe the first image shows the cloud here, the second one here. But again, you only know the angular position. And depending on the cloud height, this angular position corresponds to different speeds in meters per second. So you only know the cloud speed in pixels per second, which is another thing that we have to consider for using this kind of information then. Basically, with this kind of setup, you are limited to forecast only for one location, and this location is the location of the camera itself. Of course, it's also interesting to have such a forecast, and if your power plant is not really big, maybe it is very useful still, because it is representative for the rest of the power plant too. However, for big power plants, maybe you want to have a more accurate kind of information, and also you want some information about the spatial variability of the irradiance. So in this case, you would work with other setups with, for example, at least 2 cameras or infrared cameras, or you would also consider other sources to measure the cloud height, for example, ceilometers that use LiDAR systems to measure the cloud height. If you do that, and if you then have the cloud height, you are actually in the position to calculate irradiance maps. And not only you will have then information for the camera position, but also you will have the irradiance information for a few kilometers away from the cameras. So maybe you can cover 10 times 10 kilometers by using 2 cameras. In the case that you derive the cloud height, you also have to do a shadow projection. So basically you have to connect the clouds to the cloud shadows on the ground. For that, you can also even consider the elevation of the ground. So maybe your power plant is located on a complex terrain with some hills, and yeah, you need some kind, let's say, of ray tracing method to determine where the clouds are falling. The clouds, however, do not fully block the irradiance at some point, sometimes at least, and also the clouds affect the diffuse irradiance. So you need also some information on the radiation, the radiative effect of the clouds. This can be done if you have also radiometers. And here I present you an example for the DNI. So let's say first there is no cloud masking the sun, so you measure the clear sky DNI. Then later a cloud is masking the sun, and you can measure by comparing the 2 DNIs the transmittance of a given cloud. So that's nice. However, in most cases, the clouds have not thrown a shadow on your radiometers yet before you want to forecast their effect. on the radiation. So you need to estimate their transmittance. And this can be done, for example, based on the cloud height estimation, because the cloud height and the cloud transmittance are quite strongly connected. Low clouds are very often really optically thick. They block a lot of irradiance, and high clouds are very often quite thin and let some radiation through. Then finally, you come to the point that you have an irradiance forecast. If you combine all these steps of cloud tracking, shadow projection, and cloud radiative effect. And this is shown here. So we have a 3D representation of the clouds, the terrain, and the DNI map on the ground. You can see on the ground there are two red positions. Those mark the two all-sky images that were used to create the forecast. And you can see the clouds in the sky with red lines indicating their cloud velocities. On the ground, you can see that there are some shadows at darker regions, and you can also see that there is some ground model used to describe the elevation of the different areas. In this case, we covered about 6 × 6 kilometers with the two all-sky images. So now I explained to you like one of the typical procedures, how you derive the irradiance forecasts. If you now combine the irradiance forecast with the PV module or CSP model, you can also create the power forecast. And actually, there is a lot of different approaches. So that's the most common approach, let's say. But variations of all the individual steps exist. A very big variation, let's say, is one that uses artificial intelligence. So as I mentioned before, you can use artificial intelligence in the individual processing steps, but you can actually also do so in a much more efficient way, let's say. So you directly connect the images to an irradiance forecast with AI. There are some papers already out on this, and I present you here one. With that, I want to come now to the validation of all-sky imager systems. The validation is usually done with common error metrics, such as the root mean square deviation, the mean absolute deviation, or the bias. Also, one can calculate skill scores. So skill scores compare, for example, the RMSD, the root mean square deviation of a certain forecast model that you want to evaluate, to a reference forecast model. This reference, in the case of all sky images, is often the persistence forecast. Persistence forecasts are created based on the irradiance measurements, and then you assume that the cloud conditions do not change and only the solar position will change to derive a forecast for the next minutes. You can also validate all sky imager systems in terms of application-specific parameters. So, for example, ramp predictions can be analyzed, or you can even go so far to analyze the economic benefit that you have by applying the all-sky imager. However, the latter is still not common because it's also very complicated and depends on many power system parameters. The validation can be done at different sites and under different conditions. And this brings along a complication because the validation results depend strongly on the site and the specific conditions during the validation. On the right-hand side, we see the results for a study that analyzed the same two-camera system at 5 different sites. The validation periods are given and the sites in the table. So it's 2 sites in Spain, 1 in Portugal, and 2 in Germany. And the validation periods varied a lot between 3 years and only 42 days in the case of Portugal. So in terms of RMSD and MAD, we see the results on the right-hand side. The RMSD and the MAD are plotted as a function of the lead time, so how far away is the forecast in the future, and the different colors refer to the different sites. You can see in the RMSD that there's quite a big deviation, especially between La Africana, the Spanish power plant, and the other results. In La Africana, actually a whole year was used, but still it's very different from the other results. And also another deviation is from Evora. Here in this case, one could say, yeah, it was only 42 days, so maybe it's a very different kind of condition, maybe very complicated days were used. But it's really difficult to interpret these kind of results without knowing more about the validation conditions. Therefore, it's often helpful to separate the data set in classes, for example, variability classes. You can also separate in different days, depending on the cloud conditions, for example. But some separation is useful to describe these errors better. In the study that I show here, the DNI was classified in variability classes from 1 here, clear sky, to some very thin clouds that don't reduce the DNI a lot, then thicker clouds at times, and then even thicker and more frequent clouds until we come to 8, completely overcast with only some gaps between the clouds. The results for each individual class is shown then here in terms of MID, the mean absolute deviation. We can see that in particular for the classes with low variability, so here these first two, the results are very closely together now for all the different sites. We can also see in general that with increasing variability, the deviations increase. And then if it's getting overcast fully, the deviations fall again. The most complex classes are the ones with the highest variability. If you want to compare different forecasting systems, this dependence on the validation conditions is a complication. The best solution here is to compare systems operating at the same sites and for the exactly same time interval. Very often, as I said, comparison is done with persistence. Here we see the results in the graph for GHI and DNI in terms of RMSD as a function of the lead time. We can see that the lines without markers related to persistence are much higher than the lines with markers which relate to the all-sky images. So we can here see that the all-sky images actually bring quite a strong benefit compared to using only the simple persistence approach. If you want to compare different all-sky imager systems, this is much more complex because typically they are not used at the same site. Fortunately, the IA task 16 allowed us to organize a benchmark. We brought 5 different all-sky imager systems to the same site and operated them in parallel, and we will certainly hear later about this. Now a few words about the uncertainty of all-sky images. So there are certain uncertainty influences that we have to consider. The solar position is one. The cloud height and speed is relevant. Then depending on the cloud types and the complexity of the cloud layers, the uncertainty will change. Also, simply the image resolution of your camera system has an influence. And if you work with more cameras, also the distance between those cameras is important. If you know how the different influences affect the overall result, and if you have knowledge of the error metrics for different variability classes, you can estimate the overall uncertainty that is expected for a certain condition. And this was done in the example on the right-hand side here. So you use, first of all, the method I've shown before to derive a forecast. This is shown here in the center. So we have first the DNI map for the time of the image acquisition. Then you have the DNI map for 4 minutes in the future and the map for 8 minutes in the future here. And then you create maps of an upper limit here and of a lower limit by adding or subtracting the 1 sigma uncertainty. We can see here the map gets brighter in the upper limit case, and also for this certain method, the size of the cloud shadows is reduced. This goes so far that for higher lead times, where the uncertainty is higher, cloud shadows might completely disappear. For the lower limit, it's the other way around. So the cloud shadows are getting bigger. We can see that then part of the cloud shadows actually are connected to each other. So for the uncertainty estimation of such DNI maps or irradiance maps in general, we have to consider that the position of the cloud shadows is uncertain, and this uncertainty influences possible irradiance forecast at a certain point a lot. So if you're close to a cloud shadow, the uncertainty of such a DNI map can be quite high. Now a few words about the application of all-sky imager data for solar power plants and electricity grids. In PV plants and also for the grids, the control of ramps is important. A ramp means here a strong change of the PV power. At times there are limitations by law that only allow you to change the power output of your PV plant in a certain way, let's say 10% per minute, something like that. And in order to comply with this law, with this ramp limitation, mostly battery systems are used. If you combine the battery system with a forecast, this allows you to work with a smaller battery capacity and battery power, and also it helps you to use the battery less and to avoid unnecessary cycles. This then means that the battery lifetime is increased. There's, for example, this one study that I show here from Rio, where they reduce the battery capacity by 10% for the needed smoothing by using also all-sky images. In off-grid systems where you combine PV with diesel systems, you can save some diesel fuel if you use the all-sky images as also described in this publication by Jamal. For CSP systems, there have also been some studies here. A potential increase of the yield by 2% was found when the DNI maps were used to control the power plant better. This was for a parabolic trough power plant. For tower systems, there's also research ongoing, and also we expect some yield increase because of the use of the DNI maps and forecasts. In general, forecasts are very important for power plants to participate in an efficient way in the electricity market and also to avoid fines. Now, if you have a better forecast for the next 20 minutes, this also helps you to participate in a better way in the electricity market. However, Of course, 20 minutes is not so much for the electricity market. There you are looking typically at longer time windows, at least maybe a day. So an important thing is the combination of different forecast methods. Jan already introduced all the different methods, and the all sky imager based method is only one of those. So it's really important that you then use all the different tools to combine satellite data, weather model data, and also other methods that are just relying on the time series, such as persistence, together. So if you know their uncertainty, it's possible to combine them in an ideal way, so that for your solar technology, you have the best available forecast. It's also possible, of course, to combine it and provide the overall result to a user, so that this user doesn't have to care about all the details and the different technical aspects involved with each of the four forecast sources. Another approach to create longer forecasts is to use a big network of all sky imagers. An example is the I2Sky network in northern Germany. Here, the objection is to predict and analyze the solar irradiance and PV generation with a very high spatial and temporal resolution. The network is shown here. So we have more or less 100 times 110 kilometers that is covered with radiometers and cameras and ceilometers. So we have 22 stations where only a camera is used, 13 stations where, in addition to the camera, there's also a rotating shadow band irradiometer that measures global, direct, and diffuse irradiance. 2 of the stations have a camera and a reference MET station with a solar tracker with preliometer and chronometers. And then there are 2 ceilometers within the network that is operated by DLR, Institute of Networked Energy Systems. And there's also external ceilometers in the region that we can include. If you connect all these bits of information in a smart way, you can also improve the nowcast compared to a simple 2 all sky imager system. And here we see how one of those stations with a rotating shadow band irradiometer looks like. You see the all sky imager, then the rotating shadow band irradiometer. Here's a shadow band, here's the chronometers. And then we actually also have tilted irradiance sensors here installed. 2 examples that are taken in Oldenburg. Here we see an example forecast. So it's a forecast for the next 15 minutes that is created for the GHI. And we can see that depending on the cloud height, we can actually cover a quite wide range of the network with this forecast. You can also see that the forecast does not cover the whole region. So if the clouds, as in this case, are coming from the southeast, then 15 minutes ahead, we will maybe not have a forecast anymore for the city of Oldenburg, which is here where the most of the points are. But you will have a forecast even longer than 15 minutes in the future in the northwestern region. This is also shown here. Here we have a different example. Here the clouds are coming from the northwest, and we could create a forecast even 45 minutes in the future. In this case, we miss some parts of the area in the northwest, and we get the 45 minutes forecast horizon only in the southeastern part of the network, because the clouds that affect the southeastern part 45 minutes after the image acquisition, they were seen by these cameras in the northwest 45 minutes earlier. With that, I come to the summary of my presentations. So all sky images can deliver nowcasts of the irradiance at the camera side, maps of the irradiance for several square kilometers around the cameras. If you measure the cloud height also, you can derive even maps covering thousands of square kilometers if all sky imager networks are used. And which option is the most adequate for you depends on your application. It's also very important to combine the all sky imager forecast with other forecasting methods. And there are already many validations of the method in general around that show very promising results also for different applications. With that, I thank you for your attention. If you have any questions, please ask in the chat.
Thank you so much, Stefan, for the presentation. Yeah, we actually have some questions. So the first one is from Saad Ben Brahim. We are noticing recently an increasing use of probabilistic methods. Do you think these methods can give better results than existing methods? And can these methods be combined to ASI forecasts?
Certainly, the probabilistic methods are also of interest for all sky images. So we are actually working at the moment on this to provide a better forecast, including also probabilistic information. The uncertainty maps that I've shown before are like a first step towards this. However, of course, you will not only want one sigma information, but also further probability information. And I think in the future, we will see this a lot also for the all sky imager systems.
Yes. And the second one, it's from Rodrigo Amora Silva. Could you share your take on the sky camera image sensitivity to environmental factors like rain droplets and bird faces?
Yeah, it's definitely an issue to maintain these ground-based instruments well enough. Just as in the case of the radiometers, you have to clean them from time to time. The good thing is that you will also see some kind of effect of the soiling in the image. So the situation is at least a bit better compared to radiometer systems. But anyways, you still have to clean them. In the power plants, you have to clean also the radiometers, depending on the use standard, once per day or once per week. And so it should also be possible to maintain the cameras clean enough, but this has to be done. And so that's from the cleanliness side. The other effect is simply also the rain, as you mentioned. So here you will see the rain droplets also in the camera. So there's actually also codes around, papers around that measure the precipitation using these droplets. And if you have them on the camera, you, depending on how many there are, maybe you cannot provide the forecast for a certain number of minutes. But if you detect the raindrops on the lens, then you will also be able to cut away these droplets and use only the region of the photo where you can actually see the sky. So it doesn't mean that with just one small drop, you will directly lose the photo. You can actually then cut away this drop and use the rest of the remaining photo and still provide a forecast.
Okay, thank you. We have another one, but I will leave this to the discussion session because we are a bit over time. So thank you so much, Stefan, for the answers as well. So the next speaker, it's Mr. Andreas Kazantzidis from University of Patras, Greece, head of the Laboratory of Atmospheric Physics. So he will talk about the forecasting of solar irradiance and ramp events with all sky imagers. So stage is yours, Andreas.
Thank you so much. Thank you so much, Gordon. I would like to thank you also the organizers for inviting us in this workshop. So I suppose that now you see my presentation in full screen?
Yes.
Great. Thank you all for being here for this presentation. My name is Andreas Kasnantidis. I'm coming from the University of Patras, and as you see from the first slide, I'm the last author of many other colleagues that are working hard on this benchmarking exercise with all sky images and forecasting of global horizontal irradiance in the frame of task 16 in PVPS. So the group is big because we had the chance to have 5 different all sky image systems and with a lot of data, as well as the help from the German Aerospace Center and CMAT, because they provided their facilities at Plataforma Solar in Almeria as a test bed for all this benchmarking exercise. So if, just give me a second to go to the next slide. Yes, if I can have a minute to present the institute. University of Patras is located in south-west Greece. It's the 3rd largest university in the country, with a bucket of departments and a laboratory. And here at the physics department, it's our lab with a team of about 30 researchers. Our research activities are deviating from solar radiation resource and forecasting down to weather and atmospheric pollution forecasting to artificial intelligence, as well as specific topics as stable isotopes in rain and atmospheric water vapor, which are important for climate, ultraviolet radiation measurement and effects, and early warning system for epidemic spread like COVID or West Nile virus. In the frame of the PVPS task, there is a specific part of it that is devoted to forecast based on all sky images. The idea is to try to collect measurements and forecast data sets that could be used for future projects, validations, papers, etc., and to provide maybe for the first time an evaluation from a benchmarking exercise. There is an open call for all sky imager sky imaging systems coming from companies or prototypes from research groups, and we had the ability to host 5 of them. Us, as the University of Patras, we are working on all sky imagers, but we don't have our own hardware. So we decided it has been decided actually in the frame of the task to take over the validation of the analysis of the results. What is the target audience for this task is the forecast users, of course, and the forecast developers and providers. So Stefan present some slides which form a nice introduction for this talk too. Just to let you know that this is our location, as I said before, Plataforma Solar in Almeria, and in the right picture you can see the platform where all the sky imagers have been installed with the help of CMAT and DLR, as well as other instrumentation, either including radiation as well as metadata as atmospheric constituents, cloud height, cloud coverage, and IRSEC information as well. So we had a chance to validate the cameras and the algorithms for a period of 3 months. This period has been separated into in two sub-periods. One has been used for validation, and the other has been used for testing between the groups. We decided that the time horizon between the for that focus horizon will be almost 20 minutes, and we excluded cases where the solar zenithal was below 70 degrees because of the inherent ability of non-ability of camera to detect clouds when they are very close to the horizon, as well as because of the horizon itself at PSA. This days has been classified in some classes with more emphasis on scattered and broken cloudiness, as you can see here. So we had the cloud-free or the almost cloud-free days, but to keep it low, about 1/4 of the data that we validated corresponded to cloud-free days, because you have a site that is almost cloud-free and we just get half of the data, then you have the ability to the possibility to get a lot of cloud-free days, and so there will be a bias on the results. So you use days that they had scattered or broken clouds with low, middle, or high clouds, as well as multiple type of clouds, which is supposed to be the most difficult one. We selected days that they have a high or middle cloud during the half of the day, and the other half was cloud-free, which is also a case that the operators are facing sometimes. And of course, we have also selected days that they had overcast cloud condition during the half of the day, and then the weather becomes better and it turns to scatter or broken clouds. This is also the case, the vice versa case. So half of the day with scatter clouds and then turns to overcast, etc. So for hardware systems, 5 nowcasting methodologies in total, and these are compared with 2 persistent models. A typical persistent model, as you can see at the end of the slide, and a physical-based is more persistent models coming from NREL. The so-called PSPI there's a publication in the literature, I think it was 2 years ago, from NREL about these smart persistent methods. And this is the results in terms of 3 statistical metrics. Here you can see the mean bias error. In the middle, you have the mid absolute error, and in the lower panel, you have the root mean square error. And you have 5 columns for the 5 different ASA systems. As you can see here, each figure has 2 axes. One, it's the time interval, and the y-axis is the lead time. So if you take the first ASA system and you go in the rectangular, it's 5 to 5. This means that you are trying to find out what is the mean bias error for this system if you go 5 minutes after the time, the 0 time, and you try to find out what is the error in 5 minutes intervals. As you can see, the mean bias error in general is below 10 watts per square meter. The mean absolute error is certainly below 50 watts per square meter, and the RMSE ranges up to 85 watts per square meter. As expected, for most of the system, the error is increasing as you go to longer times, lead times. So this is the forecast for the next 20 minutes if you take into account the time interval every 1 minute. And of course, the opposite comes when you try to go to the first couple of minutes after the time that you can provide the forecast. There are some difference between the 5 old sky imagers. You see that some are in some the mean bias error is changing quite smoothly. In others, there are some differences in specific minutes. It seems that there are some spikes or something like this. There are positive or negative error, and you can see here an example. These hatched pixels indicate that negative mean bias values exist there. So what is important also to note is not to find out the overall value of these metrics, but try to find out what is their value for different cloud types. So this is the mean bias error for the 5 IC systems as well as the 2 persistent models, and you can see how they deviate from for the different cloud classes. So cloud cluster 1, it's the cloud-free class, and as expected, the mean bias error is the smallest in most cases. And if you go to, let's say, to this cloud cluster 2L, that means that you have all the day broken cloudiness with low clouds. You see how the different IC systems perform, and you can see here also the performance of persistent models. So you see that in all cases, in most of the cases, in the vast majority of cases, the error is below ±10 watts per square meter, which is considered as a typical error for also for measurements of global horizontal irradiance. But if you try to check the result a little bit further, you see that there are cases that the old sky images are trying to compete with persistent models. One very good example for RMSE is here. It's the same figure, but you see here it's the RMSE values. And if you compare these 5 ASI systems with persistent models, you see that ASIs are actually big persistent models in most of cloud classes. You can see what is happening in the first class, which is the cloud free, which is also important, as well as the cloud 2L, when you have a difficult situation with low clouds passing in front of the sun. You see that in this case, the persistent model is much higher than all 5 ASI systems. Similar results are presented for the mean absolute error and the forecast skill, which is also important. There are some negative values in case of cloud-free skies, and this is happening because if you have the persistent model is quite good in forecasting cloud-free skies, but if you try to see what is going on with in other classes, you see that even the forecast skill in all skies cameras is quite different than, let's say, another persistent model like the small persistent model presented by NREL. So, as Stefan saw before, we are progressing in terms of results from all sky imagers, and it was true that some years ago, all sky imagers algorithms they were under development, and they were not able to beat persistent. However, this is figures that shows that this is not the case anymore, at least for these 5 systems that we had the chance to validate, because here you can see the RMSE for these systems compared to persistence. So every dot line is the persistent forecast error, and every solid line is the one coming from the camera for the different cloud classes. You see here that in almost every case, the solid line is below the dotted one, and this means that ASICs are beating persistence. You also see cases that persistent, there is a difference in the results. Let's say if you check this all-sky image system, you see that in the first minute, the camera is providing a better forecast in terms of RMSE, and then it's quite similar or even or lower than persistent. But you see that in the first minute, this camera, let's say, it's not behaving in the same way like persistent. So persistent model could be, in this case, could be better for the first couple of minutes, but then the behavior changes and the camera could give us more robust results. Of course, in reality, as you go to specific cases, there are still differences, and this is a very difficult case to forecast. On 8th of October 2019, you can see here the global horizontal irradiance. You can see the variability, and you can also see that there are quite many cases that the measured irradiance is much higher than the one expected for clear sky conditions. So it's a really difficult day with a lot of scattering, and we provide here three windows, three time horizons here in this day. It's window A, B, and C, in order to zoom and see how the all-sky images are behaving. Let's say if you go to window A, you will see the real measurements, and you can see the forecast, the one by all-sky imagers. So they're trying hard to keep going well against measurements, but there are cases that almost all the all-sky images couldn't be able to detect this strong positive ramp event. Similar cases are provided around the noon time. As you can see, this is the variability of global horizontal irradiance, and this is the one that has been forecasted by the ASICs as well as the persistent models. And this is window C in the afternoon, when also we have strong fluctuations of global horizontal irradiance. So after that, we decided to check the ramp rates. So how able are the all-sky images to identify possible ramps in the next 20 minutes? I'm not able to provide a detailed information about the methodology that we use for the detection of the ramp rates, because it's not publicly available at this moment. However, I need to say a few words about it, because there are some highlights that also make us happy when you saw it. First of all, it's the verification of our methodology. You see here a typical day with global horizontal irradiance during almost all day from 8 to 16 time. So it's always between, for cases where the solar entanglement is below 70 degrees. And we use some kind of threshold to define the ramp rate, and this is the outcome. So again, you can see two windows, one in the morning, and every green point is considered as ramp by the algorithm. Every red point is considered as no ramp. So you see the performance of the ramp rate recognition, identification of in the algorithm. And in the afternoon here, you see a part of the day which is almost cloud-free. No ramps are expected, and this is the case also here when you see that green points are missing, so the algorithm seems to work quite well. In order to make a first validation of the IRSEC systems in their results that they provide us from their point of view of ramps, we made a confusion matrix of possible cases of forecasted ramp events. So in the next slide, you will see some percentage of true or false cases of ramps. So here you have the observed ramp events, and here you have the predicted ramp events from the IRSEC. So the good cases is that when the IRSEC predict a ramp event, and there is a ramp event from the observation, or when the all sky images predict no ramp event, and this is becoming true from observation as well. So this is the result. This is the confusion matrix for the 5 systems plus the smart persistent method. And what we could say from here is that we have 5 different cameras with different accuracies. However, there are some interesting things, like, let's say we take the first camera, we see that this camera is able to predict ramp events in the 54% of cases compared to the real observed event as coming from the measurements. And then in a raw ramp event, it's able to predict almost 95% of that. So this is a camera that works very well with no ramp events, and it provides an adequate forecast at more than half of the cases that you will have a ramp are detected by such a camera. You can see that there are different percentages of different cameras, and what is also interesting is the fact that there are cameras that are not so good in terms of the mean bias error, the RMSE, the mean absolute error that I showed you before. But if you come in this confusion matrix, are becoming better in detecting ramps. You see, let's say that in this camera, 93% of ramp can be detected. And also in this camera, almost all ramps, all of the observed ramp can be detected too. In contrast, as expected, these are results for the persistent model. Lower detection rates are expected when you have ramps. Large detection rates are expected with no ramp, because this is the physical meaning or a way that persistence works. So if I can summarize this validation up to now to some conclusions, it's good that all sky images nowadays outperform the persistent forecast. They have to beat the persistent models in order to provide them to present themselves as a robust system for the first and 30 minutes for some very short-term forecast. This is really important. And as you can see, depending on forecast horizon cloud cluster, they may provide better performance as the leading time of forecast increases. And also for forecast horizons higher than 5 minutes, they are able to outperform also persistent even for cloud-free skies. Moreover, we try to compare the new smart persistent algorithm with the conventional RAL. You see some slight improvement, which is also very important too. Moreover, the potential forecast of ramps is good to be investigated, and all the sky emerging systems seem to work adequately when they're asked to detect no ramps. However, there are significant differences on true ramp event predictions. So, what is coming as a highlight from this benchmarking work is that there are all-scale imaging systems that have better performance in statistical metrics. However, there are other systems that they perform better on ramps. So it's up to the user, it's up to the target group that I presented at the beginning of my talk, and for this activity of task 16, which camera fits best to their needs and activities. Thank you so much for your attention.
Thank you so much, Andreas, for the insightful presentation and all the research aspect of it. I think it's a valuable contribution from the academy to work with all the service provider and the other market players. So I think we have it. Maybe we can only take one question for now, then we can leave it for the later. What are the key parameters to anticipate the ramps?
The key parameters, excuse me, to?
Anticipate ramps.
To anticipate ramps.
So I'm not sure if it's a clear question. Or maybe I can ask the second one, maybe that we can reply in text. Is it better to forecast ramps using solar irradiance inputs or the historical data of the production?
I'm pretty sure that historical data will not be able to detect ramps in the next, let's say, 10 or 20 minutes. If you use the very the current measurements of irradiance, you will get actually the only forecast you can get is coming from persistence. So we presented the how robust can this be and what is the rate of success. This is where the answers are coming to give a better forecast, and this is the case, at least for the 5 systems that we presented today.
All right. So thank you so much again for the presentation and the answers. So now we have the last invited speaker, Mr. Nicolas Schmutz from Réunion, France, and he will talk about the sky cameras for intra-hour forecasting and few use cases. Stage is yours, Nicolas.
Thank you so much, Gorkem. Hello, everybody. So thank you for inviting me to present you our Sky Insight on Sky Camera and to present you industrial use case. Thank you also to all the presenters to introduce the subject, shall it be academic or with a global view. And now we will go to industrial use case. So first of all, here is the place I'm living in. So I'm based in La Réunion Island, which is between Mauritius and Madagascar in the Indian Ocean. Only 800,000 inhabitants, so quite small. So the electrical grid is really a microgrid. And it's really tough to balance the grid and to make sure that at each moment, the consumption equals the production. This is why insertion of photovoltaics, which can be called intermittent energy, was a real challenge, and this is also why I decided to create the company 12 years ago in order to transform this intermittent energy into guaranteed energy thanks to solar power forecasting. So the product that we have now is forecasting what will be injected in the next days, which is done by numerical weather prediction, and a product we call it Daycast. Then we forecast what will be injected in the next hours, and the best tool, the best techniques is satellite, and we call it Hourcast. And we also forecast what will be injected in the next minutes on the ramp events, thanks to our camera, patented camera, and we call this product Instacast. So we are doing forecasting, but for sure, as we are able to analyze satellite images, we can reconstruct what is the past irradiance, and we can do climatology and produce time series. So let's go for innovative camera. So far, all the presenters focused more on visible range camera, which is, well, camera that you may have in your cell phone or in a regular camera. We do use infrared camera. The idea went from the way we observe the clouds from satellite. We do observe the clouds from visible range wavelengths, but also from infrared wavelengths, for example, to get the cloud top height. So we decided to observe clouds from below using the same strategy and using infrared channels. So infrared detectors is here in the head of the equipment. We are looking downwards to this mirror down there so that we can have a global view of the sky, and also to answer a question before, if we have a bird soiling the mirror, the effect will be only 1 pixel, while if we looking up with the camera, for sure the impact of the soiling will be a major one. So by watching down to a mirror, we protect the equipment, and it is more robust against soiling. So our camera is also validated by many hybrid controllers for hybrid systems like DAVE, and we will go to DAVE use case, what we are doing with them in Amazonia. So that you have also a clear view of the benefits of infrared compared to visible range. So visible range is nice, and we can get nice algorithms to detect red and blue ratio to recover the clouds from the clear sky. But you can see here that we are definitely blurred by the sky and by the sun, sorry. And all the information which is really of interest for the next seconds or so next minutes is here in the sun area, the circumsolar, but we are definitely blurred. We have no idea if there is a cloud in front, hiding the sun or going away from the sun. Here is the same view with the infrared one. We pasted that on the same image. Here, this small black pinpoint is the sun. So it's very small and we have no effect on infrared. And we can clearly see that there is a cloud in front of it. And depending on the last images, we can know, for example, that the clouds are going this way and the sun path is going this way. So we can compute when the shadow will go away and when there will be a ramp up of solar energy. What is great also with infrared is that we can observe clouds night and days, 24 hours a day, which is of interest not for photovoltaics, but for other business where cloud impacts the business, like defense and space, for example. And as Stefan explained, we can get brilliance, brightness, and temperature from each pixel of infrared so that we can reconstruct the cloud base height and the cloud optical thickness, which is how deep will be the shadow on Earth. So we inverse the model to get the elevation of the clouds so that we know where the shadow will be exactly. So we will resolve one of the questions that we had before. And cloud optical thickness, which is what will be the impact of the cloud for photovoltaics, but also for other businesses. So now let's go for concrete use case, an industrial one, which is in Amazonia in Brazil, a small community in Oiapoque of 24,000 inhabitants, which recently had no electricity at all, but then there was a heavy fuel plant which was installed, supported by PV plants, so 4 megawatt peak plants of photovoltaics plus 12 megawatt of gensets. And what we did is we installed a camera to improve the efficiency of the carbon footprint, thanks to solar and forecasting, and also for sure reduce the cost of operation. So as we will see, we reduce the curtailment and we increase the penetration of PV in this plant. So here is what it looks like. So we have the PV fields feeding inverters, and then there are the PV controllers from our partners DAVE in this case, in a Voltalia solar plant. So DAVE controllers control how many gensets shall be turning on or turning off and will also control the power delivered by the gensets. Shall they turn idle just in case to take over, or shall they produce full speed, knowing that the best efficiency is when they are typically at 60% load? So we do send information about the ramp rates, which helps decide how many gensets shall be turned on or turned off. And there are many rules. For example, you don't turn on a genset for just 1 minute. When it is turned on, I guess it is typically you cannot turn it off before 1 hour, otherwise we will break it. But depending on which one was turned on first, we can decide when the first one can be turned off. So quite complex control law, but we simulated what happens in this case without forecasting or with forecasting. So in this one, we have the profile of production. Here in orange, you have the solar production, what can be produced out of the solar modules. And in the yellow, you have the solar energy, which is really injected. A part of it, as you can see, is curtailed. So without forecast, without SkyMeter, we must curtail, and we must also have a spinning reserve, which is a margin in case there is a rundown. The gensets must increase the power delivered to the grid, so they are not turning full speed, and maybe some are turning idle, so just burning fuel and producing carbon without energy to be injected in the grid. So we waste money and we waste carbon. Thanks to SkyMeter, we manage to be more accurate and to announce when there will be ramp rates. As you can see that in this, there is no curtailment any longer. So in the previous one, a lot of curtailment. In this one, no curtailment left, and less margin. It doesn't mean that we don't take a risk. We don't want to take any risk, nor Voltalia, nor Dave, nor anybody. We don't want to have any blackout. But we know when there will be a steady production, and we know when there will be risk, and we are able to trigger on or shut down gensets to be secure, but to save money and to save carbon. Yeah, so here you can see that when we announce a ramp down of photovoltaics, the genset can be pushed a little bit to deliver more energy. And so we optimize and we reduce the margin without inducing any risks. And some economical results is that without forecast, we managed to have a 13% penetration of PV in this small grid or mini grid. Thanks to forecast, we are able to have 20%. So we increase by 50% the penetration of PV on this grid, and we reduce by 10% the fuel consumption. But you can imagine that when you are in Amazonia, the price of fuel due to the transportation, which can take days, the risk associated, if you meet alligator or whatever risk you have during the delivery of your fuel, the fuel arrived on site is really, really expensive. So saving any barrel of fuel will have a huge economical impact. And here is also the view of the curtailment. Without forecasting, we are forced to curtail a lot. So as Jan explained, tomorrow when the price of photovoltaic modules will be nothing, we will be able to oversize and to curtail a lot, but yet so far the price of solar modules is not nothing. So we prefer to take benefit of any kilowatt hours produced, and we can see that we went from 41% of curtailment down to 5% of curtailment, which is a significant improvement. And in terms of costs, in this simulation, we managed to save based on low price, because 1 liter is 90 cents of euro, I guess that when you are in the middle of nowhere after 2 days of trucks to deliver the fuel, it is much more expensive. But with this assumption, we managed to save more than 300k euros of fuel on site. And if you want to go deeper in this topic, either you contact us, we're very pleased to discuss with you. But meanwhile, you can also see the winning award at IRSEC'21 presented by Louis-Étienne Boudreau about what we did. So here is the title of these great posters, and the images I chose were extracted from this presentation. So I wanted to do this first focus on this mini grid because it's not very, but it's more easy to understand in this mini grid that the impact of forecast is directly inducing the fuel consumption, and we can count how many barrels we did save, and we can put a price in front of that, which may not be easy when you are connected to the grid and to see what will be the impact, because there will be costs taken by the state, by the grid operator, by the IPP. So difficult to touch the cost, but in a microgrid, it's quite easy to touch the costs. There is another example of a project that we occupy, which is in California, north of Los Angeles, in the Mojave Desert, a 300 megawatt peak plant from 8-minute energy. And it helps size the battery and operate the battery to reduce both CAPEX by reducing the size of the battery, and also OPEX by reducing the aging of the battery. Once again, if you want to go deeper in this topic, because, well, I had only 15 to 20 minutes to present, we did a great webinar with 8-minute discussion, great discussion with them, which is still available on demand. So if you go to our website, you can just enjoy this on-demand webinar with 8 minutes explaining the pros and cons of solar forecasting and the benefits of SkyImager to improve the efficiency of the plant. This one, well, I guess, guys, that you know which plant it is. So thank you, Mason. We are very proud to be on board, and our camera are on board this Mason plant in order to forecast what will happen in the next minutes. So very happy to be there, and very happy to be on board this great project. Some other views to show you that there is a great value for SkyImager and that we are present everywhere in every continent. We have cameras in Australia. Here it is a bush project in the remote community. Once again, after 48 hours of truck with crocodile, killing spider, killing snakes, whatever you want, the price of a barrel of petrol is quite expensive. So every barrel of petrol saved has a huge impact. Here we have some projects in India, in USA, in France, and in Africa. To put it into a nutshell, in a first conclusion, for the day-ahead forecast is great for grid integration, for energy trading, while for the very short-term forecast, the benefits are more for microgrid, as I presented you for Oiapoque project in Amazonia, in Brazil, where we can trigger genset and help optimize the number of gensets and the fuel consumption, so optimizing both CAPEX investment and OPEX operation costs. So this is it for today, and I was very happy to present you our solution, and happy to answer all your questions with all the panelists. Thank you so much.
Thank you so much, Nicolas. I think it was good to have such like use cases in some like real pictures after all this like research like happen in the academia and like in the pieces. So I know that, I mean, like you are always in the field. So I think you also have some like challenges on the side with the real climate issues. So thanks again. So I think we have around 20 minutes, including the discussion. So maybe I can start a few questions to ask Nicolas. Then I will go back to previous questions also to run the discussion part. So the one question to you, Nicholas. Reunivat and DWD are working on an innovative project called ICAM Cloud Ops. Can you tell us a little about it?
Yeah, so we are doing a research project together with Deutsche Wehrdienst, and we are very happy and proud to be on board this project. It is for data assimilation. So there is a numerical models forecast where the clouds will be, and our cameras observe where the clouds are. So it helps us to have a rapid update of the model and to reinitialize the model to be more accurate. So it is a great 36 months project, and we are very happy to be on board this project. There was already a first webinar, and I'm quite sure that there will be a second webinar next year presenting the results. And as it is a research project, for sure, results will be published in conference. I guess it will be EGU. It will be presented in EGU this year.
All right. Thank you so much. And the second one was, can you give us an estimation of the market cap of the solar forecasting market? I'm not sure what it's meant by the market cap, but if you have some guess.
I don't know exactly what the question is about. I guess so far it is still quite a niche market for us, the solar forecasting, because it makes sense where solar really impacts the grid, which is the case in islands, which is a case in mine or remote communities, which is the case in Germany, but maybe not the case in continental France so far. So it's not valid everywhere. It's valid where you have a bright sunshine and where resiliency of electrical grid can be jeopardized by solar power. So in a desert area or in a big continents with low, with not that many industrial producer or consumers.
Yeah, thank you so much. So maybe also like one thing for your presentation relevance, how sky cameras installed in solar plant and randomly, if it's.
Andreas, you can
I suppose that it's about the benchmarking exercise, am I right? Or it's about your.
Yeah, maybe. I mean, you can both make the contribution.
Feel free, Andreas. Feel free, Andreas.
Yes.
Okay, for the benchmarking exercise, the cameras, yes, are just on the same side by side, and all the instrumentation was very close. The groups were available to put an additional camera if needed for the algorithm. In another place, there are more than 5 solar irradiance stations in that Plataforma Solar, fully equipped. So we had a lot of data and really trying to deal with all of them. I would like also to add that because I've seen also the other questions about the benchmarking, but the campaign was blind. The participants didn't know about the measurements. I mean, they didn't receive any irradiance measurements in order to try to compare themselves. We did that. They just provide the forecast, and also that every system has its own, let's say, algorithm, their own hardware. It's accompanied by, of course, some application in the literature, but also the campaign and the results are staying strictly blind to the user about which system belong to which institute, etc. So I don't know exact information about ASI 1, 2, or 3, how they work, and I'm not able to say which user has ASI 1, 2, 3, etc. Thank you.
Yes, thank you so much. So I think we have some also questions for your presentation, Andreas. Can you explain why the SAI-3 algorithm gives different accuracies in different measures in terms of RMEC, negative, mean absolute error, positive, and etc.?
The answer is no, because we don't know how the algorithms work back inside in the camera. We have the results, so and our task is to validate the result.
Yeah. Thank you so much. So I don't know if Stefan is here now. There's actually
Yes, sure.
question on, yeah, like how much does the image processing computing needs increase as the number of sky imagery increase? For example, going from 2 days to 3 days. So I think it's about yeah.
So the forecast horizon is always limited. So if you have many cameras, maybe you can go to 1 hour or 2 hours, but never to several days ahead. So that will not be possible with the all sky images, unless at least you put them on the whole globe with a distance of 5 kilometers or so between them. So the actual processing time per sky camera system is very short. So maybe if you have a 2-camera system, within 5 seconds or 10 seconds, you get already the forecast for the next 20 minutes. If you now, of course, use lots of cameras, then the computation time also goes up. You can do some parallel computing, and this helps. But at some point, then you need also a very fast computer, an HPC cluster or something like that. So this would not be possible then maybe on your laptop. What I said before, like these couple of seconds, this is possible with a simple computer if you use the right hardware, let's say. So you have to maybe include a GPU also if you want to have very fast calculations, and then it's no issue of computation time.
Yeah. Thank you so much. So we also have another question. I mean, one of you can answer it, I guess. So if we have a numerical meteorological data without cloud cover measurements, that can influence our PV power forecasting. I think it's yes, of course, but like maybe one of you can give more insights if you like. If there is no cloud coverage data, how much the influence will be on the PV power forecasting? So maybe I
for you.
I mean, maybe I can also like give my contribution here. I mean, obviously the cloud coverage forecasts, I mean, like from the numerical prediction models is like one of the key input to input in the algorithms of PV power forecasting. So if you are missing, you are most likely have some low accuracy in the like power forecasting, of course. But I mean, as we hear today, I mean, it is not all about the like MVP models. There are some contributions like this sky image or the like satellite images. So like there are additional tools if you have some missing data, but there are some solutions to reduce the gap, let's say. So we have two almost identical questions. The solar power forecasting services are mainly B2B services. Can we expect an increase of B2C services in the upcoming years? Does anyone would like to answer? Otherwise, I will also have some reply here.
Maybe for self-consumption, for sure. If somebody wants to take the most benefit in his own household of the solar plus battery, maybe he can or she can move the usage. You can use your laundry a bit later or earlier, depending on the energy which will be available. So it can make sense for self-consumption for sure.
Yeah, and also like I can tell you that I mean yes, it's more like on the B2C level, but I mean as Enercast, we also work with several energy management and smart energy companies who are actually focusing on this rooftop PV, which is more to I mean I would say it's B2C markets, but I mean as I know, like most of us, the main players in the market, we are not have some like unique services in the B2C. But I mean, what I can encourage like all the interested people that I mean, Enercast, we have a self-service portal. Actually, it's free for anyone. So like anyone can sign up and add their individual or like residential plant details and get the data. I mean, there is no like a business model around it, but I mean, our self-service portal actually allow both the utility scale or even the small scale like rooftop PV forecast. So I can encourage all the interested people to like work around. And I am sure maybe not directly from the main forecast providers like us, but there will be some companies who are using our data and make some like maybe second level product or services to the individuals. So this was also answered then. So there are some general questions. We have 10 minutes more. There's a one question to me. Enercast uses power forecasting to provide renewable energy portfolio decisions. Can you tell us the importance of solar power forecasting in this process? Yeah, the portfolio decisions, actually, we are holding a webinar tomorrow on this renewable portfolio decisions. So which is actually focused more on the historical forecast capabilities. So I will not give, of course, all the details, but feel free to join our webinar tomorrow. So such capabilities as presented today, I mean, they also can be like mimicked or regenerated in the historical time span. So I mean, as Enercast, we have the capability and the archive all of the last 10 years of historical forecast data. So actually, we can run any historical delivery time or the horizon in the last 10 years, basically. And such data can be used as an input for your decision-making process. When you are adding or buying a new asset to your portfolio, you can actually run an historical simulation or get some historical data set in order to see if this new asset will have a positive or negative balancing or any operational effect to your existing or your future portfolio. So I think all these like technologies like mentioned today, all of them can be used also for some historical simulations to get some input data for any making decisions. Maybe more general question, what other meteorological parameters that can help to better forecasting besides solar radiations? I think we have touched most of the information, but if anyone would like to highlight some of the parameters again, feel free to contribute.
Well, meteorological numerical weather prediction will help us, for example, for the clouds for the next days, also to improve the clear sky model, as Stefan explained. If you don't have a great clear sky model, it will be hard to be efficient in solar power production. And we need to get aerosols, and aerosols can be pushed in the clear sky model thanks to the numerical NWP. There is the ozone. There is a the turbidity trouble. So many parameters affecting the clear sky model are given by numerical weather prediction.
Okay, yeah. So actually, there's one good question actually. Is there a study for the best site to place the ASI, or it is usually placed near the PV grids? And maybe I can also like extend it a question with my personal like interest. I also would like to know, do you conduct, or maybe they are still in the early stage, but do you have some checkpoints if a candidate site it's really like scored to have need of like such sky view contributions? I'm not sure if there's any categorization or classification of the sites. I mean, maybe like some of them, I mean, maybe they are subject to a really like full sky over the years. So maybe such like ASI applications will not be so efficient. So do you have some like pre-analysis of the sites if such application will make an efficient results?
Maybe I can answer to that. So in the variability classes that I've shown before and the validation for these classes, we have touched this topic a bit. So if you have the irradiance data in 1 minute resolution already from a site of interest, then you can have a look at that and you can check if there is actually a lot of variability or not. And maybe in some extreme cases, you will see, okay, there's so little variability that also the benefit of the all sky images will be small. I think that will be only like extreme cases. So maybe in the Atacama Desert, you will not have enough clouds to really make a good business case for the all sky images, for example. But in most cases, I would expect that there's a quite significant variability. So in this, so it's not like a very detailed, specific and quantitative analysis that would allow you to say, yeah, so you will save this and this amount of euros, and so there is a business case with what we have at the moment. In the future, I think it would be very interesting also to couple these this kind of analysis more with the economical analysis of the benefit, and then maybe we can give better advice to possible users of all sky images to tell them if they should buy it or not.
And would historical meter or production data is also like relevant, right?
Yeah, I think that would also be very interesting.
Yeah. Okay.
If I may add something here concerning where to put the cameras or how many cameras are needed for a site. Actually, what you need to know is the movement of the shadows of the cloud to the ground. So maybe there are cases that you can move a camera quite far away, and so you can see a view of the area. I think this is the case of PSA as well, and you can check the shadows over your farm. Moreover, if you have more than one camera, you have better chances to calculate the velocity of the clouds, which is very important. And if you have more than 2 cameras, maybe you have more chances to have a stereoscopic view of the cloud, which is something which it becomes very interesting in terms of research, but also in terms of application. Because the clouds are not moving just horizontally; they have also the advection. So these are aspects for the operators to think about, but also for future research as well.
Exactly. So maybe the final one, we have 2 minutes left, but also like we had, I think, a good job to answer all the questions. What are your advices for Moroccan researchers in the field of solar resource and power forecasting? So maybe Andreas or like anyone, I think like there can be some like highlights on the regional specific studies, but what will be your advice to the Moroccan researchers?
Aerosols, maybe? What do you think, Andreas? What about aerosols? Because I guess that in Morocco, it may be more affected by the sand dust, and it has a huge impact on the solar production. So research on aerosols, maybe to even improve the clear sky model, or a specific clear sky model for Morocco would make sense. What do you think, Andreas?
I agree. In terms of the ancillary data that you need in the farm, as you said, we were discussing before. Apart from ozone or something like this, aerosols are the most important parameter after clouds. Also in terms of soiling, and maybe Stefan, you can say a few words about aerosol effect in soiling, etc.
Yeah, including also soiling forecasts for the plant prediction. It could be very interesting. That's a different topic, let's say, that we did not really cover today, but that is certainly of high interest also for Morocco. In general, I think, yeah, as an advice for the researchers, I think it's very important always to consider your specific experience already. So there's of course lots of different scientists in Morocco that bring along very different previous experience. So maybe for some, it's best to focus on adapting existing other forecasts to the regional properties of Morocco, to work on combination methods that work best for Morocco, to identify which data sets are best for Morocco. Other people would have maybe experience to improve a certain specific method more. And I think that's important to consider always, of course.
So I think we are just in time to conclude our keynote and the invited speakers part. So now we will move to this 5-minute presentation session. We have 4 different topics will be presented shortly in the next half an hour. Then we have another half an hour for a conclusion and the discussion part. So I'm not sure if the presenters are ready here, but let me just read the slides on my screen now. The first speaker is Sohala Shabon and Mohammed Maroufi. They will talk about the performance comparison of support vector regression, random forest, and multiple linear regression to forecast the power of photovoltaic panels. So,
hello everyone.
Hello.
I'm Sohaila, a PhD student at Mohammedia School of Engineers. Today I will present my research entitled Performance Comparison of Support Vector Regression, Random Forest, and Multiple Linear Regression to Forecast the Power of Photovoltaic Panels. The summary is presented as follows. First of all, we will introduce the subject, then present the different methods used, then we will present the results obtained and conclude the presentation with a brief discussion and conclusion. This subject integrates 3 main themes, namely renewable energies, artificial intelligence, and big data sets. In fact, due to the chaotic and random nature of renewable energies, forecasting their output power has become an imperative. In this context, artificial intelligence and big data appear as one of the means to fulfill this aim, especially with the advent of new algorithms, the growth of prediction capabilities, and machine learning and data lakes produced in real time by sensors and Internet of Things activators. Thus, the main goal of this study is to use machine learning approaches to forecast the hourly power of photovoltaic panels. The PV station we used is located in Rabat, Morocco, with a total capacity of 6 kilowatts. Moreover, inputs employed are related to meteorological and solar irradiation. We have the global or horizontal irradiation, ambient temperature, PV cell temperature, and panels efficiency. Machine learning approaches employed in this study are multiple linear regression, support vector regression, and random forest. The accuracy of the investigated methods is evaluated using the most common and widely used performance metrics: R-squared, root mean square error, and mean absolute error. The general structure of our regression methodology for PV power prediction is presented as follows. First, we start with collecting and pre-processing the raw data. Then we partition the data into training and testing tests. After that, we train the regression model for the training set and apply trained model on testing set. We compute the performance metrics. If R squared is highest and the RMSE and MAE are lowest, then we stop the process. If no, we retrain our regression model another time. The flowchart of our regression models is presented as follows. Performance metrics obtained for the training and testing phase are presented in the following tables. Owing to the finding, it can be seen that support vector regression and random forest obtained and achieved the best performance compared to multiple linear regression, with an R-square of 99% in the case of random forest in the training phase, and the R-square of 96% in the case of testing phase. This is mainly due to the fact that random forest and support vector regression are very efficient at lowering the variance of models, preventing overfitting, and increasing the accuracy of unstable models. Finally, from the residual analysis, it appears that random forest and support vector regression have the smallest residuals compared to multiple linear regression, and their residual density is centered around 0. Unlike multiple linear regression, REC curve is another tool for comparing residual analysis, and it can be seen that random forest and support vector regression have the best performance. In conclusion, random forest and support vector regression method demonstrated superior accuracy than multiple linear regression in forecasting the PV power. Another conclusion is that easy to implement algorithms such as random forest and support vector regression can be very effective in terms of PV power forecasting. The results obtained also ensure the ability of artificial intelligence and machine learning techniques to forecast the PV power. Machine learning algorithms will have a significant position in PV remote management, where this technology will be highly prevalent in several countries. Thank you.
Thank you so much. I think we have the second speaker, Abdelkader Elkouni. So he will talk about solar photovoltaic forecasting of power output using artificial neural network.
Hello, everyone. My name is Elkouni Abdelkader. I'm a researcher at Green Building Engineering and Energy Efficiency at the School of Architectural Planning and Design. And today we will present to you our project concerning PV power output forecasting using artificial neural network. So as we all know, when the PV modules are exposed to solar radiations, they provide us with the power. And this procedure of conversion is highly influenced by climatic conditions, as an increasement in the solar radiation will cause greater power, but is also associated with the overheating of the PV power of the PV modules. So this phenomena are always coupled together, the influence of solar radiation and the temperature, and they have never been studied together, but always separately. So our goal is to generate an artificial neural network capable of predicting the PV power plant output and including all these parameters implicitly, such as cable losses, conversion losses, and the PV power plant configuration. So in our case of study, we were working on a power plant that is located in El Qaria, which is in Morocco, characterized by high solar radiations. And here is some characteristic of the modules that we use in this power plant. This is the following configuration. For more further details about the power plant, please consult Fathi's Amin's work. Our case, we were working on one of the inverters right here with two strings of 8 PV panels. So we had 3,648 row of data set resuming 1 month of observations, and we used the PV power as long as we're working on a supervised machine learning. We use the PAC as an output to the model, which is the target, and the input were the solar radiations, the cell temperature, and the ambient temperature. Both all the parameters were having different ranges, so we needed to presage and normalization to make them in the same range. And also the output was transformed using a log transformation to reduce its variance and to make it in a small range. So this is the correlation of the independent variables. Each one has his own correlation with the output, and the following, the B figure, it shows the influence of normalization on the variables. As you can see, they are all ranging from 0 to 1. We used the RMSE as an indicator of the fitness on the model, and the data was split to 70% training, 15% validation, and 50% testing. So we are aiming for a small value of RMSE during the training and also the validation. Here's one of the experiments that we have done with a single layer to determine the optimal number of neurons. And for 2 hidden layers, we had to compute the RMSE values and evaluate it for different combinations. And after doing mini tests, we have found that the optimal configuration, it is the following, with 9 neurons in the first layer and 12 neurons in the second layer. So in the first stages of the training of the model, we tried to predict 12 hours of production. So we trained the model with the following data set. It wasn't the full data set. It was only 70%. And the RMSE was ranging from 270 to 700. And the correlation between the predicted and the output value wasn't like a good correlation. It was spread, but even though the model was capable of predicting the evolution of the power, as we can see here, it is a zoom of this section. Sometimes it overestimates and sometimes is underestimating. So the problem is loading the machine learning model with too much data was causing it to get confused because of the energy management of the inverter. So we decided only to train it with 1 day and predict the other day. So in this case, we compared between 2 days, the 25th of May and the 18th of June. As you can see, the profile of temperature of both modules and the ambient temperature was completely different, and also the solar radiations. And yet, our model was capable of predicting the output of another day that wasn't introduced even in the training on validation or test. So the model was capable of giving good predictions, and here is the correlation between the predicted value and the real value, as it seems that in both validation and training, they have good correlation. And finally, we can say that our model gives low error, good correction, good correlation, and good prediction. Here is some references that we use in this work, and thank you.
Thank you so much for an interesting research area. I think we will.
Excuse me, before switching to discussion, we have a presentation of Miss Flora Charbonnier. I will share it from my computer.
All right. I think you need to share the sounds with the Zoom function, not from here. When you are first sharing the Zoom, you should select the sounds.
Yes.
Hello, my name is Flora Charbonnier, and today I will present some of the work we've conducted in the Energy and Power Group at the University of Oxford on the assessment of risks associated with renewable energy in Morocco to avoid a resource curse. This work was conducted as a team presented on this slide and was commissioned by the Climate Compatible Growth Programme to support preparations for the UN Climate Change Summit, the COP26, which was held in Glasgow in November. The aim was to bridge the gap between in-depth academic research and the practical needs of policymakers. So let us start by defining what we are talking about. A resource curse is the paradoxical situation where a country that has abundant resources experiences slower growth than neighboring countries that are poor in resources, with negative social and economic impacts. Historically, that has been prompted by non-renewable subsoil resources, such as oil and minerals, famously with a Dutch disease of high appreciation of currency associated with the Dutch gas boom in the 1960s, as well as, for example, in Angola and Venezuela. Now, of course, renewable energy is a fantastic opportunity that could avoid some of the risks associated with oil, such as resource depletion. It brings environmental benefits, and it is more distributed and accessible in nature than oil. But there still are similarities between renewable energy and subsoil resources as complex energy commodities. So we are wondering whether the same resource curse symptoms could occur if there are no adequate policies to mitigate risks. So we take the case study of Morocco, a signatory to the 2015 Paris Agreement, of course, with high solar and wind potentials and crucially existing interconnections throughout North Africa and Europe. So it is a key candidate to meet the low carbon energy needs, not only for itself, but also for other countries. So we seek to provide a realistic appreciation of risks of renewable energy development in Morocco through the resource curse lens. We started by identifying 14 risks in the literature that were deemed potentially relevant to the case of renewable energy in Morocco, and we then conducted surveys as well as in-depth interviews with renewable energy practitioners in Morocco. Through the evaluation of likelihood and impact presented here, we identified 3 top risks that I will now present. Firstly, in terms of economic dependence, most Moroccan renewable energy projects are co-funded by both the government and international organizations or banks. Now, as renewable energy is likely to be a large source of income and a big job creator, Morocco relies on these investments. But there is stiff competition with many countries and projects by funding, so that can lead to a heightened power imbalance between investors and countries like Morocco, creating the risk of being subject to influence. However, some interviewees did highlight that renewable energy also can create opportunities in this space. So one interviewee highlighted that it can actually reduce economic dependence by cutting energy imports, and another even so external funding as a matter of fairness, as large-scale projects will largely benefit high-income countries that are historical emitters of greenhouse gas. In terms of technology, Morocco has significant capacity for renewable energy research and developments, but less capacity for technology manufacturing. So this has led to some dependence on external companies for the production of some renewable energy parts and components. This issue also relates to the symptom of expatriate job domination. So some informants saw expatriates as an opportunity to transfer skills locally, but others deemed that there's often not sufficient capacity transfer from external companies to locals. In terms of flora and fauna, the deserts often used for wind and solar developments are commonly seen as unproductive land, ideal for renewable energy, but they are a part of the natural world and home to nomadic pastoralist cultures which could be threatened by development. Moreover, some informants mentioned increased hostility from local populations towards large-scale projects, which limits land availability and may lead to increased environmental pressures, particularly if the economic development opportunities for local populations are not sufficient. Secondly, scarce water resources can be contaminated or depleted through renewable energy infrastructure, which requires cooling or washing. Though there can be win-win situations if renewable energy development ensures water supply to local populations, for example, through desalination. So environmental impact assessments are usually required for Moroccan renewable energy projects. However, these are mandated through the investors, so the Centres Régionaux d'Investissement or the international financial institutions. So private projects without external investments may not be forced to undertake these assessments. What's more, multiple informants express frustration over a general lack of centralized follow-up on these assessments at the government level. So we recommend 3 key policy aims to mitigate those risks. Firstly, to minimize the influence of any one foreign entity in Morocco with regards to funding. Secondly, to keep developing innovation capabilities with regards to manufacturing and test bedding capabilities in partnership with companies, universities, and institutions. Thirdly, MASAN has been a very effective body, and there are strong environmental policies from Law 1095 to the National Water Plan, but renewable energy could increase by orders of magnitudes in the coming years, which will lead to increased pressures to exploit the environment and to increased incentives to overlook current protections. So policies should particularly focus on enforcement. Thank you very much. If you have any questions, here's how to find us. You can find a policy briefing, which is out, and we'll be sharing an extended academic publication through our channels. Thank you.
So I think we have the next speaker, Khadija Dimitri, on the topic of PV power prediction based on artificial.
Sorry, Görkem.
Yeah. Yes, Ismail.
Just one thing. I would like to present Miss Flora Charbonnier.
Okay. Okay.
Maybe
Perfect.
she could say one word or two about the study that she has done and conducted
Right,
about
sure.
Morocco in the conjecture of the economic situation in Morocco, and also the increase in development of large-scale solar plants. So, Miss Flora Charbonnier, the floor is yours.
Yes, hello. Sorry, I think that was just my presentation that played just now. Is there a specific question you'd like me to answer?
You can present yourself and also the importance of the study that you have conducted.
Okay, brilliant. Yeah. So yeah, so my name is Flora Charbonnier. I'm a PhD student in the Energy and Power Group at the University of Oxford. And yeah, as just presented, we have conducted this research in the run-up to the COP in Glasgow earlier this month to try and bridge the gap between the academic research that's been conducted and the needs of policymakers. So we interviewed quite a few experts in renewable energy in Morocco, and that's helped us identify the risks that could turn the big opportunity that is renewable energy into potentially a resource curse if they're not managed properly. So we hope that that'll be interesting to the policymakers and practitioners in Morocco to conduct those risk assessments and make sure we get the best from renewable energy in terms of climate, social, and economic opportunities.
Thank you, Ms. Flora.
You're welcome.
Mr. Görkem, you can follow on.
All right, then. So I think we have 2 short presentation left. So the next one is Khadija Dimitri on the PV power prediction based on artificial neural network optimized by genetic algorithm.
Hello everyone, my name is Khadija Dimitri, PhD student from Qat'iyat University. And today, I'm very happy to present my work entitled PV power production based on artificial neural network optimized by genetic algorithm. We will start this presentation with introduction, then problematic, then PV power production results, and finally conclusion. Nowadays, PV technology has a range of applications. However, several problems have to be resolved in order to integrate in an optimal way this technology into power grids on a large scale. One of these difficulties is prediction. Currently, the PV power output over the next hours or days. It is in this context that our research study takes place, the prediction of the PV power with the artificial neural network optimized using genetic algorithm. As you know, PV power measurements in a specific period and a specific location are very important for designing and supervising PV systems. However, in most cases, these measures are absent. The main goal of this study is to give for PV system engineers an efficient model based on artificial neural network and meteorological data to predict the output power of PV systems. Now we move to PV power production results. The first step in the study is modeling PV system, which is able to calculate PV power based on meteorological data. In this case, we are using the irradiance and temperature values of Agadir city, where 70% of database is used to train the model's parameters and 30% is used for validation. We are using two artificial intelligence methods. The first one is the artificial neural network, which is used for predicting the PV power. And in this case, we are using two inputs, which are air temperature and solar irradiance, and it is trained using LM optimizer. The second one is genetic algorithm, which is used to optimize the artificial neural network's architecture. In order to evaluate the performance and the accuracy of the developed model, two performance factors are used, which are the mean square error MSE and the correlation error. They are defined by the following formulas. Now we move to the results and discussion. This figure presents the results obtained from testing the artificial neural network for 180 hours, 4 hours of a week. The graph shows clearly the similarity between real and predicted PV power values during the testing process. This figure shows the structure diagram, which demonstrates the high relationship between predicted and real PV power. The obtained value of correlation coefficient is 99.972%, and the mean square error is 2.3091%. So from the obtained results, the developed model is able to accurately perform the prediction of PV power. Consequently, this model is adequate and robust to predict efficiently the prediction of PV systems using meteorological data, especially air temperature and solar radiation. Hence, it is reliable to be adopted by electrical engineers to design or supervise the PV systems in case of missing values measurements. That's all, and thank you so much for your attention.
We thank you for the contribution. I think we have also one missing presentation, but I am not sure if it will happen.
No, the first presentation was cancelled by the author.
All right.
Okay.
I think she or he just writes, so okay, but if you say it will not be presented, like this author write a text in the chat, that
she asked us to remove the presentation because they are
okay. All right then. Okay. Yes.
For this reason, because we do the live broadcasting of the conference in YouTube, and she refused to put her photo in YouTube. For this reason, we remove the presentation.
Okay, no problem, no problem. All right then. So I think we are well covered with this 5 minutes presentation. So which will lead us the like last session of the discussion. So if anyone, I think I will go through the last question, and I'm not sure if this last presenter are able to give some answer on that. So the organizing team, like what will be the final session methods? Should we allow them to also answer some questions?
Yes, authors are allowed, presenters are allowed
Okay, all right.
to answer questions.
Okay then, all right.
You can
Yes.
Panelists can ask questions.
Okay, yes.
Also,
So, yeah.
Questions from Q&A.
Okay, yeah. So then I think like there is one question. I think it was already like mentioned in the presentation, but there's one question of influence of genetic algorithm on the yield of PV system. So can you answer to this question?
Paper
Khadija?
ID? Concerned paper ID.
I think the ID it's 78. So I think the Khadija presentation, it was on the genetic algorithm. So there's a question of influence of genetic algorithm on the yield of PV systems.
Khadija Misri, you can activate your mic. Khadija Misri, please activate your mic.
Yeah, maybe we can like move on the other questions. So there are several, actually the presenter said the microphone is not working. So yeah, maybe please answer the question in the Q&A box, then it will be answered. So there's a question of how do the machine learning and other heuristic statistical models compare with bottom-up PV models that use temperature and irradiance data? Are they more accurate or require lower computational power? Maybe this question can be answered by Abdelkader or any presenter that you like. I mean, the question is more about, I mean, if you use the temperature and irradiance data, is it more accurate or require lower computational power?
Mr. Abdelkader Kisani, you can activate your mic. Abdelkader Kisani, ID 62. Is there, but the mic is
yes,
muted.
Yes, I also see that. There's also one question to genetic algorithm, but I think also Khadija is not able to. But I mean, Khadija, please answer the question in the Q&A session. Then it will be answered. Thank you so much. And there was a question also like in the keynote speaker session, the influence of artificial intelligence on the performance of PV system, wind turbines, and the efficiency of renewable energies. I don't know if any of the presenter can contribute, but I mean, what I can answer here is that, I mean, hello, yeah. Please go on.
Can I answer the question that was asked about the temperature and mainly the solar modules are really sensitive to these parameters. That's why we choose them, because of the sensitivity and the influence on the power that is provided by the modules, and that's why a certain parameters is chosen.
All right. I hope the answer was sufficient for the questionnaire. So yeah, it was. I was also like mentioning about the artificial intelligence effect on the like performance in the. I mean, I think like today workshop it's like more or less focus on the like power forecasting like segment on the like renewables, and of course the artificial intelligence play a key role to gather all this data, and it was mentioned in the last presentation, I mean the big data challenges. So it is not easy to get all this like physical model or the like technical background there, but then the artificial intelligence can actually give some contribution to all the solutions available and makes them be more efficient on the specific purpose and the use cases. But any speaker would like to contribute?
Yeah, for sure. For example, when we go from irradiance forecast to power forecast, it's not only deterministic, because there is always a way of heating or maybe a shadow which is not taken into account properly by a model. So artificial intelligence is really important to go from irradiance to power, and this is the most efficient way. So we need to have historical data. So we need to wait for a couple of weeks to get enough data to do that, but it really makes a difference. We also have artificial intelligence, for example, when we use satellite to do to forecast what will happen in the next hours, where the clouds will be located. We have some machine learning algorithms to forecast also so where there is the most chance to get the clouds. So yeah, artificial intelligence and within artificial intelligence, deep learning makes a big difference.
Yeah. So maybe there's also a question on the ASI methods. So maybe Nicholas, can you also contribute on that? What is the advantages of ASI methods over historical data and time series for forecasting? I think it was already mentioned, but maybe shortly.
Yeah, in my use case, when we have to reduce the spinning reserve to make sure that we don't get any blackout, but we don't have a genset running for idle just for nothing, we can just adapt. And the impact in the next minutes of a ramp down will be this exact cloud which can be seen now. And this one cannot be forecasted by climatology. It is just seen by the imager, as it would be seen by the operator on site. And this one is hard to be modeled. Just deterministic vision is the best way. So for the next seconds or the next minutes, ASI makes a difference.
Thank you so much, Nicholas, for the contribution. I go through all the Q&A session, and all the rest is actually answered by Khadija. It was about the paper presented. So I don't know now, like for the last like few minutes, I will allow all the speakers, if you have some last highlights for the presentation, then I think we will close the session soon.
Also attendees can raise their hand to allow them to talk.
Yeah, please.
Yes, if a party attendee want to give question directly or have an explanation,
sure,
you can raise your hand to allow you to talk.
Okay, I think we don't have a question from the participants, but maybe I mean, it will be good if all the organizing team, it's also like turn on the videos, and maybe, I mean, if you have some last conclusion words, I think it will be good, and it will allow us to thank all the organizer and the team, like specifically the like all this like Morocco agency contributions. So please, if you have some like closing words, you are free to do so. Otherwise, I will close the session afterwards.
Well, it was great to have this remote webinar discussion. I would even prefer to have a live discussion. So hopefully the sanitary crisis will be much better next year, and we'll have the great opportunity to meet and to celebrate together the great development of photovoltaics and the great success of Morocco in this field.
Thank you, Nicola.
Yes, likewise. I mean, I again would like to point out the Ismail Belhai and Abdullahi Dija to gather all of us. Like it was a long-term like work behind it. So I acknowledge and like thanks for all the effort behind it. So I hope all this discussion will lead some good like business cases and the collaborations with the Moroccan institutes and the energy players with all the global market players in the future.
Thank you, Görkem.
Thank you very much, Mr. Gorkim Telener. Thank you very much for all keynote speakers, Professor Andreas Kazantzidis, Mr. John Raymond, Mr. Nicholas Schmutz, and Dr. Stefan Wilbert. Thanks also for organizers, Mr. Ismail Belhash from Mazen, Mr. Ali Jdiya from Mazen, and all team of organizing committee of IRSEC. Thank you very much, and I think the floor is yours to conclude.
Yes. Thanks a lot again. I think I never attended such high attendee numbers in a Zoom session. It's more than 300 people. So I really I am happy to see such interest on this conference, and I think it shows the success of the like organizing and the selected topics. And again, thank you so much for all the speakers, organizing team, and all the audience. I wish you a nice day, and I think we keep in touch in the Renewable Energy Business Network. Have a nice day. Bye-bye.
Bye-bye.
Bye.
Now break, waiting for the next session. Good morning. Dr. Samarana Kazim.
Hello.
Hello.
Hello, good afternoon.
Nice to see you.
Yes, can you hear me?
Yes.
Okay.
Okay. The floor is yours to start the session.
Yes. Let me see if Nico is here.
Yeah, I'm here.
Hello. Hello,
Hello.
Professor Minkuran, you're here? Okay.
Yeah,
Great.
I'm here.
Everything's fine with you?
Yes, thank you. How about you?
Okay. Yeah, I'm fine, thank you. So should I start or should I wait for 5 minutes? Yusuf?
You can start. You can start. You can present the professor, and we start. Can present Professor Wong.
Yeah, but
give him a brief biography.
Yeah. But the voice is echoing. It's why it's coming 2 times. I think you have to close the Yusuf. You have to close.
Okay. Now it's okay.
Yeah, but I think maybe it's need we have to wait around 5 minutes because we start at around 12:14, right?
Could you please mute your voice, Yusuf, because I think there is some echoing coming.
Yes. Wait for about 5 minutes. Okay. The sound problem is solved now. No.
I think so. Now I think it's fine. Okay. Good morning, good afternoon, good evening to all the participants in different time zone. My name is Imran Kazim. Hello. Yes, I think it's fine now.
Yes.
Yeah. So I will start, I think, at 12:30 or 12:35. So 5 minutes is enough for introduction.
Good morning, Yusuf.
Good morning.
Something is wrong actually with the voice.
With my voice?
Yusuf,
Yeah.
why the voice is coming 2 times? Could you please check it?
It's from your sound, Samrana. It's echo.
My voice is echo, but not coming 2 times.
No, it's okay.
Yeah, it's better. Better. So we have all the speakers here. Yeah.
I'm here.
Hi, good to see you. Hello, Minghui.
Hello.
Hello. And we have, Professor, first speaker is Professor Minghui Wing. And thank you. So, you both know each other. This is Samrana. Okay. Good.
Maybe.
Thank you.
Maybe.
No, it's fine. We are fine. The second wave is coming, but we are fine. Spain is doing well.
Professor Wong, you can activate your camera.
Sorry again.
Could you activate your camera?
Yeah.
Camera. Sorry, my camera is. I mean, it's not good enough to see me.
Okay.
Yeah, like this way.
Good.
Oh, good. It's good. It's
okay.
Good.
Thank you.
Perfect.
Because the network is not good enough to support the data transfer, so usually I shut it off.
Don't worry.
No, it's fine, I think.
Please test
Yeah,
the share of your screen. Professor Wong, you can test sharing your screen.
Now?
And yeah, please share your screen. Yes. Share screen. Yeah, it's coming. It's coming. Yeah, fantastic. Yeah, very good. Now please go to the full mode. Full mode, please.
Okay, and let me stop the video, and I can do.
Okay. Yeah.
So
very good.
Okay, thank you.
So we still have 10 minutes because your talk will start at 12:40. Someone at 10 minutes more.
Yeah.
Five minutes. So 5 minutes.
We have 5 minutes made. We can wait for 5 minutes more.
Yeah.
The talk is 12:40, so you can start at 37 or 38. 38. 12:38. Yeah, 38 or something. So more people can join. Yeah. But this I told 10 minutes before, 5 minutes before this I told.
Excuse me? You talk to me?
Hello? Hello? Yes, I think I should start now.
Yes.
Yeah. Hello, good morning, good afternoon, good evening to all the participants in different time zone. My name is Simrana Kazim, and today I'll be going to chair the session 3, which is also the final session of emerging semiconductor photovoltaic application workshop 2. So in this session, we will have three invited talks, followed by the 5 minutes presentation. So the first talk will be delivered by the Professor Ming-Kui Wang. And Professor Ming-Kui Wang is a leading scientist in the field of solar cells. And recently, he was ranked in our published top 100 Chinese energy scientists of decade by Thomson Reuters. So Professor Ming-Kui Wang is an electrochemist who works in the range of energy and environmental problems. And he received his PhD degree in 2005 from Chinese Academy of Science. And later he joined the Professor Ulrich Stimming as an Alexander von Humboldt Fellow. Sorry. Later, he joined Professor Ulrich Stimming group as an Alexander von Humboldt Fellow at the Technical University of Munich. After that, he joined Professor Michael Group at the EPFL as a postdoctoral fellow. In 2010, he became a full professor at the Wuhan National Laboratory in China. And he was also working as a visiting professor in Professor Yang Group at the UCLA, USA. His research interests focus on nanostructure solar cell and the application of electrochemistry to the fundamental phenomena in photonics. He has more than 18,000 citations with the H-index of 66. And he became also the member of several editorial advisory board of such as Scientific Reports, and also he was associate editor of IRSEC' Advances. So with that, I would like to request Professor Wang to take the floor, and we are looking forward to listen his talk. So please, Professor Wang, floor is yours.
Okay, thank you very much for the very kind introduction. Okay, can you hear me now?
Yes.
It's okay. Yeah,
we
okay.
can hear you. Yes, everything's fine.
Yeah, okay. Ladies and gentlemen, my name is Ming-Kui Wang from Wuhan National Laboratory for Optoelectronics at the Huazhong University of Science and Technology. Before starting this presentation, I would like to thank the organizing community, particularly Professor Hammond for his kind invitation. The topic I would like to discuss with you is about the lead-less perovskite solar cell, mainly focus on why we select this type of solar cell and what we have found on it. This presentation is mainly divided into 3 sections. First of all, I would like to give a brief introduction. As you know, that the main to highlight perovskite, especially those containing lead, has been regarded as promising materials in the photovoltaic applications due to their excellent optoelectronic properties, whereby the certified power conversion efficiency of the perovskite solar cells has rapidly increased from 3.8 to over 25% in the past decade. We point out during the journey of the efficiency development, it is significantly to understand the function of different layers in the perovskite solar cells. However, although there's a broad development of the perspective of for the perovskite solar cell, the lead toxicity and the instability resulting from the use of the organic and inorganic hybrid halide lead perovskite, such as the methyl aluminate iodine, that limits their applications. We knew that the human body does not need the element of lead. This would not concerned by some other solar cell. But in the perovskite, the lead is in the form of ionized state, which is significantly soluble in water. As a matter of fact, we can see this value of solubility of lead iodine into water being 620 milligrams per liter, which is a big deal from a toxicity point of view. Therefore, replacing the lead with eco-friendly metals without lowering the device efficiency and the long-term stability is that of utmost importance. Consequently, effective strategy must be taken to avoid the toxicity of the lead and environmental hazards of lead containing products. During the past 5 years, we have been seeking for a suitable method to reduce the toxicity of lead by removing the lead in the compound, but at the same time to keep the good property of the halide perovskite as photovoltaic materials. In this way, we have made some progress in lead-less perovskite solar cells, which present a power conversion efficiency in the range from 60% to around 21% by using the strand titanium, zinc, and nickel as replacement. Recently, the team highlight perovskite has won out among all the potential candidates, as it has a similar crystal and electronic structure to the lead counterparts, such as the higher symmetry and the higher carry mobility. We do have evidence rapidly increasement in the power conversion efficiency for the team-based perovskite solar cell from about 3% at the year of 2015 to about 13 this year. So we also note you that most of the team perovskite material reported for the solar cell applications has a similar crystal structure. However, the tin 2 plus actually is quite easily to oxidize to the tin 4 plus, which when the material is exposed to the any oxidation environmental, leading to a tin vacancy and high p-type conductivity. Also, the lower solubility and the greater Lewis acid of the tin iodine than the lead iodine generally leads to a faster crystallization rate of tin halide perovskite during the solution process and consequently higher defect density in the tin halide perovskite film than that in the lead counterparts. Therefore, there are many efforts have been made to reduce tin oxidation, such as using the tin source to compensate the oxidation, or using the antioxidants, or either use dimensional engineering, which we show here. One is based on the oxidation and the reduction reactions. Another one is based on the physical isolation. The following strategy discussed in this presentation will be based on the same principle as presented here. Here I show you some examples on during the study of the effect of the additives on the team-based perovskite in my group. For the first case, we introduced the team polyethylene to as an antioxidant agent into the inorganic perovskite precursor solution, aim to obtain a high content in film and stable or inorganic perovskite that is a lead team mixture mental cancer halide perovskite. The team portfolio actually is known as an excellent antioxidant in the biological, medicine, and so on to inhibit the oxidation of the oxidizable substance we suggest here, what is more interesting for us is that the functional group, the East group, actually can coordinate with the team Delt to modulate the crystallization process as well. As mentioned before, from the literature review, it is known that the a lower solubility and a great Lewis acid of the tin iodine than that lead iodine generally result a faster crystallization the rate for the tin halide perovskite during the solution process, and consequently, there's higher defect density in the tin halide perovskite film than that in the late counterpart. Therefore, a fast nucleation and a slow growth of the tin-based perovskite crystal has been proved as an effective way to obtain high quantity thin films. As you hear, we suggest that the East group of the tin portfolio coordinates with the tin 2+ and the late 2+ by sharing the learning electron pair, which can boost that the nucleation process during the film formation. Therefore, adding the team portfolio can dramatically improve the morphology of the perovskite film, as shown in the SEM images here, and result in the appearance of the compact large grains with pinholes. This is good for the device fabrication. The antioxidant activity of the tin portfolio can be onto the tin-late mixture in organic perovskite was demonstrated by observing the color change in the precursor solutions with and without the additive. The control sample showing here a distinguished color changing from the yellow to the orange red after 12 hours, and then turn into the dark red with a prolonged exposure time. Impressively, the precursor solution with tin portfolio kept its initial color for 72 hours. This comparison just reveals that the tin portfolio has the ability of retarding the tin oxidation in the precursor solution. Also, we used the XPS characterization to further verify it with a reduced tin 4+ proportion in the perovskite film from about 68% down to the 6%. This is very good for non-stability for the tin based perovskite film. We fabricated the solar cell device by using a printable metal oxide framework of titanium dioxide with aluminum oxide and nickel oxide, in addition to a layer of carbon contact electrode. And using the scissor lead tin mixture perovskite as the light absorber layer. As you can see here, the perovskite solar cell using 0.5% TP additives shows less hysteresis and higher output voltage compared to that the device without the TP. So the device also efficiency can be increased to 80% when the T portfolio is added, mainly due to the increment into the output voltage and also the current. Both of them are related to the perovskite film quantity, which can be reflected by the an increment for the EQE numbers at the longer wavelength range. The second sample I want to discuss with you is about the doping. Interestingly, actually the tin inorganic perovskite are p-type dopant. In this study, we introduced you the to turn that the property of the tin perovskite with incorporating a donor element for doping. Actually, it's not a new concept. Actually, it's old concept for the semiconductor. It's new for the perovskite. Actually, for the perovskite, there are 3 different electric doping methods, including the intrinsic and extrinsic and also charge transfer doping method. For the intrinsic and extrinsic doping relates to the formation of a charge defect in the lattice of a perovskite, which makes them highly uncontrollable. Under control, the charge transfer doping can take place through any exchange of carriers between the perovskite and the external donor. So we first carried out a calculation according to the Crouch wing rotation. The result showing that the electricity property of the sensor tin iodine perovskite can be rearranged by charge injection, such as chemical treatment or like electrochemical charge injection. Therefore, the electric property of the sensor tin iodine can be rearranged into N-type doping by charge injection. So in order to realize such kind of charge transfer, we selected the corporate season as the donor molecular, since the hormone level of the corporate sensor lies close to the conduction band of the sensor tin iodine, this perovskite material. So this satisfies the requirement for the electric transfer from the corporate complex to the perovskite material. Actually, for the corporate sensor is Cormer used 1 electron reducing agent for the electrochemical study. This material can easily give up any extra electrons from the mantle core to form any 8 electron organized species with high stability. We named this process as a remote reduction. After introducing the corporate sensor, a fast thermal electron injection from the corporate complex species into the perovskite can maintain a reduced environment and thereby to effectively suppresses the tin oxidation. Meanwhile, this process can turn the electronic property of the tin based perovskite, which can be confirmed by any emerging oxidation species of the corporate sensor. The electronic film level of the perovskite increase as the content of the corporate species. Also, they calculated the electron carrier density increase as well, indicated that the turning property of the tin-based perovskite from the p-type into the n-type. So the influence of the charge transfer from the competency to the tin-based perovskite also bring up any reduction environment for the tin species and reduce the proportion of this tin 4+. That's actually quite clear. So we suggest that the underlying reason, the reason for the reduction of the harmful effect of the tin 2+ oxidation to the remote reduction process, which can be correlated with the diluting the electrons by the corporatonency, offering any reduction environment in terms of redox chemistry, as shown in this equation. When fabricated a sensor tin iodine-based devices using the mesoporous TL2 aluminum oxide and nickel oxide carbon framework, and no performance actually it's almost lasting 0.7% efficiency was observed without any treatment. But it's quite interesting when we employed 1% of the corporate complex into the inorganic scissor tin iodine film, we see that the efficiency has been reached a maximum of 3% efficiency. Even though this efficiency actually is quite small, but we believe that by optimization of the doping concentration, we could further improve the device performance, and also the higher the EQE values for the corporate containing devices at a longer wavelength range can be contributed to the a lower trap density and thus a better electron collection efficiency. I gave showing that the third example about the team-based perovskite solar cell. Usually, for this type of solar cell, the additive for the team fullerant actually acting as the compensator to supervise the tin oxidation, which is commonly used for the fabrication of tin-based perovskite solar cell. However, it was found that the team fullerant actually induce very severe phase separation of the scissor tin iodine crystallization due to the inhomogeneously deperrior during the evolution process of the thin film. In this example, we introduced the ammonium pyrazine as an effective coactive with the tin fullerant, with the aim for producing of a high quality inorganic tin-based perovskite film. The amino pyrazine process pyrazine rings structure, which is very helpful to correlate with the tin to reduce its tin fullerant, to reduce its aggregation. So we first carried out the NMR characterization to investigate the interaction between the aluminum pyrazine and the chemical of precursor solution using DMSO as the solvent. It was found that the resonance single actually appearance at a chemical shift in the range from 7 to 8 ppm, which can be attributed to the proton chemical shift in the pyrazine rim unit. This positive shift in the single for the sample containing the coadditives verifies that the coordination between the pyrazine rims and the tin fullerant. This is also demonstrated by the FTIR characterization, showing off that the carbon to nitrogen double bond, the strength vibration, which shift to higher wavelength number. Therefore, we suggest that the bonding affinity to the tin fullerant, the amino pyrazine successfully prevent that the tin fullerant aggregations through formation sort of complex, and modulates the dynamics balance of the characterization in the film formation process. As a result, the film morphology actually changes from a stone-like and rough surface into a very dense and smooth film, which much less aggregates and pinholes. Therefore, the amino pyrazine further helps to improve the device performance. As you can see, a conversion efficiency of about 5% can be achieved for the season tin iodine device based on the misperance structure. Actually, this efficiency represents the highest value among the same type of devices. We also measured the steady state output of the scissor tin iodine IPZ devices at the maximum point in the air. I stabilized output of around 4.7 was kept towards around 300 seconds scan. Identically, that the device performance actually is quite reliable. And also this APZ incorporated solar cell showed a good long-term stability during the storage within 16 days in the nitrogen filled glove box and maintain its 92% of its initial efficiency. Lastly, I would like to talk about the dimensional engineering for the team-based provider guide. We mainly focus on the minimizing the energy loss in the two-dimensional team highlight provider guide and controlling the crystal orientation. The introduction of the large organic cancer to form so-called two-dimensional provider guide actually can enhance the intrinsic and extrinsic stability of the team highlight provider guide. Particularly, the hydrophobic organic cancers could enhance the extrinsic stability by isolating the provider stems from the oxygen molecules, and also the quantum well structure of the conferring the electron holes in special different places, which improves the intrinsic stability against the oxygen. Here, in this study, we improved the performance of a high quantity two-dimensional falling isono alumina tin iodine provides guide by embedding falling atoms into the PEI, the framework. Interestingly, we found that there's a new funded interclear electrostatic attraction between the electron definitive falling atoms and the falling rim, as demonstrated by the valence number shift of the carbon to falling bonds. In the PEI-based provider guide, a weak valence interaction dominates the assembly of the intercalation organic cancers. However, in the FPR system, a stronger interlayer electrostatic intercalation aligns the adjacent organic cancers in the same direction. So, a strong coordination interaction amongst regions induce a formation of homogeneous distribution of coordinates with a limited size in the precursor solution, which resulted in a generation of narrow quantum wise distribution. Furthermore, this large organic cancer of FPI decreased that the self-assembly of self-assembly configuration, whereby the FPR to the tin iodine layer enhances the alignment of the mesono alumina cancer, as well as the small angle tightening of the iodine to the tin to the iodine bonds, leading to the vertical crystal orientation. We have tested that the conductivity of all the two-dimensional perovskite film, and we found that for the fluorinated two-dimensional perovskite, it has much higher conductivity than that of the PEI-based perovskite. Meanwhile, that the fluorinated PEI-based TFT test also showing that it has remarkable performance enhancement. Obviously, that this interlayer electrostatic interaction can strengthen that the interconnection of building blocks in the two-dimensional tin highlight perovskite and thus improve the stability against the oxygen. So, due to that, the interlayer electrostatic interaction, the perovskite slabs can ordinarily assembled. In this way, it can boost the charge transport in the perovskite layer, and there we can get higher external radiative efficiency in the EQE measurement, and also it has any improvement device performance from about 1.5% to around 3.7% efficiency. That's actually for the two-dimensional team-based device. Actually, is quite high efficiency. To sum up, we investigate inorganic team-based perovskite material and these devices and test the method with the additive, doping, and the dimensional engineering. We hope that we can reduce the oxidation of the team-based perovskite and enhance their device performance. And in the end, I would like to thank my colleagues for their work and financial support. And also, I would like to thank you for your listening.
Thank you, Professor Wang, for a very interesting and informative talk on leadless perovskite solar cells. We have time for 1 or 2 short questions.
Yeah.
And question and answer. We have. Do we have any question? Maybe I will ask one short question. Regarding this, your case 4, you have shown that two-dimensional perovskite is showing the around 2.67% efficiency. Do you think that there is still room to improve the efficiency with doing some optimization?
Yeah, for sure. We have, I mean, in principally, we have rooms to improve the efficiency of for the two-dimensional team-based perovskite solar cell. But the only thing that before doing that, we have to make a stable. I mean, as mentioned before, the oxidation of team-based perovskite material actually is quite easily taking place. I mean, occurring even in the glass box. So that's actually that's the first job for us to make a stable material. For example, for the two-dimensional team-based material, it's much stable than the three-dimensional material. But the only thing that for the two-dimensional material is related to the charge transfer when it make into a layer structure.
Okay. Okay, thank you once again for your interesting talk. And let's move to the another keynote lecture by Professor Yingping Zhou. Hello.
Thank you.
Professor Yingping Zhou, are you there?
Come on.
Hi. I'm here. Sorry. I just have a telephone with my friend.
Okay. Yeah. So let me introduce you first. Yeah. So so Professor Yingping Zhou received her PhD degree from Institute of Chemistry, Chinese Academy of Science, China, under the supervision of Professor Yanfeng Li. And later she performed her postdoctoral research in Laval University with Professor Leclerc, and also as a visiting researcher in Stanford University with Professor Hong Ji. And later in 2014, she became full professor in Central South University, China. And her research focused on organic small molecules polymers for optoelectronic devices. She has published more than 190 peer-reviewed papers, including Nature Photonics, Nature Communications, and she has received more than 7,000 citations with H-index 44. She has pioneered recently a design strategy on obtaining high-performing non-fullerenic acceptors for organic solar cells. And also she has recent records for certified conversion efficiency by NREL. So Professor Yingping Zhong, now floor is yours. So we're looking forward to listen to your interesting talks on organic solar cells.
Okay. Well,
please make full PowerPoint presentation.
Full
screen.
My phone,
full screen.
My sound, yeah.
You go
can
to the
you
full
see?
screen.
Can you see this slide?
Yes, you can see the slides, but put in yeah,
screen.
presentation mode. Yes.
Yeah, here. Yeah. Sorry for the delay. I'm not very well prepared. So today it's my great honor to give this presentation. Today my topic is ADDA accept-based organic solar cells. My name is Yingping Zhou from Central and South University. I will.
Excuse me. Yingping, could you please put in the PowerPoint, the presentation mode? Just click on the presentation mode. Just please click on the presentation mode.
Presentation mode?
Yeah, full screen. Full screen.
Full screen.
Yes.
For me, it's full screen. No.
No. I cannot tell you because it's written in Chinese.
Know how to
on the down side of the presentation, there's an arrow.
Yeah, but in my computer it's full screen. Yeah.
No. You have to share your no. On the downside, you have an arrow, or you have a mark.
Or you can put on 100%.
No, it will cut some, Rana.
Zoom, yeah.
No, I think you are sharing. No, you are sharing the screen, I think.
Here is my computer is.
I cannot tell you because it's written in Chinese, so I have no idea.
No, you are sharing the screen on television. That's why.
Oh, I just written here, and then yeah. What? Wait for a moment. I just restart maybe. Yeah.
Okay.
Here. And I check.
Yeah, please, and also make your
wait
video.
a moment. Yeah. Wait for a moment. Yeah. I just restart my PowerPoint. Here. I'm not sure it is okay. I just share. Yeah. Do you see it?
Yes, we can see that, but again, it's not in the.
I just.
Yes. This one.
Yeah.
Yes. Yeah.
Can you see?
No. Why is not coming? Yeah, you have to press no.
Wait for a moment. I just ask my student to help me for this because for me it's full screen. Yeah.
Okay, we can proceed, I think, and when you can put the
Maybe
camera
you
on.
can just put on the 100%. Just please zoom out and then 100%. At least that would be bigger screen.
If you, I think you use external screen. Remove the external screen.
Yeah, you're right. There's an external screen.
This I just wait.喂，哎，魏天，帮我来搞一下电脑。我的这个电脑怎么不行？他们那边看不到啊。Can you see this screen?
Okay, could you please start like this? No problem.
Yeah,
Because we are running on the time. No problem. You can just start, please.
Can you see the slides?
Yes, we can see the slides. Yes, please proceed.
Okay. I continue maybe. Yeah.
Yes, please.
Excuse me, you can give me the control of your screen from Zoom menu.
Yeah,
Yes, there is a button called remote control. Click on it.
I just share this slide, from my computer. It is normal.
Okay. I think you are connecting to another screen. That's why the problem is happening. So the two possibility, either you proceed this way, or other possibility is to you give control to the organizer. Okay, so I think we are 5-10 minutes late. Please proceed. It's fine.
Click on F5. F5.
Yeah, F5 is okay for me, but it's first screen for me. But I don't know. The attendee cannot see this clearly.
It's okay. It's okay. Don't worry. Don't worry. Just please proceed what you have now. We can see your slides. Okay, only just small slides, but we can see that. No problem.
Yeah,
it's okay. Please proceed. Don't worry.
So I just F5 is here. So F5 like this. Can see the slides?
It's coming.
Yes.
Just coming.
Yes, it's okay. Just you just take a seat. Yeah. Then my outline is the following one. I will briefly introduce research background, and secondly, I will introduce our group recent work about ADA non-flow acceptors. As well known, organic solar cells attract broad interest due to its lightweight flexibility. It can be light area printing. It can be fabricated into transparency, semi-transparency devices. As like the other solar cells, PCE is the key to for solar cells. PCE is usually determined by BOC, GSC, and the fear factor. Organic solar cells usually adopted a bulk heterojunction structure. Active layer, including acceptor and donor, is very important for improved PCE. From the development of organic solar cells, new materials is the key to improve the performance. During the early stage, like in 2005, the system is P3HT as donor, PCBM as acceptor. This system can reach 5 to 6%. After that, scientific communities use DA compolymer as the donor, fully as the acceptor. The highest efficiency can reach 10 to is about 10 to 11%. And since 2015, ITRC and ADA non-fully acceptor ITRC can extend the exception and tunable have tunable energy gap. This non-fully acceptor blending with PBDBT, the PCE can reach 12 to 14%. Until recently, especially in 2020,
Excuse me.
our group. Yeah, pardon?
I think we have to move the slides. Your slides is not moving. People are.
Yeah, I think you just stuck on the first slide of the outline, and we can't see more slides.
Maybe I just changed my computer. I changed the other computer. We can see clearly.
Slides are not moving.
Slides,
yeah.
not moving.
Yes.
Yes. Now it's moving.
Yes.
Okay.
Now.
Okay.
Yeah, it's slides. Yeah. Can you see?
Yes, we can see now. Yeah. So you are now slide number 4, right?
Yeah.
Okay, perfect.
And yes. And in 2019, we synthesized our lab synthesized devices and as acceptor to blend PM6 get above 15%. After that, many groups give offer the higher efficiency. Until now the efficiency reached above 19%. In organic solar cells, compared to silicon solar cells and the perovskite solar cells, in organic solar cell has some challenges, such as there exists high VOC loss, and organic semiconductor materials has low charge mobility. Then organic solar cells, the efficiency is relatively lower than those of inorganic solar cells. How to address these big challenges? How to decrease energy loss from the molecular structure, how to improve the mobility, optimize the field factor. These are 2 key points. So our group is focused on new photovoltaic materials strategies by through control energy level and increase pure quantum yield to decrease energy loss. And the second is to enhance molecular interactions, and I cannot control the button maybe. And optimize morphology to improve mobility. So and previous non-fully accepted design strategy is ADA type. The typical acceptor is RTIC, but for RTIC acceptor, we found the absorption is just is about 700 nanometer. The band gap is close to about 1.63. For this acceptor, this acceptor cannot absorb infrared light well. So we just develop a near infrared non-fluoride. The way is to one is side chain engineering, 2 is end group engineering. How to get a near infrared non-fluoride acceptor strategy is 1, tuning the electron withdrawing ability to increase the intermolecular interaction. The second is tuning the electron donating ability to enhance the molecular charge transfer. Then our group firstly sees as ADA type non-fluoride acceptors. Then we develop near infrared acceptor, but from here we just see here we can get the near infrared acceptor, but has these acceptors have high home energy levels, and which lead to low driving force for charge separation. Then we our group use electron deficient core to replace electron donating core to get a series of ADAD type non-Fourier acceptors. Here is the first successful example. Our group C-size BZRC. This is five ring fused ring. Here we can see compared to the typical acceptor RTIC, the absorption is redshifted to is close to 500 is 900 nanometer. Redshift is 19 nanometer. Here the ELOS is decreased from 0.7 to 0.6, and the band gap is decreased too. So from this work, we can see DAD fused backbone can efficiently regulate the molecular energy level. Here, the molecular, we just BZIC is decreased. The energy level is decreased is 5.42, and then and also can extend absorption, leading to a reduced energy loss. This is our first publication for this structure. After this work, our group do a lot of work about BZIC derivatives and for organic solar cells. Then this work is collaborated with Yang group, extending the conjugated length from the fused ring is changed from pentacyclic to heptacyclic ring. We get the non-Fourier acceptor Y1, and here from this this table we can see VOC is a little increased. Importantly, GSC is increased too. Then PC is increased. Here, from this work, we can see extending the molecular conjugated length achieves nano-optical band gap and improved GSC. And then from this picture, we can see from here, we have many electron accepting unit. Then we because benzene silazole has more intermolecular material interactions, such as nitrogen and sulfur. Then we introduce benzene silazole to replace benzene triazole to get to obtain Y5. This is a very good acceptor, and here compared to Y5 compared to Y9, we found Y5 have more balanced charge transporter and higher charge mobility. We can get the fear factor. Then fear factor is increased from 0.63 to 0.71. More importantly, Y5 is blending with different band gap polymers, donor polymers. We can get the PC all the PC is above 10%. So from this work, we can see Wi-Fi is a universal acceptor. Because Wi-Fi is a universal acceptor, then we add more fluorine into the edge group. Then we design and our lab design and synthesize the Y6. Y6 have extended absorption, and home level is downshifted, and then this acceptor and the device publication is from Yongfang Li lab, and here from one Y6 is blended with PM6. We can see from here at that time the PCE is 12.9 is increased 15.6, and the certified efficiency is 15.6% from LIL. So Y6 acceptor promotes the PC of organic solar cells to a new phase of 15%, and this acceptor is developed in our lab. Now, more happily, many groups use Y6 to achieve higher efficiency. And later, collaborated with Henry Yan group, we modulate the molecular aggregation by sidechain engineering to improve PCE. We just put here is a different sidechain. We found if here the sidechain is third position onto the alkyl, third position alkyl onto the pillar motif, we can get N3. N3 has more face-on orientation. We can get the ternary device efficiency to of 16.7%. Then how to get then after that we think how to get the high performance acceptors. Then we do some work. Our lab collaborate with Professor Hong Bin Wu. We found in high performance organic solar cells have a good device has lower energy loss, and also low energy disorder should be also considered. And by comparing Y3, Y80 to and Y11T, and we found just here beta position onto the beta position of siphon different alkyl side different lengths alkyl side chain. We found introduce alkyl side chains to beta position of siphon to increase the rotational barrier between end group and the fused ring, thus reduce molecular asthma reason. And for this, by modulate the length of alkyl side chains, Y80 possess this is balanced charge transport. Here, Y80 with side chain, side chain is 6 carbon, has higher fear factor of 0.7 and the PC reached 70.1%. And then we collaborated with Inge Xuanli. We get the crystal structure of Y6. Some work indicates that unique molecule stacking to enable 3D transport, because here we can see it's port to end to end have some stacking. So this unique paper stacking can form efficient Hall and electron transport channel is very beneficial to charge transport, and then we can get higher efficiency. And also we optimize the molecular structure to reduce energy disorder. We see that our lab synthesized the BZ4 fluorine 5, 6, 7. We found the Uber energy and energy disorder in the film can be suppressed by extending the conjugated length of BZ4 fluorine series receptors. Here, energy disorder here is fused 7 fused ring is the best non-fluorine receptor. And here, from here, we can see length structure disorder has longer firm mean ring path and higher thermal diffusities. And also Y series receptors have longer firm photons, mean ring path and higher thermal diffusities. So compared to traditional fluorine and non-fluorine ions. So here for this Y series, it has better thermal stability. And here we just reveal the relationship between the thermal stability of ADDA have non-fluorine acceptors, and here is the thermal conductivity. And for 7 fused ring have non-fluorine receptors has higher stability. And to summarize this, our work is the second on is the first on is our group proposes the new molecular design strategy is ADA this strategy, and the second on is synthesize a series of the ADA type small molecular acceptors with near infrared absorption and high electron Hall mobilities, such as Y11 and Y18, and the TV device with low energy loss. Finally, we developed a high performance style non-fluorine receptor Y6, and leading to the rapid improvement of PCs. Power conversion efficiencies. Here is the development of organic photovoltaic materials in our group. And then here, I think I will take a group. Here is our group. I would like to thank our group members, and also I would like to thank our great collaborators, especially my supervisor, Professor Yongfang Li. He's always support me for my work in Central South University. Here's our group. Here, just is a small group. Up to now is increased to a big group. Hopefully, we can get more and more good work. And And also organic solar cells can develop well in the near future and also for commercialization. Thanks for attention. We are looking for more collaborations. Okay, I just finished my talk.
Thank you, Professor Yun.
Sorry for I'm not well because the busy time. I'm not well prepared. Just because before I just finished my PPT slides.
There's no problem. It's okay. We are on time, so there is no problem. Thank you for your work and congratulations to you and your group for achieving record efficiency in organic solar cells. So we are on the time. So before any further question, we would like to move to the third and final invited speaker in this session. So okay, let me introduce Dr. Vida Ingman. And so Dr. Vida, she finished her PhD in 2014 from Ilmenau University of Technology, Germany. After that, in 2014, she joined the Matrix Clausen Institute at University of Southern Denmark. And later in 2015, she became the associate professor. So she has received L'Oreal UNESCO Award for her work on additive assisted stabilization on organic solar cells, and also International Rising Talent Award in 2020. And her research focused on bio-inspired approaches to stabilize organic semiconductors, films, and energy devices. So today she will be presenting her work on additive assisted stabilization of organic solar cells. So let's welcome to Vida. And hello, Vida, are you here? So
yes,
the floor is yours.
I'm here. Thank you.
Yes.
Let me just see if I managed to get everything working. It's a bit tricky with these computers. Let me try. Yeah, now you have to tell me, please, do you see anything?
Yes, please just put on the presentation
on the
mode.
big screen. Yeah.
Yes, exactly.
Is it? I'm clicking it, but I'm not sure. Is it?
Sometimes, yes, we are nervous and we don't see that. That's fine. Just click.
Is it? I did click it now, but I'm not sure if it's. Is it big?
No, not yet.
No, because I see it big here. Wait, I was listening. So maybe I pressed the F5 now. Is that maybe any good, or F1 or something? Wait, no, is this maybe working now? I clicked on doubling the screen. Can you see it big now? Maybe.
I think you have to close your formatted background. You have opened some pictures.
Yeah, on my screen it looks big, but I'm not sure. Is it big on your screen?
No. I think you're also using double screen. That's the problem. Maybe.
No, I don't. Could I make this bigger? Yeah. Wait. Click out and click in. Maybe that helps. Wait. Let's try.
Or you can put on the slideshow as well.
Yeah, slideshow.
Just click on the slideshow.
Yes, and I'm doubling the screen, and is that hopefully?
Yeah, when sometimes you have double screen, it always creates a problem.
Can you see my presentation now? Is it big?
No.
Yes,
no.
not big. We can see the presentation. Please put on the slideshow. Just click on slideshow.
I think you must stop sharing your screen, then leave the presentation mode and share your slide via Zoom. Stop sharing your screen, leave the presentation. Okay, let's see. Stop sharing your screen. And then I leave the presentation mode. Okay, left. And then I go into the Zoom. Let's see. I'll go to Zoom and now I share it. Let's see if this will work. Oh God, I hope it does. Wait, no, share. Can you see it now?
Yes. We see now. Please go ahead.
Oh, please say that you do. You do. Good. Lovely. Okay, so it worked. Good. I'm happy. If by any chance it stops, please just let me know. Then yeah, the computers are evil. That's the conclusion of today.
So you have 20 minutes, so please go ahead.
Okay, but in that case, if you see it, I will just start talking. So thank you so much for inviting me here. I was very happy to receive this invitation, and especially to be in such a famous company. So I'm very happy to be here. What I'm going to talk about is about the photoactive stabilization of organic solar cells. So I'm sure that I don't have to, whoa, too fast, sorry. I don't have to convince you how great organic solar cells are. We all know that they have a lot of advantages. So they're flexible and transparent, and they can come in a lot of colors and shapes, and they're also lightweight, and you can process them in a very cheap way. So using these roll-to-roll techniques. They also don't need direct sunlight, and they work very well also in low intensity conditions, light intensity conditions. And also they're very environmentally friendly. So not only that they have the lowest energy payback time, so that's basically just how much time they have to work in order to produce the same amount of energy that was needed to create these cells. But they also are having they emit the lowest amount of CO2 per kilowatt of electricity produced. So they have the lowest global warming potential of all of the renewable energies. So that's quite cool, right? And in order now to make these cells actually commercial, there's, well, usually the 3 points that we have to address. One thing is the price, and that's already pretty fine with this technology. So both the materials and the processing. The second thing would be the efficiency, and the good news with these organic solar cells have started happening lately. So the efficiency has boomed from some 10-ish, 12-ish% to over 18 at the moment, which is the record now. And that places them quite nicely side to side with this the conventional silicon solar cells. The only thing that makes them a little bit, that gives something to work on is their organic nature. So that organic nature is responsible for these devices being a little bit more sensitive to the typical environmental stresses. So both to oxygen and to heat and to light. And even the best performing organic solar cells at the moment, they under use, so under exposure to these degrading factors, they lose their efficiency relatively quickly, and that is a problem when you look on like a molecular level. Let's say what is happening in these devices in order to lose this efficiency comes down to more or less two things. So one thing is when you think of these polymer molecules, organic molecules, as you shine light on them, they will absorb the light depending on their property. And as they absorb the light, these bonds between the atoms can easily break. And when they break, you're somehow losing the conjugation your molecules, and somehow by losing conjugation, you are losing the absorption, right? And that in the world of solar cells translates into losing the current, which is directly connected to the efficiency of these solar cells. So actually, there were some studies which showed, for example, in P3C, the drop in the absorption will be directly corresponding to the number of destroyed TIFN rigs. So yeah. And then the second thing that is also problematic, when you're breaking these bonds between the atoms, you're also very often creating the radicals and these reactive species, right? So it is very easy for such a, let's say, radical destroyed material to react with the surrounding molecules. And also, it's easy for these radicals to trap the excitons themselves and trap the electrons, so which you are producing in your device. So somehow you're introducing a lot of recombination in such degraded devices. Then, and in several organic solar cell systems, it was shown that there is an exponential even relation between the loss of the performance and the density of these radicals upon aging. So an even stronger problem there. So now that we know approximately what is happening, we have to find a way to prevent it. There's several things that are employed usually. One thing would be definitely the encapsulation, so preventing the oxygen from coming into the device, right? The only problem is that in order to have a good encapsulation material, usually you're using some multi-layer stacks containing barriers and blocking layers, and all of that somehow decreases the flexibility of your resulting device. And also it can decrease somewhat the transparency of such devices. But above all, it will definitely strongly affect the price. So it will increase the price of such devices. So somehow you lose your selling points for such organic solar cells. Another thing that would be the most logical thing to do would be to make more intrinsically stable molecules for these active layers. However, it is not an easy task to at the same time achieve high performance and the high stability, and usually what you read about in the literature is either very stable molecules which don't have that high efficiencies, or very highly efficient molecules but which are not that stable and over time lose their efficiency somewhat. So what we're looking at in our lab is the third option. So I'm not saying this is only 3 options available, but this is our option, and that one is coming down to interfering with the mechanisms in charge of degradation in such materials. So usually we look at the 2 main dominating processes in the organic solar cell. So in some cases, the singlet oxygen will easily react with these molecules. So in such systems, what one can try to do is to add another, so third component of the active layer, which would either quench the singlet oxygen itself, or it would quench the polymer or the acceptor, a triplet state, so which would otherwise generate the singlet oxygen. Or the second thing would be to simply try to interfere with this radical chain oxidation. So once that the oxidation of the polymer or the organic molecule starts, you would generate different types of radicals, which are also drawn here on the picture. And then you can add some molecules which would somehow react with these radicals, so preventing that the radicals interact with your active layer materials, right? So somehow like sacrificial agents, right? And this way, then you prevent this oxidation cycle from continuing. And this is a concept that is actually known from the commodity plastics and works very well there. However, since organic solar cells are optoelectronic devices, then it's not so easy to just copy paste the solution into the organic solar cells world. And this is something that we worked on a lot. Here is just the main ideas about it. So the main thing that is necessary for such an antioxidant to be working well in organic solar cells is that it does not make a mess in your active layer blend. So one thing would be that its energetic levels are harmonious with respect to your active layer molecules. So basically, it should just not interfere with the acceptor and donor levels. It should not fall within this effective band gap, so that you do not create traps in your device. And also, as you know, morphology is very important. So getting the optimal morphology means getting the optimum performance. So this presence of this third molecule of the antioxidant should not disrupt this optimum morphology. And we have, in the very beginning, when we introduced this thing into this idea into the OPV, we have tested first the second type of the molecule, so these antioxidants which interfere with the radical chain oxidation, and somehow it makes sense to that we have done that, because at that point the most typical materials used were the P3HT materials, where singlet oxygen does not play a big role in the degradation. And by using a very extensive library of different antioxidants, we could identify some materials which which fit the needed requirements, and we could achieve quite a prolonged lifetime. In this case here, it's expressed in terms of the accumulated power generation, basically just looking at the amount of power your device will be producing over a certain amount of time. In this case, it was, I think, set to 2 years. And this improvement in the stability was happening because of the stabilization of the molecules. So as you can see here in the FTIR, both the initial stage degradation products, so different carboxylic acids and the hydroperoxide molecules were strongly reduced. And also, sorry. And also in the CO region, you can see that the later stage degradation products are again being reduced, and also that the side chains of the P3HT, so these high hexyl side chains, have been to a large extent retained in the material, which is otherwise known to be the first stage of the degradation of this type of materials. But then also this method can be applied in the systems where the singlet oxygen is the main responsible for the degradation. So for example, here I show you results on the PTB7 PCBM systems. And so here it is known that the singlet oxygen is the main responsible for the oxidation. We have tried then to suppress that with a naturally occurring molecule, so a beta carotene that you know actually from the leaves, and the nice the one that is responsible for the nice color of the leaves in the autumn when we look at the trees. And it is known that this material in the biological systems has a very good, actually superior, the best. It is the best singlet oxygen quencher of these biological systems. So we decided to try to use that molecule here as an additive. And as you can see here, we could reach a big enhancement in the lifetime. So these dotted lines are the devices without the additive, and these full lines correspond to those which have been which contain a beta carotene. And this turquoise line is the PTB7. The red one is just for comparison P3HT. And in this case, also we could quantify this lifetime increase in terms of an increase in the accumulated power generation. But apart from that, we also noticed something interesting, and that is that this initial degradation period, known as the burn-in period, has been almost completely eradicated in case of when beta carotene is present. And we found that very interesting because it was burning is something that is rather controversial for each system. It is pretty different, and for the PTB7 at that point it was unknown what is causing it. So what we decided to do is have a look at how is our beta carotene affecting such devices. For that, we've joined forces with some collaborating groups. And first, we made electron spin resonance spectroscopy measurements on these on pure films containing pure acceptor donor molecules and the blend of the molecules, and then containing the same ones but with also the beta carotene additive. And what we could see is that upon aging, the amount of radicals formed in the presence of beta carotene is suppressed in our blends. And so that already gave us a good indication that indeed we are really stabilizing the molecules. Then we wanted to see what role has the singlet oxygen when it comes down to beta carotene. And we, for that purpose, joined forces with Professor Ogilvie from Aarhus University, who is an expert in singlet oxygen spectroscopy. So we could use a direct singlet oxygen spectroscopy technique, which measures just the singlet oxygen signal in the samples. And I'm saying this because quite often in the literature, you will notice that singlet oxygen is being measured using molecular probes, which is also a good way. However, it can somewhat bias the results, as these molecular probes some can under certain conditions also themselves generate a singlet oxygen. Long story short, we made a series of films with increasing fractions of the PCBM inside of the film, and we have measured it with the single oxygen phosphorescence. And what we could see, which was interesting because it was not previously reported in the literature, that the films containing just the pure PCBM were the ones which gave us the highest singlet oxygen signal. And as we were reducing the fraction of the PCBM in the films, we could see the singlet oxygen signal becoming lower and lower. And at around 60% fraction of PCBM, there was no signal that we could detect anymore with this technique. So we could from this conclude that the singlet oxygen, the main sensitizer of the singlet oxygen in this system is the PCBM molecule. And then we repeated the same experiment, but blending the optimal composition of optimal concentration of the beta carotene. And then we could see that we have very successfully managed to fully quench the singlet oxygen signal. So do notice, please, that the scale here on the right side graph is much smaller than here on the left side. And now that we have established that the PCBM is the main precursor of the singlet oxygen in our system, we wanted to see if we can somehow understand what is actually happening in this burn-in period. So we have kind of taken the same approach and put it on the devices. So we made the devices with increasing the amounts of fractions of PCBM in the active layer. And what we could tell from this, so remember once again, PCBM was the main sensitizer of singlet oxygen. And if I look now at the devices containing the highest fraction of the PCBM, in the presence of beta carotene, I can see that this burn-in is completely eradicated. So this led us to conclude that in case of this PTBM systems, that the singlet oxygen is actually the main responsible for this burn-in. And after that, we wanted to also check what are the possibilities of using this type of additives, but to give them more functionalities. So usually one important thing for these devices is the flexibility, especially for all of the application later on. And if you look in the literature, although inherently polymeric materials are more flexible, still they do suffer from cracks upon repeated mechanical stressing. So we wanted to see if we could maybe develop an antioxidant which could at the same time do some good for the mechanical properties of these films. And for that we have continued working with carotenoids, but we chose for this another similar to beta carotene molecule, and that is the astaxanthin. And we chose it because it has similarly, well, at least from biological systems, we know that it has similarly good oxygen quenching abilities, singlet oxygen quenching abilities, but because of these hydroxyl groups at the ends, it allows the attachment to another molecule. In this case, we chose a PDMS molecule, and in that way we could also make sure that we will not destroy the molecule itself, so that we would not lose the conjugation of the molecule by this attachment. We could somehow aim it to be happening here on the hydroxyl groups. And we tested then these molecules in devices. Oh, before I continue with that, I should just say that was done in collaboration with Professor Skoll from the Danish Technical University and Professor Brooks from McMaster University. And once we developed this novel antioxidant that I call XCPDMS, then we tested all of these compounds in the devices as additives. And what we could see is that well, the blue one here curve belongs to the reference device, so without any additive. We could see that when we include astaxanthin, we get somewhat increased stability of the devices, but this altogether increases much higher when we add in a small amount of this novel developed antioxidant molecule, so this AX-PDMS molecule, that is this darker red curve. And that is somewhat surprising because, well, astaxanthin in itself is a potent antioxidant, and one would expect that it's the addition of just that astaxanthin alone would bring the highest effect. However, we realized that the highest accumulated power generation was achieved for this novel molecule. And although we have already now published the first results on it, we are still looking exactly into detail what is the cause of this. But our current knowledge on that points to a difference in the morphology, well, the resulting morphology upon mixing astaxanthin or astaxanthin PDMS molecule. And it seems that astaxanthin itself generates a much finer morphology, which is also observed in a little bit lower power conversion efficiency in the beginning, and which also in itself positions the astaxanthin not that favorable as with respect to the PCBM, which is the molecule it has to be in contact in order to effectively photooxidatively stabilize it, that is to quench the singlet oxygen. Oh yeah, of course, and just to say, we were very happy also to see that with this molecule we could quite efficiently increase the flexibility as observed here in the elastic modulus measurements. So that was the part of the work which was done in collaboration with Professor Prince from the Uni of Arizona. But as I said, more investigations on exactly how does morphology play a role when it comes to positioning these antioxidants in the active layer is on the way. So more about that I will leave for the next time. I think with this I have eaten all of my time up. And I think that means that I should thank you for your attention and thank you for inviting me here. And also I thank everybody from the group and all of the collaborators. And of course, I think the funding agencies that were kind enough to sponsor us. So thank you very much.
Thank you, Vida, for your interesting approach to stabilize your organic solar cells. Very interesting and very nice idea, naturally occurring, using naturally occurring additives. So I think we don't have any question in Q&A window. So I would like to ask one question. So as you are working on this additive stabilization in fullerene based solar cells, because this fullerene are known as radical scavengers. So what do you think about that if you use this recently discovered this non-fullerene acceptors in the organic solar cell? Do you think that you can use the same approach to stabilize? Will it work for these NFA acceptors also?
Yes.
Did you try also?
Yeah, we are at the moment we're testing this, and actually it would be unfair if I would say that we are the only ones testing it. So there was I had actually a hidden slide, but I'm not sure how to dig it out. But there was several groups. Actually, there's two groups that I know that have published some results on ITIC-based systems. So I know that the UV absorber molecules have shown to be efficient in stabilizing the ITIC-based systems, and another group also reported nickel chelate type of molecules to be also efficient in stabilizing the ITIC-based systems. In general, I think it should be very well applicable to these materials, especially because there is a nice work by Professor Doran's group. I believe the first author is Speller, but don't take my word for it, where they were they were making some both theoretical and experimental work, and they could pinpoint that the problem in most of these non-fullerene type of acceptors was the superoxide radical anions, which I mean the initiating molecule for the degradation. So somehow such materials would be expected to follow this same problem with this radical chain oxidation, generating the same radicals as we saw, for example, in P3HT based systems. So I believe that very much the same approach will be successful for the non-fullerene acceptor-based devices. Yes.
Okay. Do we have any question now? What was the? Oh yes,
I see a question.
Yeah. So if you have read already, so you can answer it.
I see the question was, what was the incentive for limiting adding beta carotene at a rate not exceeding 3%, and what is next for beta carotene research? Mm-hmm. Yeah. So that it's we always there is no theoretical limit, but kind of the rule of thumb. When you add some kind of additive, is to expect that you will most probably get a little bit of a reduction in power conversion efficiency. And of course, the more additive you put in, the better will be the stabilization effect. But the idea is always to make some kind of a trade-off. So for each of these systems and for each of the additives, we always test a wide range of concentrations, and then we took as the limiting value that we don't lose more than 3/4 of the initial efficiency. So that's why 3%. It is just because it allowed us to have still a decent efficiency, but then also to have the stabilization effect. And what is next for BC research? Oh yeah, well, I'm not sure. Well, you mean what are we doing next? I guess what we're trying to do now at the moment in the lab is find successful antioxidants for non-fullerene systems, and what we would also like to do now is to translate then this into nanoparticles. So to be able to this is especially nice, I think, for the upscaling of this whole OPV, so that we can make the same thing but from water dispersion. So somehow that would be kind of the next step. And also the idea was that we're looking into now, maybe it's not related to BC but itself, but of course it will be containing beta carotene. So we want to see also if one can apply such systems further for different type of energy technology. So one of them would be, for example, to try photocatalysis for water splitting, generating hydrogen, because there is some reports at the moment in the literature which are showing that non-fullerene acceptors based systems have very good ability to contribute to that. So that's something, if that's what you mean, that's something which is the next for the BC research in the lab for us.
Okay, great, Ida. Is there any more question?
I think one attendee to talk.
So should I start this 5 minutes presentation now? Or should I wait for some more questions, because we have still 15 minutes for more discussions?
Yes. Samson, you can talk. Please unmute your mic. Ayedel Samson.
Sorry, Yusuf?
I think he's not there.
One more question, Vida. I want to ask that when you use this beta carotene, so are you adding this in the bulk heterojunction, or you are using just with separately with your PCBM system.
Yes, we put it directly into the active layer.
Into that
So,
system,
yes,
right?
yes,
Yeah,
yes,
exactly.
yes. I guess it could be also interesting maybe to put it as you say, like on top of it.
Yes,
but
as a bilayer, like because basically you will have different efficiency and the different recovery.
You're right.
Mechanism when you use in the bulk heterojunction or when you make in the bilayer.
Yes,
because
you're right.
basically, yeah, the main culprit is acceptor, this fullerene acceptor. So I don't know what will happen when you use it, adding just in the PCBM. So,
right. It would be interesting actually to try it as separate layers. Yeah, that's a good idea. Yes, we should do that. I can disconnect myself if the next.
yeah, please, you can stop sharing.
Okay. Yes, I was thinking. Okay, good. Thank you so much once again.
Yes, thank you for your time, and I think we can move now to 5 minutes talk. If there is no further questions, I would like to move to 5 minutes talk, and the first talk here is synthesis and characterization of copper, iron, cobalt, tin sulfide thin films prepared by the simple. Something is missing. By Sophia. Did you see who is going to present this talk?
It's okay.
Safia Darisi.
I'm honored.
Hello. Yeah.
Hello everyone, I'm Safia Darisi. I'm student in Faculty of Science Melania University Qadiya Marrakesh, Morocco. I'm honored to present my work about synthesis and characterization of CFCTS 50% cobalt tin film prepared by the sample technique sol gel for solar cell, supervised by Mrs. El Kisani and Mrs. El Asali, and I thank for giving me the opportunity to participate in this conference. The outline is introduction, films elaboration, results and discussion, and finally conclusion. Introduction. The CFCTS is a potential absorber for a low-cost thin film solar cell because it has a direct band gap between 1.2 electrovolt to 1.7 electrovolt. It has a large absorption coefficient over 10 power 4 centimeter 1. It is an eco-friendly material. The novelty of our work is that the preparation of the CFCTS film via facile sol gel spin coating method is without sulfurization process. Films elaboration. The films is synthesized by the sol gel spin coating technique, which is a simple, less expensive and easy technique. We prepared the solution of this CFCTS film as we see here in the picture number 1. The tin film were deposited on glass substrate by the spin coating method as we see here in the picture 2.
Excuse me, there is no slides. Please run again.
In a nitrogen atmosphere in different temperature.
Please stop it and run the slides.
Yes, please.
X-ray
excuse me.
We notice the presence.
Excuse me, Safia.
112 plane. Other.
Yes.
There is no slides moving. Safia, hello, Safia.
Then 204 plane. At it peak. 1, 2.
We can't see your slides.
Is more.
Hello.
I'm still what's the problem.
We cannot see your slides.
Hello everyone.
Hello everyone, I'm Safia Dressi. I'm student in Faculty of Science Mlalia Université Kadi Ayad Marrakesh, Morocco. I'm honored to present my work about synthesis and characterization of CFCTS 50% cobalt chain film prepared by the sample technique sol gel for solar cell, supervised by Mrs. El Kisani and Mrs. El Asali, and I thank for giving me the opportunity to participate in this conference. The outline is introduction, films elaboration, results and discussion, and finally conclusion. Introduction. The CFCTS is a potential absorber for a low-cost thin film solar cell because it has a direct band gap between 1.2 electrovolt to 1.7 electrovolt. It has a large absorption coefficient over 10 power 4 centimeter 1. It is an eco-friendly materials. The novelty of our work is that the preparation of the CFCTS film via facile sol gel spin coating method is without sulfurization process. Films elaboration. The films is synthesized by the sol gel spin coating technique, which is a simple, less expensive and easy technique. We prepared the solution of this CFCTS film as we see here in the picture number 1. The tin film were deposited on glass substrate by the spin coating method as we see here in the picture 2. And finally, the prepared films were calcinated in a nitrogen atmosphere in different temperatures. Result and discussion. X-ray diffraction. We notice the presence of the peak corresponding to 112 plane, other peak corresponding to 204 plane, and the plane 321. These results show that the film have a tetragonal stoned structure according to the standard card number 45 1446. We also say that the major peak 112 is more intense and narrower, which confirm that the crystallinity is good. we can say that the major peak is observed at 325 centimeter 1 and another peak at 289 centimeter 1. The intensity of the peak 325 is high, indicating to the annealed film has a good crystallinity, confirming the XRD result. Morphological and compositional analysis. In the picture E shows a uniform reproduction on the film surface. The layer of CFCTS is denser and homogeneous. For the figure B, the tin films contain the elements copper, iron, cobalt, tin, sulfide, and the percent iron and cobalt almost the same according to the percent of the concentration 5T%. Optical analysis. In the figure 6, the band gap of the CFCTS is 1.58 electrovolt. This result shows that the CFCTS film has the ability of absorbing the majority of the solar spectrum. Conclusion, we found that the CFCTS 5T% cobalt tin film successfully prepared on glass substrate by the solid spin coating without sulfurization process. We found that the optimum annealing temperature is 400 degrees Celsius. And finally, the film has a good crystalline structure and a band gap 1.58 electrovolt, which make the CFCTS film as a good absorber in visible range and suitable for solar cell. And thank you for your attention.
Thank you, Sophia, for your presentation. So the next talk is efficiency prediction of copper chalk pyrite-based solar cells, a post-principle study. I think it will be presented by Bikaruin Muad. I'm sorry for if I'm not Bikaruin Muad, right?
Is Bikaruin Muad. I'm a second-year PhD student, supervised by Professor Bali Mohammed. Today, during this presentation, I will discuss with you a study on chalcopyrite materials, which is the study of efficiency prediction of copper chalcopyrite-based solar cells, a first principle study. First of all, this is the plan for today's presentation. I will first present the general concept and the motivations behind this study. After that, I will describe in details the adopted theoretical framework. Further, I will show the most crucial obtained results, and I will finish my presentation by giving a brief conclusion of the work. My PhD thesis focuses on solar energy materials, mainly new materials with high solar conversion efficiency and low production costs, things that will accomplish the industrial goal. So in this study, we have focused on chalcopyrite materials, principally used in thin film solar cells, and achieving the industrial goal requires a deep understanding of the different mechanisms behind solar energy conversion. So to obtain the optoelectronic properties of chalcopyrite materials, density functional theory was used in an attempt to solve the Schrödinger equation as implemented in the Vinci code. During this study, we have adopted an approach based on the NBG plus U approximation that minimize time and improve results. After that, we have used the spectroscopic limited maximum efficiency, which is a theoretical model for calculating photovoltaic performance using the FT results. And we have considered two back reflection cases to determine the effect of a perfect reflector at the back of the solar cell on the performance. From band structure results, we can observe that in all cases, both valence band maximum and conduction band minimum are located at the gamma point. Thus, all studied materials are exhibiting direct band gaps. The remarked decrease in the band gap with heavy anion is since their valence band maximum is composed from hybridized copper D states and anion P states, and the presence of lower atomic energy levels in heavier anions shifts valence band maximum to higher states, decreasing accordingly the band gap. Now, the following figure shows that all absorption coefficient components for studied materials are anisotropic. Moreover, chalcopage materials show the highest absorption coefficient among compounds used in solar cell. So, to estimate the efficiency of the absorber film in the normal test condition, we first present the room temperature plots of the current and power as a function of voltage for the studied chalcopage materials. The current voltage plot shows a large short circuit current density for copper indium diselenide material. However, this material has a smaller open circuit voltage, leading to a reduced output power. Now, concerning the efficiency as a function of the tine film thickness, we can remark that the efficiency begins to saturate after overpassing the 0.5 micrometer thickness, and it decreases by making the film thinner than this value. Therefore, without too much loss in efficiency, we cannot obtain an efficient thin film solar cell with a thinner absorber layer than this value. Moreover, from the plot of efficiency for the studied compounds versus the band gap, we can conclude that the cell with a reflecting rare surface is the most efficient due to the enhancement of absorbing and recycling photons. Therefore, we can classify copper indium disulfide as a potential absorber layer with a power conversion efficiency larger than 30%. In conclusions, first principle computations using the MVG plus U approach have been conducted to investigate the optoelectronic and photovoltaic characteristics of chalcopage materials. Our findings indicate a good agreement with experimental results, which prove the reliability of the chosen approach. The inclusion of a perfect reflector in the chalcopage-based solar cells results in higher performance. These results will certainly help the researcher and engineers to design and optimize thin film photovoltaic devices working with copper-based chalcopyrite. And thank you so much for your attention.
Thank you for the talk. And the next talk is property evaluation of iron silicon nickel base under the Earth's inner core conditions, aside from the ab initio investigation by Al-Mehdi Salmani. Hello, are you here?
Everybody, my name is Mustafa Zidan. We are talking about today. We are talking about properties evaluation of under the Earth's inner core condition by using density functional theory. Now, we are going to talk about this planning of this presentation. Firstly, the introduction on geophysics. Secondly, the calculation of by using density functional theory. Thirdly, the electrical resistivity of HCP structure. And fourthly, the thermal conductivity of HCP structure. And finally, I summarized my presentation in the conclusion. Let me to start with some information about density functional theory. We can use the DFT calculation in many areas of materials research. For example, chemistry, physics, surface science of materials, and geophysics, which is the subject of our topics. Now, we are going to turning our attention now to introduction on geophysics. The geophysics is a branch of earth science. There are several methods which using in geophysics, such as the gravimetry, the geomagnetism, the seismology which based on density, the electrical resistivity which based on electrical resistivity. Now we pass at the internal composition of the Earth. The internal composition of the Earth is divided in three parts: the inner core, the nucleus, which divided in two parts: inner core and outer core, and the second part, the mantle, and the third part is the crust. Now we pass at the stability of iron. The iron is excited in the nature at the three structure: the FCC, BCC, and HCP structure. Now we pass at the calculation by using density functional theory. We see some information about if a compound structure and the volume of some structure as a function of pressure. Now, let me to pass at the electronic density at 360 gigapascal of FeSe. Some structure, the electronic density of some structure. Now, we pass at the bond structure, the even structure with we have calculation we have performed the calculation of the bond structure at 360 60 gigapascal of FeSe. Now we pass at the Fermi surface at 360 gigapascal, the condition of the Earth's core. We see the cross section of the Fermi surface are low at height percentage of the amperages of nickel. Now we pass at the electrical resistivity of HCP structure. The electrical resistivity as a function of pressure for first graph, and the electrical resistivity as a function of as a function of temperature for second graph. For first graph, the electrical resistivity are decreasing as a function pressure, and the second graph are increase with the temperature. And we pass the term for the thermal conductivity, which increase with increase of temperature. Finally, we conclude which all material converged to the 100 of electrical resistivity have the possibility to exist in the inner cores, because many studies consider this value of the electrical resistivity is this value of the Earth's core. Thank you very much for your attention.
Thank you for a nice talk. And now we have the last 5 minutes talk, impact of conducting polymer, interlayer, and iodine doping on the electronic properties of hybrid solar cells based on alkylated sexythiophene and nanostructured zinc oxide by Huda Jebari.
Hi, I'm Huda Jebari from Laboratory Lamsi University, Mohammed V, Morocco. Before starting my oral participation, I would like to thank the organizer committee to give me this opportunity to present my work concerning the impacts of iodine doping and the polysulfidine interlayer on the electronic properties of hybrid solar cells based on alkylated sexythiophene and nanostructured zinc oxide. The hybrid organic solar cells based on intrinsically conducting oligosylphane and polysulfidine as electron donor and zinc oxide as electron acceptor have attracted a lot of attention because of their intrinsic low cost, their environmental stability, their flexibility, and their moderate power conversion efficiency. Thus, Several research reports that the electrical properties are in a major part controlled by the doping process and by the electron and or host-supported layer. And as a result, they found that both processes make better the photovoltaic response. While the main goal of this work is to investigate the influence of polyethylene within anti layer and the iodine doping effect with various amounts of electrical properties of hybrid solar cells based on a mixture of the cell cyclophane as blunt donor and nanostructure zinc oxide as acceptor active layer. A series of solar cells studied in this work are fabricated in a conventional sandwich structure with and without polyethylene as a host supported layer. We include iodine indium tin oxide, coated glass as transport electrode, a host supported layer based on a polyethylene were deposited by spin coating, a photoactive layer and alumina electrode were fabricated by successive deposition using the spin coating technique, and they are completed by thermal evaporation of alumina circular contacts on active layer. Here is we have the dark and the light current service voltage characteristic of the sandwich device. In the dark part, the current voltage curve is symmetric and non-linear, suggesting that the contact between alumina and active layer is rectifying. And this is in good agreement with other research on Shockley diodes based on cyclophane. In this part, we insert an artificial layer between the active layer and the ETO transport conductive electrode. This figure describes the current voltage characteristic of the photovoltaic device doped with polyethylene as a hot transporter layer, which measured in the dark and under illumination. Then we can notice that the rectifying behavior is lost. And to improve the performance of the study solar cells, the last part of this work was focused on the study of the influence of iodine doping on the electronic and photovoltaic properties of the photovoltaic device. Indeed, we have introduced a different proportion of iodine of 5%, 10%, and 15% in the active layer. Here represents a summary table proving that the cell which integrates the HCl polyethylene as household polyethylene layer and 10% iodine concentration in active layer appears the best performance because it allows to have a significant increase in short current voltage and a remarkable increase of open circuit voltage. To sum up, the polyethylene substitutes the cyclophane and zinc oxide were easily synthesized by chemical methods. Also, the thin films were easily deposited by spin coating technique. Therefore, the sandwich device with and without polyethylene as a hot transporter layer, and the doped one by several amounts of iodine were fabricated. The most important finding in this in the experimental study can be summarized as follows: the no-ohmic rectifying behavior of the studied device, and the cell which integrates the HCl doped polyethylene as artificial layer and the 10% iodine concentration in active layer appears the best performance, and this may be due to the increase in the concentration of the charge carriers of the organophane, and this is in good agreement with the research works of the electronic properties of doped small molecule organic semiconductors. And thank you for your attention.
Thank you, Huda, for your nice presentation. And we have finished all the 5 minutes talk for the session. And I saw some questions for probably, yes, for Safia, the receipt from Huda. So Safia, are you there? Hello, Safia? Hello. There is a question for Safia, why you did not apply the photoluminescence characterization technique?
Yes.
Could you please answer, Safia?
Yes.
Why you didn't use the photoluminescence technique?
I did not use the photoluminescence characterization because the laboratory does not have the material to do this analysis. I substitute this analysis by analysis UV visible.
Okay.
Thank you.
Next question, I don't know, it's for Safia, from Huda again. Did you anneal your samples in order to minimize the deep defects?
Repeat this question.
Did you anneal your samples in order to minimize the deep defects? Did you heat your samples to minimize the deep defects? To reduce the defects?
Defects?
Yes, the traps.
Tracks.
You can, I think you can read yourself in the question and answer this question. If I'm not able to clarify you. This question is from Muad. Okay. Hello, Muad.
Yes.
Yeah, you have to mention the name.
Yes.
Muad, there is a question for you. Did you anneal your samples in order to minimize the deep defects?
Can you repeat the question?
Did you anneal did you heat your samples in order to minimize the deep defects?
In fact, we didn't study the experimental process. We have done all, just the theoretical part.
Okay. I saw also that some raise hands in attendees. So I think the first one is this Camelia Monish. I think we can allow to ask the direct questions. I don't know for whom they have the questions. Please, Camelia. Yeah, also the first Camelia, and then we can go for the next attendee, Samson. So Camelia, you can ask. Hello. Do you have any question, Camelia? Camelia Monish. Please allow to speak. Okay, maybe next, Samson, do you want to ask any question? Hello, Yusuf, can they ask the questions? Hello, something happened. Hello.
Yes.
Can we allow to attendees to ask the questions? There are some raised hands in the attendees.
Yes, I allow him to talk. Since he has to unmute his mic. Yeah.
Okay, Linda Hussein. Linda Hussein, you can talk. Linda. Linda.
We can't hear you, Linda Hussein.
Amiri Said. Dr. Samarana. Doctor. If there is no question, we have to conclude this session. Thank you very much for Dr. Samarana Kazim and all keynote speakers of this workshop 2. Thank you for Professor Shahzad Ahmed and all team of this workshop.
Yes, I would like to also thanks to all the speakers and all the attendees for having patience and listening to all the speakers. And if I don't know if the Chair Shahzad Ahmed want to say a few words to conclude this session.
Well, thank you very much, Dr. Qasim, for chairing this session, and it was a real pleasure. My special thanks to all the keynote speakers, invited speakers, and the organizers to assembling such a great program. Thank you very much. I know you have a next session for lithium-ion battery, which is also many star scientists are giving the talk. It's also very helpful for young people. So thank you very much, organizer and Professor Yusuf Jaz. Thank you very much.
Thank you very much, Professor.
Let me see. I saw some message. Just a moment. Sorry.
Proposing this workshop.
There is some more message. Thank you for the presentation. If there is anybody interested in asking questions, Amir, Saeed, or Samson, please ask. Otherwise, we just close the session. Okay. So I think there is no more questions. So thank you, everybody. And thank you all the organizing committee members and you, sir, for organizing such a nice conference, and all the participants who were listening carefully all these sessions, and very interesting work.
Thank you very much for for sharing this session and for giving a keynote yesterday.
Yeah, it's my pleasure. Yeah.
Thank you very much for Professor Shahzad Ahmed and the whole team of this workshop.
Yeah.
Thank
you all the speakers. Yeah, thank you all the speakers, and especially our Chinese colleagues who were spending time with us in this session. So thank you, Minghui, and thank you, Yingping, for spending time with us for all your sessions. Thank you, Vida.
It's a pleasure for us.
Yeah.
Thank you very much.
Take care. Bye-bye.
Bye-bye. Hello, Federico. Elise,
Hello, hello.
Yes.
Can you hear me?
Yes, we can hear you.
Oh, okay, good. Thank you.
Just try to share your slide.
No, I don't have a slide for today.
Okay.
I'm the moderator.
Okay.
The first speaker is Professor Monsef Krafti.
Yeah. You have the biography for Monsef?
No, I don't have anything.
Yes, I will. You can find it in the IRSEC website.
Oh, okay. You mean to present him?
Yes, for presentation.
Oh no, I have here. I have here with me. Thank you.
Okay.
But I'm not sure if he's already around.
Monsef is not yet connected.
Hello?
Hello, hello, Professor Crafty.
Hello, how are you?
Hello, good to see you.
How's it going?
Good to see you.
Ready?
Yeah, I'm waiting for the instructions here to. So
okay.
We can start.
Share my screen. I'm not sure if it actually. I guess I can't. Seems.
Okay.
Hello, Yusuf. How are you?
Hi, how are you? It was.
Good to see you, Yusuf.
Hello, Professor Orland.
Good to see you. Thank you very much again for inviting me to be
Hello,
here.
Professor Krate.
Yeah, hi, how are you? It was. Took a while to get in, I guess. I'm not sure about tomorrow, by the way. Did you see my email? It's too early for me.
Yes. We are looking for moderator for tomorrow.
Okay, great, because it's already 7 o'clock here. So, so tomorrow will be 3 o'clock or 4 o'clock.
It's really pleasant to see you again in IRSEC.
Yeah,
The
too
last
bad
time
is
was in Rabat.
hopefully next year. Let's see.
Thank you, Professor Orland. You are now used to be with us in this workshop.
Yeah, thank you. It's a pleasure.
Really appreciate your effort to be always with us.
Thank you very much for inviting me. It's a pleasure. Thank you to Professor Larousse, to Professor Garoun, and to Romani also. Thank you.
Dr. Romani, I think, is with us. We can, I think, we'll start.
Can I share my
5 minutes?
Hi, Professor Razaz, Professor Orland, and Professor Krati.
Hi, how are you?
Pleasure for me to see you.
Great.
Yeah, and thank you to be here with us.
Thank you for the invitation.
Thank you.
Professor Moussef, you have photos from Morocco, yes, no? In your background. Photos in your background.
Yeah, my background is
from
close, yeah.
From Morocco?
Actually, Tunisia, but close enough.
Tunisia, okay. It seems like Morocco.
Yeah, it's the same anyway.
Same sceneries.
But mostly in France as well as now US. So I've been all over the place. Can I share the screen or you have to?
Yes.
Because it said you cannot start screen share while others are participating. I guess we may have to wait.
How can I share your screen?
You're seeing my screen? Okay. So I'm sharing. Let's see, yeah. Just to make sure you have the PowerPoint. Do you see the PowerPoint?
Yeah.
Do you have video in your presentation?
Couple slides, yeah, but just animation.
No video.
No video, no, just animation. So I'm not sure, actually I can check it just to see if it works. Even though it doesn't matter.
Yes, it works perfectly.
Yeah, it's working.
Okay. Yeah, okay. Maybe this one.
Yeah, it's working.
Okay, good. Just an animation. Okay, great. I think we're set. Let me know when you want to start.
I'll wait for the instruction here. So,
okay. Yeah, it must be a challenge to organize everything remote for these 2 years.
I did this myself last August, yeah, and it's different, yeah, it's different.
Mm-hmm. Yeah, it's better to do it the ones or the other. You cannot do hybrid. It's very difficult.
Yeah, oh yes, definitely. Yeah.
We tried hybrid, but yeah, it didn't work very well because you have two different audience, and it's hard to meet both expectations.
Yeah, it's true, and people to control the audience. I mean, the questions from the audience, all that. This is complicated, I think, for the hybrid. Yeah.
Already, yeah, remote is already complicated enough.
Hello, Mr. Carl, say hello.
Hi, how are you?
Hello, Najima. How are you?
Thanks. Thank you for being with us and honoring this workshop. Thank you very much.
Yeah, thank you for the invitation. Thank you.
It's my pleasure, Najima. Thank you.
See you next year, perhaps.
Yeah.
In person, hopefully. Even though.
Mr. Monsef, we will see you in 30 November in Marrakesh.
Hopefully, I still need to decide. It's not easy here to travel. But I thought you could do remote. But anyway, we'll see. Yeah, it's Colorado. It's we already have a lot of, like Europe, increase in the cases here. Even though we're half a month or a month behind. So this is the 5th wave around here.
Professor Ibrahim Ben Hammou, you are here?
Yeah, hello everybody.
Oh, hello.
Hi, Ibrahim, how are you?
Fine, with you?
I ask you tomorrow to share the session. Professor Clardy will not be with us. It's because of time difference. It's still light in the US. If you can
no problem.
Share,
thank you very much. Yeah,
tomorrow.
it's around 3 a.m. here. So.
Oh, good morning.
Yeah, it's in the middle. It's not too early. It's not too late. So it's hard.
Okay, no problem.
Thank you very much.
It will be my pleasure.
Thanks. It's already 7 a.m. here. In the afternoon over there, I guess. So let me know when to start.
Professor Orlon, you can start now.
Oh, okay. So, yeah. So thank you very much, Professor Zals, and it's my pleasure to be the moderator for this first session of workshop number 4, energy efficiency in the buildings and construction sector. And the subtitle for this workshop is Building Energy Challenges in Urban Sustainability Emergency. We have 2 distinguished keynote lectures this morning, and 4 panelists. The panelists are Dr. Faham Aranjani, Professor Mohamed Garoun, Professor Najima Laroussi, and Dr. Zaid Romani. And our first keynote speaker is Professor Monsef Krati. The title of Professor Krati's presentation is Overview of Smart and Grid Interactive Efficient Buildings. Professor Krati is a professor and coordinator of the Building System Program Civil, Environmental, and Architecture Engineering Department at the University of Colorado. He has a vast experience in designing, testing, and assessing innovative energy efficiency and renewable energy technologies applied to buildings. He's the co-founder and the editor of the Journal of Engineering for Sustainable Buildings and Cities. He has directed several projects in designing energy-efficient buildings with integrated renewable energy systems. Professor Crafty has published over 300 technical journals and handbook chapters in various fields related to energy efficiency, distribution generation, and demand-side management for the built environment. Moreover, he has published several books on building energy efficient systems. He's a fellow member of the American Society for Mechanical Engineers, ASME, and he has also taught several different courses related to building energy systems for over 30 years in the United States and abroad. And as part of his activities as a professor at the University of Colorado, Professor Crafty has been managing the research activities of Energy Management Center with an emphasis of testing and evaluating the performance of mechanical and electrical systems for residential and commercial buildings. He has also helped the development of similar energy efficiency centers in countries, in other countries, including my country, Brazil, Mexico, and Tunisia. He has an extensive experience in promoting building energy technologies and policies overseas, including the establishment of energy research centers, the development of building energy codes, and the delivery of energy training programs in several countries. So without further delay, I would like to pass the word to Professor Crafty, and so
thank you, Professor Orlando, for this lengthy and nice presentations. Today, I'll talk a little bit about the latest, at least research activity we're doing, as well as in the area, obviously, of the built environment, as well as I'll introduce some of the technology that we are working on, as well as we hope the future building will have. Actually, I'll talk about the center, what we call the BEST Center, the Building Energy Smart Technology Center, as well as some of the activity that we're doing. So my presentation will focus mostly on, as I said, the built environment and the energy efficiency, as well as what we call smart technology specific to the built environment. So I'll introduce what's the incentive, including the energy use trend, as well as the current trend in energy efficiency of building. I'll talk about the new concept that actually introduced by the Department of Energy here in the US, related to what we call grid interactive efficient building, which is another name for smart as well as sustainable building. And I'll go through maybe a couple technology related to smart building, as well as a few applications related to obviously designing and operating building in general. So why building are important? Obviously, we spend a lot of time in building, 80%. This is before COVID. Now maybe 90 or 95% we're spending inside, unfortunately, including the way we're doing conferences like now, remotely. In addition, building are made up a lot of community and cities, and a lot of people live in city. Used to be only 20% live in city in 1900. Now, 80% of people actually live in the city. The expectation is that 50% of the population now is actually in urban cities. There will be 60% by 2030 in less than 10 years or so. And obviously cities are made up of buildings. So That's why in most countries, building use the most of energy. In the US, it's about 40%. That's the actually the yellow band there. That's the trend over the years of how much building consumed compared to other sector of economy. In Europe, like UK, for instance, is even higher, 60%. In China, industries remain important. So building is about 25, 27%. In India is 50% of the energy, of the total energy of the nation actually is used by building. Worldwide, actually, 39 to 40% of the total energy of the world consumed is actually by buildings. So it's the first sector that actually consume energy. But the future is ominous. So, for instance, we show here the energy use per capita, meaning per person, as well as the energy use per floor area of building in kilogram of equivalent coal equivalent. Obviously, the US have the highest, roughly, with Canada, and other country a little bit lower, but China, actually there's two China, what we call the rural China and the urban China. Here in this second figure here, we show the trend, the blue line that the US, that's the energy consumptions per floor area. In the US is stabilized over the last decade or so, but China is coming. China now is what used to be in the 1960s, the US. So the expectation is that the energy consumption on average in China will increase dramatically, double, if we use the example of the US. So the future, there's a lot of need on energy. And that's why in many countries, there is interest in improving the energy performance of building. And we talk about many standards and codes as well as mandate related to design and operating building. So for instance, sustainable building using different rating system like LEED or BREEAM in the UK. Intelligent building, and that's really what the focus of my talk today, related to building that are adapting to the need of the grid, as well as what we call, because of the climate change and the extreme event, resilient building. So all these notions, sustainability, smart, resilient building, is combined these days into hopefully better design and operation of building. EU, for instance, has currently a mandate that all new buildings has to be net zero energy, designed to be net zero energy. Similar in California, the US, the total US may come in 5 to 10 years or so, that all new building has to be net zero energy. Actually, many counties in the US, that's the norm. Every new building has to be net zero energy. When we look at a typical US building, commercial building, we could see that obviously the energy consumption happened during the operation of that building. So this is a pie chart that shows how much energy is used during the manufacturing, that's the blue here, as well as the maintenance, that's the yellow, and then the maroon here is the operation of the building throughout the its life. So when we do life cycle assessment in terms of carbon emission, for instance, we focus quite a bit on the operation, not just on the manufacture, transportation, and construction of building. This pie chart shows in the US, at least for the entire commercial building sector, where energy is actually used. As you could see, heating, space heating in the US is important, as well as lighting. And that's important to know because that's where you need to focus at least your attention in terms of reducing energy consumption of building. So why we're really focusing, at least in building energy efficiency, at least many policymakers as well as the country, because as I mentioned earlier, that's where we spend most of the time. So health is an important issue. That's where most of the energy in many countries are used in the building, but building also affect the ecosystem, the environment in general. When we have urban setting that actually create its own ecosystems, it will use a lot of material resources, both in terms of the construction as well as energy. And obviously these days we talk about a lot of carbon emissions and climate change. Building is actually one of the main source of carbon emissions. And as I mentioned, because of COVID, we're spending a lot of our activity, so we need to feel good to actually be productive. So when we design and operate building, we have to keep in mind the productivity of occupants, the health of occupants. So in terms of the future trend, as it's mentioned, we are trying to design now energy efficient, resilient, and smart building. Why is that? Because it will, as I mentioned, reduce the energy consumption and improve operating cost in terms of reduction for the homeowner, for instance. It will add the value to the property. For instance, NREL did a study that showed any $1 reduction of energy consumption translate into $20 increase in property value. So you could sell your property higher. It will also increase the security, as I said, with the climate change. There's a lot of extreme events, so it has related to the resiliency. And then we can integrate with the renewable into smart grid and smart city. So when we talk about smart building, is actually a subset of a smart city and smart grid. These are some of the program and some of the trend now in the US when we talk about building. So when we design building, we have to say, what is the purpose of the design? So I mentioned currently there is a lot of interest and there is a push to have a net zero energy building, and in general, what we call grid interactive efficient building, meaning building that interact with the grid, that responds to the needs of the grid, including the supply, the availability of the supply. For instance, of solar energy or wind energy that changes over the day and over the season. So the shape of the load has to change in the building. And that's the challenge as a designer and operator that we have. We also talk about the grid connected community at community scale, similar to a grid interactive efficient building. In the US also, there's a lot of talk about making all building and city electric. So we convert from the fossil fuel to electricity, all the operation of the systems, which lead to easier decarbonization of that building, as well as making building more resilient by introducing renewable energy as a power supply within the building and the community. So I'll focus today mostly on the grid interactive efficient buildings. As I said, this notion is very common the last 5 years especially, and it's promoted by the Department of Energy as well as RMI here in Colorado and international, as well as the national associations. So what is GEP? The abbreviation of what we call grid interactive efficient building is actually building that are energy efficient, that has the capability to shed load, shift load, modulate load, as well as generate power. So everything that you need to effectively, dynamically change the shape of the building load. And the term is actually synonymous of introducing technology that allow that. And many of these technology are already here, like smart glazing, for instance, smart thermostat. But we have also other systems that I'll talk briefly about what we call smart building envelope in general, as well as HVAC systems. In general, is related to anything that could be controlled. Okay? So what does energy efficiency do? And this is obviously reducing the shape of the load profile, the energy load profile, making it lower. And we know we've been doing this for many years, 50 years or so, is to try by implementing, for instance, thermal insulation or high efficiency air conditioning, we can reduce the load throughout the year and the day. Load shifting, that's usually a demand side management option. We try to actually reduce the peak of the load through, for instance, sensor, for instance, dimming for the lighting, reducing the operation of the HVAC by setting either up or down the temperature, depends on heating or cooling mode. Load shifting, that meaning we shift the load from one peak period to another off-peak period. And this could be done by thermal storage, either within the building envelope itself, or using active system like chilled water or even ice storage system for cooling. Modulation, load modulation, this is typically for frequency regulations by using, for instance, variable speed drive or battery inverter. We could balance between the load and the demand and the supply side in terms of the frequency, for instance. Generation, obviously using on-site PV, for instance, we can generate power and try to meet, or at least partially, some of the load of the building itself. So these are related to many technology, and actually we reviewed this in a paper in, I guess, published in SME 2020. There is many technology that we are considering as dynamic or smart, what we call the GAP technology, either related to architectural, meaning building envelope, and I'll talk about a couple that we're working on in our lab these days. Smart insulation as well as smart shading devices, but we already know and we have smart glazing. In the mechanical, we have dual fuel HVAC system, thermal energy storage. These are existing and well-known technology. In the power generation, we have the PV as well as what we call combined heat and power system. And obviously in the control, there's many technology. First and most is a smart thermostat. So as I mentioned, I'll talk about now a few technology that we are working on related to some of the GAP technology, including these are some of the system we are trying to develop and improve, including double skin facade as well as dynamic roof, smart shading devices, and what we call smart or dynamic insulations. So I'll talk about a couple, as I said, to give you an idea of what we mean by smart or dynamic. So this is obviously one solution of many. This is what we call the mechanical solution of dynamic insulations. So similar to a louver in a shading device, we can actually place the insulation layer in a louver that can rotate. It depends on the need. So if we want to fully insulate it, we close this louver systems. That gives you the highest R value or the lowest U value. If we want to have lower R value, we start gradually opening this louver with a certain angle theta there. And we showed using a lab testing that depends on the angle, we have different R value. Go from a high level, and obviously that depends on the thickness of the initial insulation, to a low value, which related to the convection heat transfer within the cavity. So this allows us to actually now control the air value of the wall or the roof or any actually system that's insulated. And we showed in the US at least that just by the fact that we can adjust the thermal insulation from high to low, meaning two-step control, what we say, we can reduce a lot of energy consumption, especially in mild climate, like in San Francisco here, where we could reduce by up to 45% the heating and the cooling need of a residential home, of US home, typical home. So these lines gives you the contour of the percent reductions of heating and cooling energy use, okay? Because, so the point of this work is that it's not always good to actually insulate the building. In some season, in some days, it's actually better to let the heat go out rather than keep it inside. So this is the crux of this whole idea, what we call dynamic insulation. In a similar way, the shading. As you know, in many countries, especially in North Africa, like Morocco, we use shading of a window to reduce the cooling energy and in a way, reducing the solar heat gain. That's in a actually cold climate, like where I am in Boulder, Colorado, is actually not a good idea to have shading because we want solar radiation to get into the house, for instance, to reduce the heating load. And that's true also for any home anywhere where there is a change of season, summer versus winter. It's a good idea to have shade during the summer, but it's not a good idea to have shade during the winter. So you want something that it's dynamic, that actually a change in terms of the position. And that's the idea of what we call dynamic shading in general. On top of that, we can use shade to actually place PV. So the movement or the dynamic shading becomes a dynamic PV panel itself. And that's what we call PV integrated dynamic overhang. For instance, in this case, we're working on testing different prototype. This is an example of a prototype that allow you to, again, change the positions. It depends on both the solar radiation intake as well as the cooling load of the building. So there is two functions that the shade can actually provide. We did some analysis and we showed just by using these PV integrated dynamic overhang in a typical, at least apartment unit in the US, we could make most of the, at least in certain climate like in San Francisco, we can eliminate totally all the energy needs, okay? Because the PV itself generate power, electricity, and the overhang reduce the heating and the cooling load. So it has two functions. So as you could see here in, as I said, San Francisco, we can eliminate and we can be net zero energy, even positive energy housing unit just by using this particular technology. This PV integrated dynamic overhang can allow us also to flexibility to increase the size of the window because it's not a penalty now to have large window. It's actually a positive because now you have a PV integrated overhang with it. So the higher actually the window, the higher is the PV panel that you can integrate it with. So this technology is relatively low cost and could improve in both the energy efficiency as well as the renewable energy implementation in building. In terms of heating and cooling, there is also many technology that are basically passive that we can introduce in a building. including use earth tubes, evaporative cooling, natural ventilation, ventilated slab, thermoactive foundations, as well as using variable refrigerant flow. So these are technology that we work on or working on. I'll mention only the thermoactive foundation as an example of the technology. This has actually been implemented already the last 20 years in Europe as well as Asia. This is an example of Dubai building where this technology is installed. It's basically ground source heat pump loop that it installed in the foundation itself. So that saves the cost of the digging the well, which actually one of the highest cost related to the ground source heat pump with vertical well, borehole. The potential, like any ground source heat pump, of saving is significant. We did some analysis for thermoactive foundations. Some call it also thermopile technology. We showed that it saves both heating and cooling in almost all the climate in the US, including the cold, like in Denver, as well as hot, like Phoenix, by saving almost up to 50% of heating or cooling load. So ground source heat pump is another technology that we recommend, especially if you want to have what we call electrified building, meaning a building that uses only electricity for heating and cooling. Smart thermostat, everyone knows what is smart thermostat. It's adapt to your occupancy pattern as well as your needs for comfort over the days. After a few days, you could actually learn at least the thermostat will learn what you need, what you want. We did some analysis, at least for the case of Saudi Arabia, to assess what's the potential saving when every home in Saudi Arabia actually have a thermostat. As you may know, in Saudi Arabia, homes usually have many air conditioning units, up to 10 air conditioning units, one per room, typically. So, and air conditioning is one of the most important end use of a residential building, as well as any building in Saudi Arabia. 60% of all the energy used by residential building in Saudi Arabia is actually related to air conditioning, to cooling. So using smart thermostat makes sense. And that's why there is a pilot to actually try to implement this. The potential saving when you use a smart thermostat is huge. You could save 30% of that cooling energy use, which represent in the US about 30 or so tetrawatt hours. So it's a significant amount of energy. All this leads us to the fact that we need tools to now design as well as operate a building. Unfortunately, tools are fragmented in the building industry, especially related to how to design energy efficient building as well as smart and well-controlled building. Currently, when we design building, we don't think about the control. The control comes after. The paradigm needs to change. We need to be able to design and control in the same time using some tool. Obviously, that's what's lacking in terms of the current industry is simple to use tool to help design what we call smart building. Obviously, there is tools to do what we call optimization analysis, as well design net zero energy building like VOPT, this tool developed by our students as well, NREL, that allow to optimize different technology to determine what is the best to either reduce the energy consumption or to design what we call net zero energy. And we apply this concept, what we call sequence search technique. Basically, it's an optimization technique that allow quickly to find a solution, optimum solutions it involved a lot of detailed simulation tool as well as optimization and interaction between the different algorithms. So that's for a new building. For existing building, we also need some automated tool to do what we call energy auditing. And we developed a tool that does the calibration of the energy model automatically using basically, again, some optimization technique as well as artificial intelligence algorithm. Some applications. So we applied these type of analysis to design net zero energy, either building or community in almost everywhere in the world. This is an example in Shanghai where they want to actually design their district, business district to be net zero energy carbon. So you use the same idea of optimization to first focus on energy efficiency and then the on-site power generation, mostly PV, to determine what is the best option. In many cases, and that's true in many locations, energy efficiency is still the most cost-effective compared to on-site generation, even though the cost of PV is going down, that in maybe a few years, actually it makes more sense in many cases to actually install PV than to try to reduce the energy consumptions. But in general, that's why this point is higher than the baseline in terms of the life cycle cost, meaning it's not cost effective compared to the optimal design. And you see that in many countries, actually. So this is an example of the application of net zero energy design for office building in France, in many locations in France. With energy efficiency, you could actually reduce, compared to the current standard, your energy consumption by 40%, at least in Paris, for an office building. And then the rest, to get to net zero energy, meaning 100% reduction of energy consumption, you need a PV on the top of the roof. And that's true for many, as I said, location as well. Doesn't matter what the life cycle you consider, 10 years, 20 years, or 30 years. In Nigeria, it's a different problem when we design homes, is actually the insulation is not always good, as I mentioned earlier, in Nigeria because of the climate, relatively mild climate. So you need to focus mostly on the lighting as well as the cooling system efficiency, as well as the set point. So these give you some idea what technology you need to focus on to reduce the energy consumption of a residential home, a villa in this case, in Nigeria. But the same idea, with energy efficiency, the current, at least technology, we could reduce cost effectively the energy consumption by about 40%. And the rest, we can use PV to actually get to net zero energy. In Mexico, close to home in Brazil, I guess, Alcedo, we did actually similar analysis in Brazil, but this is for Mexico, for residential building in Salamanca, Mexico, where we applied, as I said, net zero energy design for a residential building here. And we found that cost effectively, you can reduce energy use by 35%. And with the PV, you can get 100%. We did a very wide region in the MENA region in terms of what's the potential in terms of energy saving for a residential building. And we found it actually could be significant, up to 50%, especially in a hot climate in the desert, as well in both the Saudi Arabia desert, as well as Algeria desert. As well as other in the coastal area, you could get even 35% reusing cost effectively technology that exists, mostly high efficiency air conditioning as well as LED lighting. At the community level now, we could use a similar analysis, but we typically focus on carbon reductions when we do these designs rather than just energy reductions. There's different tools. In this case, Homer, for instance, is used to design the generation system to reduce the carbon reductions. So for an entire community in El Kubar here in Saudi Arabia, we looked at, for instance, in this case, the wind turbine, PV, as well as a battery and a converter. This is a grid-connected system. We could see that optimally, cost-effectively, we can reduce carbon emission. It depends on, obviously, the cost here, but typically around 40 to 50%. Cost effectively, we can reduce the carbon emission of entire residential community. Similar for island, this is a project we did in Masariya Island in Oman, where actually the government needs to ship fuel for a generator to generate electricity for the homes and people living in the island. The cost for the government is about almost 27 cents, $0.27 per kilowatt hour. That's very high. If they use, and we showed in this study, renewable energy, wind as well as PV, that could reduce that energy cost by almost 50%. And now it will be only less than 15 cents per kilowatt hour, using renewable energy sources, among other things. Close to home in Morocco, actually, recently with Professor Lohi Amin, we did some analysis to try to, for a rural community in Fas Meknes region, to reduce the energy consumption of the homes, as well as obviously meet the energy need for standalone, meaning it's not grid connected community, with biogas generator, because it's a rural, so they have a lot of potential fuel for the biogas generator, as well as PV. We showed that we could meet all the needs of this community at a cost of about 11 cents per kilowatt hour, which is competitive, at least in terms of the grid cost these days in the region. So as you could see, there's a lot of application related to energy design, as well as the control of building. Before I conclude my presentation, I want to mention a few things, including the fact that there is a lot of potential now to design and operate smart, grid interactive, energy efficient, and resilient building, but we need multidisciplinary knowledge as well as team of designer to do that, including people interested in the control, as well as obviously design of different system, lighting system, electrical system, mechanical system, structural systems. So that's why building our complex, I always say, it's not easy to design a high performance building, because you have to have many disciplines and knowledge. And then obviously there is still a lot to do in terms of research and development of new technology that make the load of building dynamically changeable. You could actually change the load as you want, and as obviously related to the fact that the power now, it changes over the day as well as over the season, if we are going to rely on renewable power like PV as well as wind. So the future, or at least my visions, and this is where the center, I'll mention quickly, focus on, is really developing this, what I call smart and dynamic technology for buildings. So that involve many knowledge, including obviously material science, as well as energy and renewable science, as well as optimization controls. So we're working on, as I mentioned, phase change material integration with building, because it allows to shift the load, as I mentioned, related to the gap technology. That's the hard part left. How we can store energy and use it later. That's the most expensive and challenging technology actually in building these days. We could do almost everything else. We can control how systems operate. We can reduce the energy use of HVAC, of lighting. Actually, LED now does not require a lot of electricity to operate, but storing energy remain the big challenge, at least for the building and for the energy community in general. And that's why NSF funded recently, just a few months ago, a center at actually CU, University of Colorado, as well as City College of New York, to work on what we call smart energy technology. So this center is a national in the US, but we, at least the center, allow NSF fund international collaboration. So if you're interested in collaboration in the center, there is funding available to bring people here if they're interested in what we call smart, intelligent technology specific to the building. When we say building, is obviously not just individual building, but community and urban center. That's our focus. And our goal is to try to, as I said, have resilient, efficient, intelligent building. And that's many technology, including in the building envelope, the lighting system, the equipment, the HVAC, and involve obviously some control system, artificial intelligence mainly, as well as a cybersecurity issue that we have to deal with. And in terms of power, we have to integrate obviously renewable power. With this, all the content, or at least of this presentation, can be found in either a textbook I wrote or some paper I wrote. I mentioned at the bottom usually the reference, the source of the slide. So if you're interested, you can look at these textbooks related to electrical as well as energy efficiency in general. Finally, and if some of you are interested in publishing some of the papers that are presenting in this conference, I mentioned at least a journal that I'm co-editing, the Journal of Engineering for Sustainable Building and City, and SME journal. So please let me know if you're interested in publishing your paper. We'll go through the process. With this, I'll give a shout to our students since they won, at least this year, as they did in the first two competitions, solid decathlon competitions for a house that they designed and constructed in Colorado here. You could see the snow already in the house. With this, I'll let, if there's any questions, I'll be happy to answer. Thank you for your attention.
Thank you. Thank you very much, Professor Prati. We are behind the schedule, but I think that we can catch up later in the time available for discussions. And I'm checking here the questions. Most of the questions I think that you have already answered during your presentation, but there is one here that I find interesting, and it's from Tariq Luchami, and says that what is your vision for smart buildings in the world after the corona pandemic? And if I could add to this, how do you see the integration of sensors for health conditions in the smart building, and how this
that's
can
a very
act
good
for the sake of the inhabitants?
Yeah, that's a very good question, and actually a challenge that we are tackling in terms of the wealth and the health of occupants within the building. So that's obviously one parameter among many, what we call constraint when we design and operate building. So there is still a study to come up with the best system as well as the operation, but natural ventilation system, as I mentioned, related to the dynamic HVAC system, natural ventilation is one of them. So we could passively actually both heat and cool building using natural ventilations. But in the same time, the natural ventilation will provide better health conditions and indoor air quality within the building. So, and some of the study that you may heard about, the impact of mechanical air conditioning in transmitting COVID virus, for instance. That's a challenge in terms of designing and looking at what's the best air velocity and placement of the air supply of HVAC system in general, meaning how we design HVAC system will affect the well-being of occupants. So that's in a way another challenge that we have to meet in terms of designing future building. We should not just focus on energy only, but also on the occupant themselves. And actually that's the most challenging criteria to design, the thermal comfort as well as the indoor air quality.
Right. Okay. Well, so thank you very much again, Professor Rarty. I think that it's about time to move up to the next presentation.
Thank you very much.
Sorry, Professor Orlando. Can I ask a quick question?
Yeah, of course,
very quick question.
Of course. Please go ahead.
Yeah, thank you. Just a question about the dynamic insulation. What about energy saving benefit versus the cost, both investment and operation cost? This is the first question. And the second one, is there any real building that was insulated using this dynamic insulation louvers?
Yeah, that's a very good question. So obviously, this is a new technology that we are exploring. The cost we showed, and we did some analysis, that even if you increase the cost of that system by relative to conventional insulation by a factor of 5, it's still cost effective. We are actually installing this system in a roof of what I call mobile home to test the performance in a real building, to answer your question. So this is relatively new technology, but it is getting a lot of attention, at least here in the US.
Okay, where is this building, this prototype with the roof insulated dynamically?
Yeah, so there is, as I said, a mobile home where we use this system. It can be a panel. It's actually a panel that you can install ready to go. You don't need to install it on site. Okay. You have a panel that you install in the ceiling. In the US, usually there is an attic, and then you can just put this panel in the attic. Okay. And you remotely operate it, meaning you have a controller that decide when to open and close the insulation.
Okay, thank you.
Okay, thank you. Thank you very much.
Thank you.
And once again, thank you very much, Professor Crutty, for the very nice presentation.
Thank you very much. Bye-bye.
Okay, thank you. Thank you. So we now move to the second keynote lecture of the session. I see Professor Humberto Berardi is here. The title of his lecture is The Future of the Built Environment in Face of Climate Change and Global Challenges. Professor Berardi is a Canada Research Chair in Building Science. He's a full professor and director of the BTOP Center at the Ryerson University in Toronto. His main research interests are related to the study of innovative solutions and new materials for improving the performance within the built environment. Professor Berard has an extensive publication record, including 130 peer-reviewed journals, 130 international conference papers, and 5 books. Dr. Berard's publications have received 10,000 citations. He has a body of funded research comprising over 2.5 million in government and private sector funds. So please, Professor Berard, you have the screen. Thank you. Thank you very much. Thank you.
Can you hear me, Alcio?
Yes, we can hear you. And we can also see your transparency.
Perfect. Thanks so much, Alcio, for the nice introduction. Thanks to Professor Crutty for having preparing me the floor for my following up keynote. And really thanks to all the participants. I see we have more than 200 people connected. So I hope I will match your expectation for today's talk. That basically, it's looking a bit on some aspects that in the BTOP Center in Canada we have been working on over the last 5 to 6 years. So the topic is the future of the built environment in the face of climate changes and global challenges. And I'm going to present you a lot of work done for Canada, but with a clear understanding that the similar work could have been done somewhere else. And I hope I inspired through this talk what you can ideally do also in other contexts. Let me give you a bit of the background of this talk by showing you what I have downloaded this morning for the current situation of Toronto built environment. For those of you that have never been in Toronto, Ontario, Canada, this is a city that is basically undergoing and has been undergoing over the last couple of decades a significant boom of residential construction. Today, we have over 220 cranes in operation. We have over 100 buildings, more than 40 floors under construction. And we have over 300 new buildings already proposed with the construction process starting soon in the next few months. So it's a lot of construction, as you can probably see from this 3D map, where what typically used to be a low-rise construction housing in the typical North American style is now being substituted by these huge towers. So the question of the center I direct has been, what really is happening in Toronto? The center is a new center that involves basically work on testing the efficiency of the construction we do. So we tend to do a lot of work on the monitoring of constructions that are occurring or will occur. And we are trying to understand what we can do in order to make sure we get an understanding of the future challenge that these buildings may face. That's why you see the acronym TOP, TOP, for testing, operation, and performance. We are critically looking at the challenge that may involve a new scenario where these buildings will have to perform as intended. And we know this is probably often not the case. And one of the reasons why that's not the case is because we know that these construction are going to be exposed to an environment that is not the one we sometimes anticipate. So the city is booming. You can see here in the animation of the construction happening from 2000 to 2015. So this is already history, and you see how the city changes. And all these buildings are basically generating a significant interbuilding effects, are basically enhancing what it is the urban island effect in the city of Toronto, which basically adds on the climate change we all are expecting. So my talk today is what really can buildings do to help us meeting the SDG. And you probably are aware of these 17 criteria that we have commonly tried to solve in the COP 2006 that closed last week in Glasgow, represented one of those milestone opportunities to try to address this. Now, a building in the way in which Munson prepared us with dynamic insulation, with phase change material, with a bunch of smart technologies, address a lot of different SDG. Sometimes we tend to put a lot of attention to the SDG 11 and 12 for sustainable cities and communities and responsible use and consumption of resources. But the reality is that buildings are key players of a lot of other goals. They are key players if we want to have an environment in which the well-being gets promoted, is basically a critical piece, the built environment, when we speak about the future infrastructure, cheaper infrastructure, fuel poverties, and so on and so forth. So there are a lot of different basically scenarios. And these trends will have to be addressed all together. But while Professor Carty showed us some of the options, what I'm going to focus today are not necessarily some of these technology represented in the slide you see here, but I'm going to focus on the impact that the climate can play for the functionality of these buildings. Now, I don't want to spend the half an hour given to me to discuss too much about climate, but the reality is that we are well aware that for whatever reason, sometimes human related, partially, fully human related, but we know that we are expecting a change in the climate conditions our building will be exposed to. And we know that this change keeps going up. I took this map because it's showing Morocco where the IRSEC is, virtually currently going. And you see that there is an expectation for a significant drastic change of the climate, even on Morocco. But the same thing typically occurs in Canada too. So when Professor Carty said that in the US and in many countries, we have been seeing a significant attention for net zero energy buildings, my understanding and question is, but in which climate we want to have these zero energy buildings? In Europe, for example, since last year, or more or less since this year, a lot of regulations have been suspended. We know that with the new energy performance building directive, the recast of the EPBD, they have been putting a significant attention for energy efficiency. So the buildings from a reference building consumes less, and then with some local production of renewable energy, basically compensate that lower demand in order to basically stay on this net zero line, the line that basically differentiate a traditional building with a building that basically consumes resources from the ideal of a positive energy building, so a building that basically produces more energy that it needs. We want to stay as close as possible on this line, and probably we want to stay as close as possible to zero in order to also save resources. We don't want necessarily to have a building that demands a lot and produces a lot. We want a building that passively can produce a little, locally produce a little. But the reality is that this kind of balancing that in Toronto has led my center to coordinate the activity of how to design a zero emission scenario for the built environment. We'll have to face also the challenge of the future conditions. And one of these challenges, for example, the fact that our grids are not infinitive, so we don't want to produce a lot and require a lot because our grids are not necessarily available for that. But also we need to do this knowing that the forecasted weather conditions is not what we've been used to. Clearly, we know that the buildings is 40% of the energy demand, 40% of the resources. Numbers could fluctuate country by country, but this is a significant, already well-known data. And we know that I took this slide just to give you a bit of breakdown of the demand of different cities across the United States. But you basically said that the buildings is a huge portion, and when it comes to the city levels, it's even a bigger portion, as cities are these pieces of the equation that mainly consumes energy all the time. And I want to take this snapshot and put within the context of climate. Now, when it comes to climate, basically records and measurements tell us that our last 4 decades have been the warmest on record in temperature. So the Earth temperature has been basically raising constantly over the last 4 decades. Typically, we get already around 1 degree more than we had a couple of centuries ago. And we probably are well aware of the fact that the goal of the COP was to try to limit this raise to 1.5 degrees Celsius, and some other forecasts and discussions were around 2 degrees Celsius. But the reality is that this 1.51 is not necessarily well represented of what can happen climate by climate, condition by condition. And I'm going to use Canada to show how this 1.5 degrees Celsius means for the country where I speak from. Now, in Canada, the government has been spending a lot of resources to try to, do downscale models of the RCP scenarios, the scenarios that basically represent the current path versus other mitigation scenario. And there you get a sense of how the climate has already changed across the different seasons. What basically has been happening is that we have a lot of regions of our country, especially Alberta, especially Saskatchewan, especially Minnesota, but the raise has been already in the range of 3 to 4 degrees Celsius. And that kind of heat means a lot of things. It means fewer heating degree days, which for a heating dominated climate can be good, but also means a lot of cooling degrees days more than expected, which really means a lot of building will have to take a substantial approach to start including cooling systems in building that historically were not provided with that. That clearly means a lot of new machines, a lot of new investment, and a lot of new attention to the cooling side of our buildings. And this is not just happening for Canada, it's happening globally. For example, connecting again to Professor Curti, the ASHRAE climate zone, I'm in the panel of the standard that promotes 169, the climate zone classification for ASHRAE. We have been seeing a significant over the years change in this map, and a lot of zones that used to be in one zone now are basically moving up or moving down to lower numbers of the zones as they move to zones that are warmer. Just to give you an example, Toronto used to be in zone number 7 a century ago. If we take the records of a century ago, it's currently in zone number 6. And but it's in zone number 6 because we still take basically the records from the 90s. But if we were taking only records of new century, Toronto will already hand in zone number 5. And the forecast is that in the next few years, we will have Toronto constantly within 18 degree days below 3,000. So constantly within a range. That basically means that Toronto will be at zone 4, the current zone of New York City, just to give you an example. So what is the current challenge we are facing? The challenge is that the buildings, needs to be more and more these days built thinking about the future scenario. We need to start using future climate files to promote efficiency, performance, and resiliency of the buildings we use. We need to start making sure that in the built environment, we use future weather files much more than we have done in the past. And I'm saying this because we have good understanding from different sciences, geography, biology, climatologies, the future weather files, and we need to start understanding the impact of that. Whatever is the cause could be, the emissions of these or that gases, could be an anthropogenic cause, or could be another kind of source. But we know it's happened. We know that the concentration pathway basically is projecting an increase in the CO2. Different models may, kind of model differently the concentration pathway that is the toughest one, the milder one, or a kind of a more modest one. But we know that we have at least a couple of degrees Celsius increase in temperature. If we want to convert an RCP into a degrees, you probably have been sometimes looking at this kind of graph, where we get from the current path of CO2 emissions per year to what is the forecasted, and these multiple lines are the possible alternative models that we follow up, and we are unfortunately still on the red track, and probably, as Professor Kwarti anticipated, as China and India are not necessarily liking addressing these too severely, we will not necessarily be able to be too far from this. And even the United States, as many other countries, for example, Canada is currently the country globally that consumes the most for building energy demand. We have an energy use intensity that almost hits 300 kilowatt hour per square meter per year as a result of poor building standard with harsh climate. That makes actually, the possibility that we will end up following this red curve quite high if we don't address this challenge. So, together with a lot of work on building technology, I'm going to focus only at the end of this talk to some solutions. We do some good amount of work looking at how to create future weather files that are customized for buildings. So we take large global models, we do what we call it downscaling. So we do basically from a global climate model to a regional climate model, then we go down to the scale, and we generate weather files that then we use in models, or also to recreate laboratory works of this. Let me give you an example. This is the IPCC RCP 8.5 report for Canada. It's basically, the projection of the scenario where we don't do that much for Canada. And here you see January, and here you see July on the right for 2005, 15, 65, and 2017. 5. And here you see basically the change in temperature. And what that means, it means that you can anticipate that we will have significant kind of higher cooling demand in summer, and not necessarily that significant warming up in the middle of the winter, as we will be suffering much more extremes than we had in the past, with a lot of inconsistency when the temperature fluctuates, and we will not necessarily always be able to switch from heating to cooling mode with the same heat pump, but we will go back and forward as the system oscillates more dramatically. Now, if you want to get a sense of this, I strongly encourage you to go to the web file climatedata.ca. This web page is full of nice variables and gives you a lot of the kind of work we do. But the idea is to downscale a global model into something that is a local model. And then from that, we basically, once we have a data for a specific small location, as small as the GTA, the Great Toronto Area, so the range of a city, we start doing a lot of statistical analysis of this work. Now, for today, I'm going to specifically focus on the tool that are called World Weather Generation Tool and Weather Shift Tool. And I'm going to focus on the RCP 8.5. So the scenario that basically represents the most significant crucial change into the climate pattern. Now, what we tend to do in our center, we take a weather file, we take this weather file, we do statistical analysis of different pattern of the weather file, we map a city, or at least a neighbor, and then we run multiple statistical analysis of that kind of scenario. And then from having a model of a community and having multiple weather files, we generate and build statistical possible distribution of the energy demands of a given urban morphology. And then from that, we introduce optimization, and then we go back from this optimization to Pareto optimal or any other kind of smart optimization of what can be the most aggressive strategy to implement given this uncertainty in step number 2, the uncertainty of the future weather conditions. And with that, we help cities to promote more stability of the energy demand, more reliability of what will be likely the energy demand of the future, as well as support the idea of robust grids and flexible buildings. This is really goes back into what we heard about phase change materials as a solution to buffer the energy demand and promote the possibility to switch and move the timing of the demand of the energy within the building. So let me give you a bit of examples of this work. I'm going to start for a model of the city of Toronto, then I'm going to focus on models across Canada, and then I will finally give you a bit of the sense of globally. So here you see the current and future weather file represented for the city of Toronto. We have, as you probably have told you, already 80-degree days collapsing down. And to be honest with you, we have forecasted options that are also showing some risk that by 2075, we may even have less than 3,000 18-degree days. So here you see some different possible weather pattern that can occur in Toronto. Now, the difference between these four kind of conditions are related to what is the starting point, what is the current weather file we use. The current weather file is the weather that we used to have in the 90s, so it's the one that we had over the last few years, or it's the one that we had in the new century. But basically with that, we build this kind of scenario of the weather in the years to come, and we do models of different topology, different buildings. So here, for example, you see for high-rise apartments, mid-rise apartments, hospital, large hotel, as well as healthcare, fast food, restaurants, and retail stores. So 8 among the most common typology for commercial buildings as well as residential buildings in Toronto, what can be the heating and cooling demand. So respectively, when you see the dot that is filled is the current one. When you see the one that is basically empty is the forecasted one. And then you see the heating and cooling demand change. As expected, the heating demand and the cooling demand basically will both be affected by the change in the weather pattern. And if we want to quantify this kind of change, typology by typology, let's look for an example to this summary of the kind of analysis we have been performing for Toronto. So the heating demand basically reduces, so it's expected to reduce between 15 and 20%. And the cooling demand is expected to increase by anything small as 15, 20% for hospitals or any other topology that doesn't rely necessarily too much just on heating and cooling. But it will be also increasing, much more significant for places like warehouse, like restaurants, and even in apartments. We are expecting an increase in cooling that can be at least 30, but more likely in the range of 40, 50% of the energy demand. Now, what can we do with that? So we've been starting working on what climate change will mean for the well-being of people within buildings. And we've been starting looking at the set point temperature and different climate models for people preference. Now, just to start in scaling up, here you see the results for the work in Quebec City, so in a zone that is particularly cold of Canada, in Toronto, and in Vancouver, which is more or less the large city with the mildest climate. In all these scenarios, you can see monthly the different future weather files in 2000, basically 60, 70, are expecting an increasing temperature that can go from 5 degrees in the range of Quebec City to something around 4 in the range of Toronto to something in the range of 3 in the case of Vancouver. And you can also see from the different colors that this kind of change is dynamically not fixed, but changes monthly by monthly. So with that, we have been not only doing models of entire cities on average. So here you see the results for Quebec, Toronto, and Vancouver with a change that is from 20 to 30 degrees in cooling, and then from 10 to 15 kilowatt hour per square meter per year on average across the city in the case of heating. But we also have started looking at how different weather conditions and set point can change and affect the energy use intensity. Now, while we do this kind is putting buildings in the middle of a new weather file artificially built on modeling, we also need to understand what occurs at the city scale. Now, the city scale for Toronto, for example, with all those towers is expected by a significant increase due to the urban heat island effect. Here you see a space temperature photograph, instantaneously recorded. And you can see the difference between the built environment, the lake as a huge thermal storage place, and the green belt, the green area of forestry that we have around Toronto. And here you get the sense of kind of work that we have been doing. We have been monitoring buildings for comparing roof surface temperature and radiant heat coming out from this surface in the case of buildings that are in detached areas, in the case of buildings that are in mid-rise areas, and in the case of buildings that are in high-rise constructions. Now, in terms of roof surface temperature, basically what has been recorded is a change that can be quite significant once we start playing into account the urban heat island effect. And that significance can be even of 10 degrees Celsius during peak time in the daytime period. So the urban heat island effect basically generates a couple of degrees in air temperature, but over 10 degrees in the overall surface temperature of the warmest surfaces, which are clearly the roof surfaces in the middle of the day. And that really has been spending and expanding our research on mitigation strategy. What can we do in order to make sure that we don't necessarily underestimate the impact of climate files? We probably can memorize the bad images of the severe heat waves that occurred in Vancouver this summer, with repetitive days over 40 degrees Celsius and several morbidity and mortality rates coming up in cities for this increased climate impact of the DUCE scenario. So we do a lot of mesoscale modeling and microscale modeling. Just to give you the sense of the difference, this is a weather research forecast. This is basically a microscale model. In the first one, we basically stretch the weather file from a location. In the other one, we basically fix the weather at the surrounding, and we simply look at the wind fluidodynamically changing the temperature across a given geometrical domain. So two scenarios and two modeling techniques that help us understanding what spot within the cities are at risk of suffering the majority of the heat wave. Now with that, we help municipalities to address this challenge. And some of the solutions, I've been already covering in the previous talk. We've been working quite a lot since 2010 on the latent heat thermal energy storage, where this phase change material basically becomes your battery for buffering the thermal demand and move when it doesn't really cost you a lot. Now, more or less what you do for a nice bucket that you put in a glass of water to basically cool down instantaneously, thanks to the huge density that is associated with a phase change. Now, historically, we worked on passive thermal energy storage. 10 years ago, I was a faculty member in Boston. This is the Solar Decathlon house, just going back to the Solar Decathlon that we built for the tongue construction. And it had concrete PCMs on the floor to buffering the solar radiation arriving from the roof. But more recently, we have been working on coupling thermal energy storage with air conditioning systems. So the work has been more or less moving towards the air conditioning systems storage more than the passive building storage. Reason being is that this technique is definitely highly promising, but also quite expensive. As you put the low density phase change material, and you tend to put microencapsulated, highly expensive in terms of cost and quality phase change materials, and we're trying to actually now lower the price of these thermal storage batteries. We also have a significant expertise with a lot of studies and some patents on super-insulating materials. We have done multiple patents on both ambient pressure drying hydrogels, as well as different technologies for sealing vacuum insulating panels. So the idea is that we now have the opportunity to make sure that we have materials with thermal conductivity below 0.01 watt meter Kelvin, so thermal conductivity below 10 milliwatt per meter Kelvin, and we can do at a price that is already comparable to the price of more traditional fibrous material and mineral insulating materials. The idea behind this approach is that you may want to basically lower the possibility of heat transfer by convection as well as conduction with the structure of the material by recreating this 3D porous, empty porous structure of aerogel. Now, typically this gets done in the most majority of studies by doing supercritical drying process. So you basically get ready in the gel of the liquid portion by drying at high pressure, and this basically creates a lot of high cost. And we have been developing different approaches to do this drying at ambient pressure. So this drying, where the gel needs to basically be evacuated of the liquid component to generate an aerogel, gets done without necessarily passing by a supercritical conditions. And by not doing that, we keep the price to be low. And then last but not least, we have been trying to do a lot of work on smart coatings. What I mean by that are selected coatings that are retroreflective. So coatings that are capable of re-reflecting the radiation from the sun not according to the Lambert's law, but in the same angle of incidence. So the energy arrives, gets reflected within the same angle back to the sky, or thermochromic coating. So we have been working on transparent thermochromic coatings for windows as well as opaque. So, colored thermochromic coating for opaque walls. So in conclusion, climate change is already a phenomenon that is evident, it's significant, and may need to be more deeply considered within the built environment. We know that this is affecting the heating demand of buildings. In Canada, overall will lower quite significantly the heating demand by even 30%. So generally some saving, but also some challenging with unfortunately increase in the cooling demand for buildings that often do not even have a cooling system. So a lot of discomfort are challenging. And we have solutions to do that, but in order to do that, we need to start paying more attention to higher insulation rates, higher thermal mass and thermal capacity, and more or less better control of the radiation arriving to our buildings. In conclusion, I want to thank a bit of the students that do a lot of the work in the center. I have the honor and pleasure to direct, as well as the funding agencies that have been supporting a lot of the work that is at the base of what you heard today. So thanks for your attention, and I'm more than happy for kind of answering any possible question or curiosity.
Thank you. Thank you very much, Professor Berardi, for the very nice presentation, very comprehensive. And there are, you can see here, 2 questions. And the first one is from Dr. Zaid Romani. Thank you very much for this presentation. What is the best optimal scenario concerning the future climate conditions to be taken into account in the building thermal simulations? This is a very interesting question, because from all those scenarios, which one we should work like for planning the construction of new buildings or even retrofitting?
I should say that none of them, or otherwise all of them, because I think what needs to be understood is that any modeling and a design, a project is a modeling exercise. Unfortunately, gets perceived by designers as a deterministic process. But in my life, I tend to basically be more and more aware of the fact that it's a probabilistic, modeling. We pretend to know how many people will occupy the buildings, but we have no really clue what that actually means at the end. We tend to assign to the zones different functions, but they may change. So I'm really skeptical when my students give me the energy use intensity projected for a building. And I actually often ask the students in any course I teach to give me a range of possible energy use intensity that may occur. So I think actually we need to reestablish what a design is to do. It's a forecast, and the weather is one of those factors that may influence the forecast. So I think we need to at least try to do multiple simulations, also because it doesn't take that much time these days. If you have the weather file available and you have a building energy model, running again the simulation with a more critical condition, warmer or colder, gives you a bit of sense of how sensitive your building becomes to the climatic situation that may occur. And I think that's really what resiliency means at the end of the day. It's basically be ready to possible alternative scenarios. Otherwise, you have a perfect solution for a scenario that may never work. And that's also why I think the phase change materials, although being a nice topic, becomes challenging if it gets only used as a passive strategy with the envelope, because the envelope will be not smart necessarily that much to be adjusted, versus when it gets into the connection and collaboration with the mechanical systems, you can adjust the conditions more easily by changing the flow, by changing the temperature set points. So the reality is that my answer is multiple ones. I'm really skeptical to pretend to give you one single file, because at the end of the day, I don't think there is one single file, as a building will live 50 years and will be exposed to 50 different weather conditions year after year. So, I mean, it's not even just getting the results in 2100 and modeling with that. We need to be ready to know more or less what can occur in 2030, in 2040, in 2050, and be ready to this continuous update.
Okay, thank you. The other questions was actually very much related to this previous one. And I'd like to ask you about these. What is the life cycle of these PCM materials that you have been using? Construction, okay. If it presents hysteresis or something like this.
Yeah,
especially those containing nanoparticles.
Yeah, so this is a good question. And, you know, again, it's one of those questions that have multiple answers. So in inorganic PCMs, easily you get around 2,000 to 3,000 cycles with a reduction basically within 10%. And, you know, 3,000 cycles means that if the PCMs is supposed to be charging, discharging daily means 10 years. Now means 3,000 times of charging and discharging, you know, 300 days a year means 10 years. But the reality is that this is true in a lab condition. And when you bring the scenario in an outdoor condition with a lot of multiple alternative situations that may impact the lighting of the building and the exposure, I mean, we don't have that clue of how things such as UV, for example, can deteriorate the polymer that surrounds the PCMs, and by deterioration of the shell that surrounds the PCM may impact the life expectation of these materials, or at least their fluctuation in terms of storage. Hysteresis is one problem, subcooling is another problem, and it tends to be accentuated with the time. So the control becomes more challenging by the fact that not necessarily buildings cools and melts and freeze at the same temperature instantaneously, because there's this shift between these two, but also they tend to shift with the time as the material ages. So, I mean, I would say 2,000 to 3,000 cycles, but my answer could be inaccurate for other kind of materials.
Okay. Thank you. Thank you. I ask if there are other questions, especially from the panelists. Well, so in this case, I would like to thank again the two keynote lecturers from this first session of our workshop number 4. Professor Krarty and Professor Berardi, thank you very much for the very nice presentations. And I guess that we should now move on to the 5-minute presentations in this workshop. As I understand, the recorded presentations will be broadcast, and there will be in the first session 3 presentations, papers 122, paper 93, and paper 163. And then we have time for some discussions on these papers, and then we continue again for the second session. So we already have there on the first paper 122. Please go ahead. Thank you.
Hello to everyone. My name is Sajjan Pokhriyal. I am a student at the University of British Columbia in Vancouver, Canada. The topic of my today's presentation is a sustainable heating solution for multifamily residential buildings in cold climates. It is a case study of a Canadian building for which we propose a green heating solution. Now, without further ado, I would like to take you to the proposed construction site. Okay, this is the satellite image of the location, and the total area of the building is 73,500 square meters, of which 35,000 is available for solar system. There will be 2 buildings, building A and building B, and totaling of 826 apartment units. There is a municipal sewage line system that runs 40 meters beneath the site. So the idea is to utilize the low-grade heat from this sewage line to meet the thermal demand of the building with the aid of heat pumps, right? But as we all know that heat pumps can be effectively used to improve the quality of heat from sewage line, but at the same time the compressor of the heat pump requires electricity to function. So a solar PV system with lithium-ion battery storage is proposed to supply the electricity to the heat pumps to make the building 100% green. Okay, in this slide I discuss about the techniques that we used to model the system. There are basically four components. The first one is the estimation of the building thermal demand. Building thermal load accounts for the energy needed to heat the fresh air and heat losses from the building from walls, windows, doors, roofs, ceilings and floors, and accordingly it also accounts for the hot water consumption in the building. The second one is the design of the sewage heat recovery system, which basically consists of designing the heat pumps and designing the water pumps. The heat pumps COP, or the coefficient of performance, is calculated based on the evaporator temperature and condenser temperature, while the pumping power is designed or calculated based on the desired sewage flow rate to run the system. The third component is the solar PV and the battery system. It is designed based on the availability of irradiation at that location and keeping in mind the worst case scenario, which is the month of December, because December has the lowest irradiation availability and the maximum power is needed to lift the water to the surface in the month of December as well. And finally, economic evaluations are performed, which is basically calculating the capital cost, cost of energy, energy savings per year, and the payback period. Now I would like to take you to the results section. The first result is the thermal demand of the building. The picture represents the building monthly heat demand. The annual heat demand is 20 terajoule, and the highest heat demand is for the fresh air heating, which is followed by the envelope heat loss and followed by the hot water demand of the building. The month of January has the highest heat demand, while the month of July has the lowest. And these are the results for sewage system design. This diagram depicts the total number of heat pumps required and their corresponding COPs for different months. And the heat pump that is used in this analysis has the rated power of 95 kilowatts, and the COP of the heat pump varies between 3.6 and 6.4 depending on the temperature of the sewage line. Similarly, the total number of heat pumps in use ranges between 1 to 5, again depending on the month of the year. And the figure on the right represents the amount of electricity that is required to run the system. The compressor consumes the majority of the electricity, while the water pump also consumes some power. Similarly, this slide presents the results of solar power generation and the economic findings. The figure to the right side of the screen depicts the energy generated from the system for each of the months, because the solar system was designed for the worst case scenario, which is the month of December. Extra energy is generated in all months other than December, and this extra power and energy will be used to power other electrical appliances throughout the building. And also the main economic findings include the proposed system cost estimation, energy savings, payback period, and according to the table, the system's total capex is 22 million, while the annual savings is 0.8 million. As a result, the system's payback period is 26 years. So going to the conclusion, this study proposes a renewable heating solution for a residential building with 826 apartments. The sewage heat recovery system and solar PV system are primary energy sources. The total number of heat pumps required is 5, with COPs ranging in between 3.6 to 6.4. The total area of PV modules will be 26,000 square meter, and the system payback period will be 26.6 years. Thank you so much.
you may go ahead and play the next presentation. Then we'll have the discussion sessions after the 3 presentations. Thank you.
Hello everyone, my name is Marian Tariq. I'm a researcher at School of Architecture, Planning and Design at Mohammed VI Polytechnic University. First of all, I thank you to give me the chance to participate in IRSEC'21 to present our work titled Thermal Behavior Evaluation of a Traditional Earthen Building under the climatic conditions of the Benguela City, which is a relevant topic to the energy efficiency in building. This work is a part of research activities at our university in collaboration with the Material, Energy and Acoustics team at Higher School of Technology in Surrey. Without delay, allow me to present to you the plan of my presentation. First, we will put the project in its context by a general overview, as well as the objective of the study. We will then move on to the experimental and numerical study, and then discuss the results obtained, and we will end with a conclusion. As you know, the building sector is a very energy consuming sector. At the national level, it represents almost 33% of the energy consumption. However, it represents almost 8% of the national effort of mitigation of greenhouse gases. Hence, the interest in looking for alternative solutions in order to be able to contribute to this target. The main objective of this work is to evaluate the energy performance of the earth material of the city of Benguela through the determination of the thermal properties by characterization and measurement methods. After that, perform dynamic thermal simulation on a case study. The earth on which we work is extracted from Benguela City. It went through several stages to prepare 3 samples on which the 2 methods, hot flash method in a steady state regime and differential scanning calorimetry method have been carried out. As you can see in the picture, this shows the experimental setup of the stationary hot flash method, which gives us the ability to calculate thermal conductivity through this equation below. Several tests were carried out to find an average value of the conductivity with minimal error. Subsequently, and through the method of differential calorimetry, it was possible to estimate the specific heat by determining of the additional heat flow to be supplied to the sample to reach the temperature of the empty crucible. And finally, we found the following value. To be able to switch to dynamic thermal simulation, an analysis of the city's climate is essential. It gives us an idea on the climate, which is hot semi-arid climate with a maximum temperature in summer, which can exceed 45 degrees. The studied building is a traditional Xor-type construction hypothetically located in Benguela City, unoccupied and without any other system of heating, air conditioning, and ventilation. By using Design Builder tool, the dynamic thermal simulation is carried out. The walls of the building studied were composed in such a way as to respect the traditional construction methods in the regions of Morocco by integrating the properties taken from the experimental study. The figure illustrates the results of the dynamic thermal simulation. For the question of thermal comfort, we note that the value of relative humidity remain within the comfort range. The analysis of the temperature profile for a winter period of 1 month shows that the thermal performance and the comfort conditions are improved to raise the interior temperature of the building to an average temperature of 18.72 degrees. We take the example of the month of July for the summer period, when the outside air temperatures can reach extreme values up to 45 degrees C. We note that thermal energy performances are not much improved. However, the absence of temperature fluctuations in hot waves is a good result, although the maximum under mean temperature reached 29.44 degrees C for this type of earthen construction, and average temperature is this same period is reduced to 27 degrees C. To conclude, and given the above, we can say that the measurement method have many advantages, and earthen construction in the region studied presents good results for the winter period and less improved results for the summer period. Using passive solutions of bioclimatic architecture or energy efficiency measures can make the building energy efficient at all time of the year. Traditional earthen construction is a real opportunity to face the challenge of the century, which is climate change. Thank you for your attention.
Good morning, everyone. This is Hisham Pastouri from the School of Architecture, Planning and Design of Mohammed VI Polytechnic University. Today, I'm going to present to you this paper around the upgrading rural living. It is about the agri-greenhouse concept for the agriculturist, or it is called agri-greenhouse or agri-demonstrator. This concept is conceived and implemented by Professor Hassan Ridwan, and it is a joint research with the LMD of ex-Polytechnique de Paris, namely with our collaborators, Mr. Philippe Ludrobinsky and Mr. Jordi Badousa. The agri-greenhouse or agri-demonstrator will be an implemented full-scale building for experimentation dedicated for the agriculturists, which means that it will be a rural concept, a rural example for the human establishment in the extra urban areas, and it will be implemented on the basis on many aspects. I would mention some aspects, energy efficient aspects, sustainability and resilience aspect that are the concern of any establishment in this area. So if we talk about the energy efficiency for the rural living, we will talk automatically to the commonly used classic materials in this context. I would name some of them, like the adobe limestone earthenware blocks, where these materials are abundant or are available in the area, in the rural areas of especially in the context of the region. So these materials will be energy efficient, also will serve to have a good performance in the vis-a-vis the environment. So to have a good concept that will consider many aspects, here we include also the low-tech and the high-tech and also the ICTs. These kind of upgraded technologies, so we are in the era where advanced technologies must be included in order to merge this kind of housing into the local context. So the house will have this kind of technology that will serve to manage the energy and also to manage the productivity of energy in this house. Also, some other passive techniques that are abundant in the region or in the context of Mohammed VI Polytechnic University. We have the advanced wind catcher, which is a really relevant technique that is really efficient in terms of cooling and heating or preheating or pre-cooling the air for the evacuation, for the air conditioning purposes naturally without the need of any energy. So also we will use the pebbles bed thermal storage. This pebbles bed is a technique which is really relevant for the storage of the excessive heat during summer or the cold during the winter to be used in the next season. And also we may have kind of application of this pebbles bed for the agriculture application. So to conclude, the agri demonstrator or the agri greenhouse is a concept, is an ongoing full-scale house to be implemented very soon, and it will consider the most aspects and the most techniques that will be serving to have a good implementation or a good example to be considered for any kind of agri greenhouses. So this project is financed by the Mohammed VI Polytechnic University and Total France. Thank you.
Okay, so thank very much for the three authors who have presented the papers in this session. We have about 11 minutes for discussion on those papers to catch up to the schedule. Professor Brahim Behamouk, please, you have your open phone. Would you like to make questions, comments?
Yeah,
Please,
thank you.
Ahead,
I have a couple of questions for papers ID 1 to 2. Two questions indeed. The first one is, you mentioned that in the build demand, fresh air flow rate is 0.06 CFM per square foot. What is the correspondence in terms of air change per hour per occupant? This is the first question. And the second one is about the payback period. You mentioned that it is 26.6 years in your case. Are you happy with this such high payback period? Are the occupants happy with this?
Yeah, thank you. Okay, can I speak? Can you hear me?
Yes, we can hear you. Please go ahead.
Great. Yeah, thank you so much for the questions, and these are really good questions. I think I would like to start from the second one. Are you happy with the payback period? Yeah, to be honest, like, I mean, it's not the best case scenario, but like using solar in Canada is not as good as using solar in other countries which are near to equator. But in terms of, because this is a kind of big project in terms of size with more than 800 apartments, and being considering the availability of the solar, we are okay with the payback period as a researchers, but we want to minimize it. But if you ask from the investor's point of view, it is a affordable housing project. I think that will be financed mostly by the government of Canada if it is like undertaken. Hopefully they will agree to finance it because it is a federal project. But if you ask for some private companies or private financing companies, they might not be totally interested at this. They might not be like completely interested at this point. Looking at the payback period, but the lower was the better. But as a research people, we have to speak what we see, what the data speak. So that is what we got. And regarding the first project, the CFM, did you ask what is the source of this data, or what was the question again? Can you please repeat that?
No, what the question is, what is the correspondence of this flow rate in terms of air change per hour per occupant?
Okay, air change per hour per occupant.
Yeah.
Right, this is 0.06 is the CFM cubic feet per meter per square per unit area. So I do not have the exact number in my mind, but we multiply this with the total area of the building to find the flow rate what is needed on hourly basis. Yeah, this is basically cubic feet per CFM is cubic feet per minute, right? And then we use this to I can use the calculator real quick, but I do not have the data in my mind. What will be the total flow rate in an hour? Yeah.
Okay, thank you. Okay.
Thank you.
Any other questions, please?
Thank you. Any other questions?
Can I ask another question for paper ID 93?
Yes, please go ahead. Actually, we still have 12 minutes, and
okay.
I didn't notice well the time when I mentioned 11 minutes before. We have plenty of time for discussions about these three papers. Please go ahead.
Okay, my question is, which kind of earth construction are you considering there for this building you are simulating? This is the first question. And the second question, did you check the suitability of the soil of Ben Guerir for such earth construction? Especially, did you check the granulometry of this soil? I think the author was Tariq Lamrani.
But I see here Hikam Masturi online. So can you open your microphone to answer the question?
Yes.
Oh.
Mr. Benamu, you want me to, as I am involved also in that paper?
Yes, please go ahead. Please go ahead and answer the question.
Yeah, regarding the typology of this soil, we got three types of soil in Ben Guerir, but only we have chosen the one which is more abundant in the region. So I provide these samples to Tariq Lamrani mainly for the main soil type that is more abundant, to be more considerate. But for the granular test, no, unfortunately, we couldn't have this kind of probing or testing.
Okay. Okay, thank you.
You're welcome.
Thank you. I would like also to make a question about presentation 93. I was wondering which thermal property played a fundamental role to improve the building internal conditions with this material.
Tariq Lamrani, he conducted the thermoconductivity study using the hot plan methods and other methods that was implemented in the laboratory with help of the researcher in that laboratory. So he, based on these values he made a simulation using Transys software to a building existing in Ben Guerir under the conditions of climatic Ben Guerir, and he got these results compared to the commonly used classical materials, especially used in the Ben Guerir region. So he got this result to compare the thermal performance and the energy performance of these materials, of these soil materials for the 3D construction that he implemented in Transys.
Okay, thank you.
You're welcome.
Other questions or comments to the authors of these three presentations? About paper 163, presentation 163. This was very much conceptual, the presentation. I was wondering if there are quantitative results that you could share with us regarding the agri-greenhouse concept.
Yes. This agri-greenhouse, this house will be dedicated for the extra urban housing. So it is on the basis of several models that are already existing in the ecosystem of our university, ecosystem of Ben Guerir city. We have some inspiration from the passive techniques that we got in the Villa Chercheur. This is a project that is fully implemented from the local materials of the same city. So I have in mind some results that are already implemented for this kind of housing. I would say that the local materials, namely the limestone that is called Buscura rocks, and the thermal insulation, natural thermal insulation, that is the hemp insulation as mentioned in my paper, and also the porphyry layers and so on. And these techniques are relevant to give good results that could stand up to 80% of reduction in terms of the heating and cooling loss. So it will be similar concept, and it will be fully implemented very soon in the experimental farm, which is a big farm that is dedicated for the agricultural experimentations at our university. And this house will be having this kind of other passive techniques, such as I mentioned, the solar, the air tower, and also the Perl's bed.
Okay, thank you. Thank you. Professor Benhamou, would you like to make a question? Yes, please go ahead.
Okay, a subsidiary question to paper ID 122 about the reduction of the energy consumption of these buildings. As it is what mentioned, the payback period is too high. Are you going to optimize some components in this project, especially for fresh air? I thought about, for example, heat recovery to reduce the heating demand for this fresh air. Do you have some tank? Are you still working on this project to optimize its components, especially the heat recovery?
Yeah, thank you for the question. Yeah, I would like to add a few more points regarding the payback period. Yes, the payback period is comparatively higher, but I think we should also consider the life of the project while evaluating the payback period, because I think I'm not a person with the the construction part, but I think the buildings in Canada will have a life of at least 50, 60, or even 100 years, such buildings. Mm-hmm. So considering the life, I don't think the project is too bad, but again, I said it would have been better if it was lower. And coming back to your question, are you considering the heat capturing? Yes, we are still working on the project, and we are thinking to implement the heat recovery system here in the building from the water exhaust and the hopefully some of the air as well. That would reduce the project profitability. And next issue was the pump consumption, the energy that is required by the water pump, because the sewage system that we are considering, sewage line is at the depth of 40 meters from the surface. It is not just beside the surface. So some amount of energy is lost in pumping the system. But what I can say is we are considering different options for this project. This is one of the cases that I presented, but if you give me some time, I can say more. Like, we are also considering how can we better optimize the system, not only the system, but even thinking of other energy generation and storage kind of things. Like, for example, because we have some area which is available for solar, we are thinking to implement solar thermal in terms of solar PV as well, and just use the direct heat instead of energy, or using the borehole thermal energy storage system to supply heat demand in the winter time. All these options are being considered, but Canada has a very low price of natural gas currently, so it's also making the payback period higher. But according to the NDC, nationally determined goals for, like, according to the Paris Agreement, they have to increase the cost of natural gas. I think the carbon price is being increased at the rate of $15 per some. I mean, I do not remember the exact number, but it is being increased. Like the curve is like higher in terms of cost of the natural gas, which will again bring down the payback period, or at least the comparison between the conventional resources versus the alternative resources. So yes, we are working on different possibilities to implement on this building, whether it is solar PV, solar thermal, or the sewage line. So we still have to come up with the best decision, what will be the optimal decision or the best case scenario for this project. Yeah, thank you.
Okay, thank you. Just a precision. Where it is located? I did not pay attention to this.
Oh, it's in Ontario, Canada.
Ontario in where in Toronto?
Sudbury.
Okay. Okay, thank you.
Thank you.
Okay, there is one question in the Q&A for paper 93. It says, is there any proposition for the use of passive cooling? Author of paper 93. Author of paper 93. Is there any proposition for the use of passive cooling? Well, so we have no answer. I think that in this case, we should stick to the schedule, and we move ahead to the next session of recorded presentations. We have 3 presentations, papers 145, 194, and 209. So I would like to ask the organization to play the videos one after the other, okay? And then we come back to the discussions on these 3 papers. Please go ahead. Thank you.
Hi everyone, this is Isham Basturi from the School of Architecture, Plan and Design of Mohammed VI Polytechnic University. Today I'm going to present to you this paper, which is about the design and low-cost insulating panels to enhance building thermal performance, which is a part of Sustainable Energy Chair ENSUS, with the collaboration of Moroccan collaborators, Khadija University, Coimbra University, and the CNR ITA. The low-cost panels has a general objective to lead the transition toward innovative new basic techniques and also for the refurbishment of the new buildings. It is about a new concept for low-cost panel to reinforce the envelope and to investigate the impact and the outcomes of this research, and also to serve for the local housing in Africa and in Morocco precisely. So the idea of this low-cost panel to attack or to be more pertinent for the non-finished housing, as the African continent has a lot of non-finished housing, which is an opportunity to suggest or to propose new techniques that will be sustaining or to enhance the envelope of these non-finished housing, namely that are standing out for the 65%. The non-finished housing that are the majority of the African continents, they have a really weak structure in terms of the outdoor fluctuations and outdoor climatic conditions that are in Africa, that are really harsh in Africa. So you may see here from the modeling calculations used by Transis, the walls are really weak against the outdoor conditions. Morocco is no exception from this non-finished housing in Africa. But we do have two typologies of buildings that are really weak in envelope and in the structure as well, that are not having a good inertia. I'm talking about the social housing and the triple M typologies of housing that are having this kind of weak walls calculations in terms of transmitters. So the PCM will serve as what? PCM will serve as a new technology to sustain the envelope structure, the envelope component, to have a good thermal inertia through the stabilized PCM, through the halved indoor environment quality, and also further developments like the solar cells. So it is about capitalizing and advancing research to create better informed indoor environment, taking into consideration all these or several aspects. I'm talking about sustainability and resilience to boost the sustainability and resilience of the buildings, to boost the smart identification of the case study for the buildings, to boost the energy performance, and the also new refurbishment suggestions. So from this figure, we can see clearly from the transit simulation that we conducted, the low-cost panel, which is the configuration E compared to the gypsum, compared to C, the air gap, and compared to B, the perlite insulation, has a good results in terms of the thermal performance. So we can conclude that this technique will be serving neatly for the insulation. So we have here the general aspects and the general idea of this project. It is about improving the energy efficiency, the structural integrity, the sustainability, the comfort, and the safety of the housing occupants. And of course, the outcomes of this project will be patented. We will have further publications, and also we will go for the manufacturing process, which is really important in this project. Here I would like to thank our collaborators from the MSN UM6P, from the Qadaya University of Marrakesh, and from the Coimbra University, and also from the CNR ITA from Italy. So this is the project, and we will work together to implement a real effective project. So thank you so much. I would like to thank you, and thanks everyone for
Hello everyone, welcome to the study entitled Energetic Performance Evaluation of Walls Incorporating Phase Change Material under Semi-Arid Climate of Benguiri City. My name is Salih Mustafa, and I'm a PhD student at the Green Tech Institute at Mohammed VI Polytechnic University. I'm working on thermal energy storage systems, especially on thermal storage with phase change material for the improvement of energy performance of building. During this presentation, I'm going first to introduce the context and objectives of this research, then the building description, methodology, and results obtained during this study. Finally, I'm going to finish this presentation by a conclusion. So, according to 2020 Global Status Report for Buildings and Construction, the building construction sector is considered energy intensive and is responsible for over 1/3 of global final energy consumption and nearly 30% of total direct and indirect CO2 emissions. So, it is of great interest to develop innovative technologies for thermal management of buildings. This work is related with integration of phase change material into building due to their ability to improve the thermal inertia of the building envelope. Using passive thermal energy storage with PCM in the building envelope presents an attractive solution for improving the building envelope's energy efficiency and reducing both energy consumption and CO2 emissions. As depicted in this figure, at the envelope element scale, the thermal performance of the energy system is mainly influenced by the external and internal boundary conditions and thermophysical properties of the PCM, Therefore, the main objectives of this work is to study the potential of various PCMs in reducing temperature fluctuations, as well as the energy consumption under climate of Benguiri City. Also, select the optimal PCM for semi-arid climate in Benguiri City. For these purposes, a typical building as shown in left side is selected for the present study, with floor area of 12 square meter and a height of 10 meter. It has one double sliding window and a wooden door in the south side. The construction materials are shown in the right figure, and the PCM is located on the interior surface of the building. The simulations was performed without considering unstable heat sources such as home occupation, electrical appliances, etc. with fan coil unit as IHVAC system and operates 24 hours a day with temperature set points of 21 degrees C for heating and 25 degrees C for cooling. The paraffin commercial Robotherm was selected as a PCM for the current study. Various PCMs was used with melting temperature ranging from 18 degrees C to 35 degrees C, with enthalpy temperature curves are plotted in the left figure, while for the location of building was Benguiri City in Morocco, with a warm semi-arid climate. The right figure shows the temperature variations for a typical year in Benguiri City. To simulate the impact of PCMs in the typical building, Design Builder software was used as a graphic interface for Energy Plus. Energy Plus software uses a finite difference conduction algorithm based on a fully implicit solver using the following equations. As we can see, this algorithm is associated with enthalpy temperature function to consider enthalpy change during phase change. Further, to optimize the selection of a PCM, thermal and energy performance indicators such as ATFR value and energy saving are used. They are calculated according to the following equations. First result is validation of the algorithm used in Design Builder software by comparing the simulation results with the work conducted by Alam et al. A single zone building as shown in this figure was constructed and simulated in Design Builder under climatic conditions of Melbourne in Australia. The results of the indoor operative temperature are illustrated in the right figure. As we can see, the results obtained in this study are in good agreement with the results reported by Alam et al. Hence, this tool can be used to evaluate the thermal performance and energy saving potential of building integrated with PCM. Thermal comfort is highly dependent on indoor building temperature. A comparison between the indoor building temperature with and without PCMs is depicted in the left figure for 4 days in April. Indeed, the integration of PCMs results in a reduction of the daytime zone temperature and an increase in the nighttime zone temperature. As shown, the PCMs with a melting temperature of 25 and 28 degrees C are more efficient than other PCMs. The results of the ATFR value calculated for the 5 PCMs are shown in the right figure. So, the melting temperature has a significant influence on the efficiency of the PCMs. The PCMs with lower melting temperature are more effective during the winter season, while PCMs with higher melting points are more effective during the summer season. This section focuses on evaluating the building heating and cooling energy consumption for different phase change temperature. This figure shows the annual energy saving results with the selected PCMs. The higher heating energy saving is achieved with RT18 during winter season. However, during summer season, the maximum cooling energy saving is achieved by the RT28. According to these results, the highest energy saving was obtained with RT28 HC as PCM. Thus, it performed well in buildings located in the regions with semi-arid climates such as Benguiri City. As a conclusion, we can say that the performance of PCMs depend on phase change temperature, and optimal melting temperature dependent on the local climate and season. And for regions with semi-arid climate, such as Benguiri City, the PCM RT28 is the most suitable, with the highest annual average ATFR value and energy saving. And thank you for your attention.
Hello, my name is Fatima Najwi, researcher at School of Architecture, Planning and Design at Mohammed VI Polytechnic University. This project is under a research program about integration of renewable energy in the building. The project took place in the context of Ben Guerir. Specifically, it's a study of some passive solutions integrated to residential building using multi-objective optimization. This topic is actually closely linked to the energy efficiency in buildings. Firstly, I'll introduce the context of the study and the methodology followed in this research. Following this, the results of the optimization that allowed the material choose and simulation result to minimize the heating and cooling needs. To optimize the building in Ben Guerir, the following methodology was used. First of all, based on a general literature review that was concluded on the optimization of the buildings in a semi-arid region, the design builder software was selected for this study. Secondly, preparing a prototype for the buildings and its properties are specified: total surface, openings, layout, and geographical positioning. Then, two optimization studies were conducted in order to define the optimal parameters for design builder simulation. Lastly, different scenarios were proposed in order to minimize the cooling demand. Each scenario is actually a passive solution. The house is situated in Ben Guerir, a region which is under the 5th climate zone of Morocco, known to have a semi-arid climate. The region has high temperatures in summer with a very dry climate throughout the year. The case study is a simple courtyard house composed of a ground floor and the first floor. It has a south orientation for living room and bedrooms, as well as west and north orientation for the kitchen and bathrooms, respectively. With the results of the optimization, a simple combination of the construction material had been made with the use of the clay, and then in initial simulations was conducted in Design Builder software. The first concerned the choice of the material combination in accordance with the cost and CO2 emissions. The second one dealt with the openings and the blends used in order to minimize the heating and cooling needs and the cost in general. The result of the optimizations showed that the clay or earthen material provides natural insulation. The second one showed the importance of the shading and double glazing. The initial simulation shows a significant annual heat gain by the windows. It also highlights the cooling needs that can reach 111 kilowatt-hours per meter square per year. Other simulations were carried out in order to minimize the cooling needs. Each simulation was an additional solution, such as insulation, shading systems, and then the use of mushabe. The results were compared in terms of heating and cooling needs reduction, CO2 emission, and the cost. The last passive solution was in addition to the insulation, mushabe system that covers the south and west facade of the building with one mirror space of air circulation. The system was deemed the most effective by simulation in order to minimize significantly the cooling needs with a total that is less than the required value by Moroccan thermal construction regulation for the Ben Guerir zone, which is kilowatt-hours yearly. And thank you for your attention.
Well, so thank you. The papers 145, 194, and 209, they are open for discussions now. Professor Beham.
Yeah, thank you. I have a couple of questions to Mr. Salehi, paper ID 194. The first one is you are integrating the PCM to the walls, not in the roof. I think it is more interesting to integrate it in the roof than in the wall, or maybe both of them. This is just a remark, and my question is, how are you dealing with this integration? The PCM, is it encapsulated inside the construction materials?
Is the author of paper 194 there to answer
Hello?
the question? Hello. But please go ahead.
Thank you. Thank you for this question. Actually, I didn't integrate the PCM in the roof, but I think it's a good idea to work on the future. It's for the first question. For the second, I used a PCM encapsulated in the panels and integrated in the walls, not on the construction materials.
Okay. So if I can add a comment about this. When you are considering PCM panels, there may be some issues with the melting when the PCM is going to liquid phase. There may be some issues in the modeling. I know this because we had some work on that field, and we had some issues with the modeling of the PCM when it goes to liquid phase, when it is in panels instead of encapsulated in something like small spheres. Mr. Sarhi, did you?
Yes. Actually, I didn't have these issues because I used the Energy Plus that used the finite conduction algorithm, and for consider the PCM, the melting PCM, use the specific heat capacity for which is used the function of temperature with the enthalpy.
Okay, what is the thickness of this PCM material, the PCM panel with?
The thickness is 1 centimeter.
Okay, okay, so it's too small. Okay.
Yeah, thank you.
Maybe it's okay with this. Thank you.
I'd like to also make a question about this, because you mentioned that you have used this PCM located in the internal part of the wall. Why was that? Because like if you were still, maybe it would be better to insulate the wall by using the PCM in the outer part of the wall. Did you try this or?
Yeah, actually, the configuration of PCM exposed to indoor of building is the first configuration, and in the continuity of the work, I considered other configurations such as putting PCM layer on other position, like exposed to external wall.
External wall. Okay. Okay. Thank you. There are other questions also for papers 145 and 209. I have a question for paper 209. The author there. Oh, okay. I see. My question is that what exactly were the design variables that you considered for the multi-objective problem that you have solved?
Sorry, are you talking about the design of the house?
The design variables that you have used for the multi-objective optimization process. Which variables you tried to get out of the optimization process?
Yes, we actually did the variables for the material, like for our envelope, building envelope materials choice, and then with the shading. So,
okay.
So we actually tried to minimize the cooling demands.
Mm-hmm. Yeah, I remember two graphs that you had two different sets of objective functions. And my question is if you have done a sensitivity analysis to see which would be the most important design variables.
Sorry, can you repeat the question?
My question is if you have done a sensitivity analysis to verify which would be the design variables that would affect more the design the objective function.
We actually didn't do selective analysis. We actually had since Bulgaria had like high cooling demand, we directly did an optimization for the envelope because it's the one who actually leaks the more of the energy. So we did directly choose the envelope as the points, the focal points, and then the material. So we did directly an optimization around this.
Okay, thank you. Okay, questions, comments? We still have plenty of time. Questions or comments for these three papers?
Yeah, just one additional comment, if you allow.
Yeah, of course.
Yeah, about the paper 194, the selection of the PCM was done with regards to the melting temperature. But to select the suitable PCM, I think you should also consider other parameters other than the melting temperature. What are the parameters you are considering or you are going to consider in the future to select the right PCM in terms of cost, in terms of performance, in terms of latent heat, etc.
I base it on indicator performance like energy saving and ATFR value for the selection of the optimal PCM for the climate of Bulgaria city. If I understand your question.
Yeah, my question is about other parameters like cost, etc. If you are going to implement this material in a real building or to suggest this for other researcher, you should consider other parameters like cost, for example. Okay, anyway, that was just a comment, not a question.
Okay, I used organic PCM that is environmental friendly, and it's cheap compared to other PCM.
Okay, thank you.
Please, Professor Orlando, I have a question for the paper. Do you hear me?
Yes, sir. Yes, we hear. Please go ahead. Please go ahead.
For the paper 194, evaluation of global energy performance. My question is how to justify the operation of air conditioning for 24 hours in your project.
Mustafa Salihi, please unmute your mic.
Yeah, we cannot hear.
Yeah.
Okay.
I'm here.
Okay.
The HVAC system is operated 24 hours a day, just for consider the energy consumption for heating and cooling HVAC system. So the reason behind the chosen the operation 24 hours a day is for calculating the energy consumption during the period of the simulation.
Okay. Thank you.
Thank you. Other questions? Comments to the speakers? I don't see any other questions here in the Q&A. I'm sorry if I missed any of the questions before. Apologize for this. So if we don't have any other questions or comments, I ask Professor Zazi, if we close the session here?
Thank you very much, Professor Orland. Yes, I think it's time to close this session. Thank you very much for your engagement. Thank you for Professor Crarte and Professor Berardi and Professor Najma and Professor Romani and Professor Ibrahim bin Hamoud. Thank you very much. And see you tomorrow in the second session of your workshop.
Yes, thank you. Thank you. I would like also to thank the keynote speakers for the very nice presentations. Also thank the other participants. We had 6 nice presentations. And also the audience, where I noticed here at some point that we had more than 200 participants, which is this is very, very nice. Also the workshop organizers, thank you very much. It's my pleasure, great honor to be here with you again. I guess then I'll see you tomorrow. Any other? And I pass the word back to Professor Zas. Thank you. Thank you, Professor Zas.
Thank you very much. Bye-bye. See you tomorrow.
Okay, see you tomorrow. Bye-bye.
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 Thank you. Thank you.